Hát tudni kell, hogy a 10 van meg annak a kibrésznek, ami
a nyugdíj az, hogy tárgyalnak.
Reményeim szerint mindegyikön. Legutóbbi tudomásom szerint. Akkor csak jobban, hogy látni nincs, hiszen nincs kipattintós. Ja, igen, ez a véletlenül. Hát esetleg meg lehet próbálni valakinek jóféle művőnettel, vagy a... De majd nem volt ebből a volt. I think those azok egy átalakított, és akkor melyik volt az elvileg itt, ha jól emlékszem, és mindegyikben volt pontosan ilyen dolgok. Valaki megnézte ezt, mit tettem, és ilyen képen volt és hogy tett ide a másik medvédet. Most már igen. Azért kérdezem, hogy átrakni, hogy nagy én nagyon megint. Én nem tudok vele meditálni. Persze. Aztán persze indult, hogy így betem fogjuk, hogy nincs, hogy hozzá. Jobban. És van-e? Szedjem le a wifi-ről? Nem beszélj. Szerintem akkor a Windows azért azt csinálja. Én tudom, hogy én tudom, hogy de most már mindegy. Ez Windows 11. Megyek a folyamathoz, akkor gondolok csinálni. Angol egyébként csak, hogy egyszerű legyen. Magyarul van egyébként? Nem. Nem akkor. Teljesen angol. Jó, akkor igazából egy kis lehet ezt valóban. Ez mire van beállítva? Igen. Mi a jelszaveg? Melyik jelszaveg? Nem tudom, ez mihez kell? Admin, hogy engedélyezze a jelsz. Akkor gőzöm sincs mi azért az, hogy
Ezt nem veszi be ezt a izét.
De beveszi, csak engedélyezni kell azt a certifikátet
Amihez.
az Ethernethez.
Jó, ezt nem tudom most
Oké.
Jó, rendben. Akkor marad így. Akkor még viszont a másik pontban. Jó, akkor én is
Vagy mit vagy?
maradjon itt, mert ha
Jó.
később rájövök, hogy nincs akkor is jó, ezt mondjuk, hogy egy ilyen gép.
Akkor képen is van.
De várjuk el, ez az.
Csak kezdeni. Nincs már bekötve.
Nem szakmai felmondta.
Jó, azt
Nem is kell.
nem.
No, hát akkor let me switch to English because the whole program, we have a couple of English speaking guests, not yet here, but the whole event is recorded. So welcome everybody, and it's a pleasure to be here again as usually. And I give the opening words to Peter Devai, the director of the Wigner Institute, who will say something on behalf of the event.
Thank you, Gergely. It is my pleasure every year to be here and to announce the starting of the yearly GP2 day, or double day, as it became a couple of years ago. It is a privilege to be here, and also, although you are not too much present, but I know that altogether 60 people has been registered, and usually half of them used to be present, half of them used to be online. So welcome everybody. Our institute, or much more a research center, so it's the Wigner Research Center for Physics. So we are on one side very glad that this event is running. Now I think this is more than 10th, 12th, 13th, 15th, 13th. So last 30 years, many experts came together, come together, exchange ideas, learn, teach, and I think this is the main message and the main mission of this event. Also, you know very well that in these years, the IT, artificial intelligence, machine learning, which attract and really as a magnet. On the other hand, don't forget that you who are participating in such event, everything, not everything, but close, everything depends on you, who is really making it, developing to have a useful and successful meeting for the 2 days. Take your time, enjoy the speech, and I am pretty sure that, as usually, these 2 days will be very successful for all of you. And also my duty to thanks for the organizers, Gergely Barnaföldi, Tamás Bíró, Gábor Bíró, Szabolcs, the two Szabolcs, the two Balázs, and the local to make this happen, and of course you who are joining and who are present. So enjoy and learn. Thank you. Please.
Thank you very much, Peter. So as you can read from the poster and the advertisements, for Peter Lévai and István Csabai are the two main hosts of the events. So let me jump to the middle. So welcome again, everybody. This is a very beautiful day. So this is really when you have to come to the GPU day. So there's nothing outside, only rain. So let's jump to this session. So first of all, let me present the supporters of our event. So of course, the Wigner, as usual, which is member of the Ökotloránd Research Society. Quantum Information National Laboratory Stream, HPC, the Hungarian scientific funds, and of course the Lombik Limited with us since the early beginning. So the topics you know very well. So massive parallel classical and quantum computing. This is what we finally achieved as a track in the recent years, and we have very good results on this. As you know that this is just one laboratory, but we have many projects from different fields, and Gábor Bíró, created by the artificial intelligence, he asked that what the artificial intelligence is thinking as a picture if you ask what is GPU day. So that was the result. So maybe later on my slides you will recognize that how this funny pictures come originated from. Okay, so the aim of the Wigner Scientific Computing Laboratory, which is started as the Wigner GPU Laboratory, is to bring together those who are on the computational side and those who are on the physics side, and exchange ideas, help to each other, and use the strong computational power for boost physics, biology, chemistry, whatever. So the Wigner Scientific Computing Laboratory is a very open lab, so you can use different kinds of devices. So here is a brief history. Most of you already know the story. So in the early years, we started to think about how to use GPU technologies in physics, which was emerged in around 2000. Then in 2009, we formed a laboratory with just one machine with two AMD cards. Then immediately after, we organized the first GPU day, which was a very similar to this one. So there are a few interested people, and together with Nagy Máté and Daniel Berényi, who were students at that time, we started this whole series. So we pick up the thread with colleagues. We started to build up this community, and later in 2016, we started to we got too big to have only one event per year. So we have one event, the GPU days, which is an exchange between scientists. And we have another regular event, the lectures on modern computing in science, where we are teaching the students bachelor level and so on. So since 2016, we introduced this Wigner GPU Laboratory Fellowship, which means that sometimes coming people from outside can have a fellowship with us to present something. You will see many results from these fellowships during these 2 days. And in 2021, we changed the name from the Wigner GPU Laboratory. We formed a much more bigger lab, which got the name Wigner Scientific Computing Laboratory. And this is how we are running from 2021. And this is actually, we got a special stamp from the National Funding Institute. We became one of the National Open Research Institute among the top 50 in Hungary, which is a very good reputation. So here you see the aims and the origins, and today we are 4. So you will see us, and most of you know very well. So Balázs Kocskovics, the big band, Balázs Szigeti, who is helping us behind. Gábor is in Amsterdam because he stuck there yesterday, so he's on the way. And myself, Gergely. So you can ask us if you need anything during these 2 days. So we have a couple of projects to highlight. So we have this massive parallel quantum computing simulation projects, which we started 2 years ago, and we have of course, a lot of investment, which you see this in numbers, and you can see the ongoing and finished projects on this QR code. And I just would like to briefly present the hardware. So the Wigner Scientific Computing Laboratory is existing here in this building. So this is the Wigner Data Center. The Wigner Data Center room number 2 is the one rack, so each block is one rack, and the red ones are the Wigner analysis facility in connection with the Alice data analysis, and Ranka Crucero will speak about this in a few minutes later, that how she can run these things on this facility. We have the Wigner GPU laboratory, which is located here. And of course, we have the local WLEC Tier 2 sites, even the Virgo and the EUProxia sites located in different places. I don't want to go to the very details of this. You can find this in my presentation, but here you see the numbers, that how many computers, how many resources we have in the storage side and in the computational element. So here you see that we have not only the Wigner side on the VRCG system, but we have also this 8-core and the single-core analysis facility. And again, Ranka will speak about these things. Okay, these are the GPU machines, and this is the Tier 2 machines, which are also located. A lot of machines. You see you see the details here. Okay, and also the time of machines. I think everything is available on the internet. Again, for the events, so here you see the posters of the previous GPU days. So as Peter already mentioned, this is the 13th GPU day, which we are very proud of this. So this is the logo of the last one. And if you see the background pictures of the posters, now you can recognize that what the artificial intelligence picked up on us from the internet. So this is how this picture was generated. Probably that it find that these are the cool backgrounds, so maybe it can make something. Okay, another thing, the lectures on modern computing in science, which is a teaching direction, and you can follow us on the GitHub and the YouTube. We have, such as these lectures are going on YouTube as well, so you can find the earlier ones regularly. The projects highlighting, as you see, the Wigner has a major impact on nuclear and solid state physics, and which both contains physics. So we have physics, but you can find any other things, molecular spectroscopy, solid state physics, many biology and chemistry and so on. So there are many projects, but of course the main focus is on physics. As you see, the GPU days used to be very well populated within the small communities. So we usually have about 60 to 100 people, depending on the year. This time we are kind of limited due to the host of this place. And you see some results in numbers, and of course everything is there. I don't want to go to the list of topics which we have, because you will see this very nicely during the next 2 days. But let me just jump to the future. So the most important thing that for those who would like to use our machines, please go to the Grant Opportunity case or field of the GPU Laboratories web page where you can sign up with the project and you can use our facility for free of charge. Of course, if you're coming from the academic era, and if we have the possibility, we try to support also the young fellows of the community. And on short time scale, we are about to be connected in 100 gigabit to the GEM network, which means that it's much more faster connection between CERN and the other institutes. And there's also an ongoing project to get the next level KIFIS project 11, which is interconnected with the quantum laboratory people here, which will be maybe we will be a future quantum center here. Today we have quantum computing simulations, which are very, very productive. Okay, and finally, at least but not last, you see the previous partners and the colleagues from different institutes and universities from all around the world. So I think that's all what I wanted to say at the moment. And maybe that's the time we switch to the first speaker of today, who is Adam Pinter, the director of the Wigner Data Center. So Adam, please. And this is PDF, or this is PDF, yes.
Yeah.
You are speaking?
Okay.
That's okay.
So thank you very much for the opportunity to talk a little bit here. And you are very kind to invite also the IT team from the data center. I would like to talk a little bit about one very specific project we are doing. Later, if you have any questions online or in person, you can contact me. I will put my email at the end. So, as Gergely mentioned, we have an ALICE analysis facility running in the data center. And for that, we have quite a lot of hardware, but we would like to keep it in shape. And actually, we are very grateful for CERN because they left the hardware here for the future generation and for physicists to create something new. So we decided together with a team of Gergely that we are working on it and we are creating this facility. The first rack was introduced in 2000 and something, end of 2000 something. Okay, as the data center, it was started in 2012, and mainly the project was for CERN Tier 0 site, and they were here until end of 2019, so 7 years. And still, CERN is here by other projects. So one project is analysis facility. As the data center, as more, we have 4+1 rooms, and each, if we count, we have more than 400 racks. VRC as a whole is consists of analysis facility, P2 site, GPU lab. In the GPU lab, there is this quantum communication and quantum computing simulation facility, and we have also a virtual Lego development project site. Other projects we have in the data center is the ERKH Cloud, which is a great way for researchers and universities to have resources in the data center. And from that, the publication or multiple applications. And so we try to facilitate searching and reading that. We have also RP, which is a data repository project, together with other institutes from Hungary. Let me talk a little bit about the capacity of this facility, analysis facility. It was started in November 2020. It has, as Gary also mentioned, more than 300 vCPUs and 7.5 terabytes of RAM and 2.3 petabytes of storage. This is wrong, but if the redundancy is selected, I think it's a little bit less. We decided in the beginning of the project that the OS layer, so we provide the team for Bonafide Gergely, the operation, the OS disk sent to us. And after that, they take control and install what they would like to run. So basically, it's HT Condor, but I hope there will be a discussion about this later. And okay, I told you about the hardware aging. So monitoring is very important way and tool to measure and react if something is broken and to keep all the system healthy. For this, we define checks, and these checks are for specific environment, and some of them are really basic checks, just if they're available or not. Some of them are quite advanced, so if we need to program it in Python, for example, and there are some very complex cases to make sure that the system is running. Or actually, as Gergely said, 9 checks are present and working nicely. We need to do it almost in real time, so no way to turn it off. So in order to give the projects and the jobs space to run, and we define several types. One of the type is storage, the other type is work and load. Here are some of the examples for the checks. And there are the most basic checks like checking the CPU if it's 100% or 90% or 50%. For example, what we discovered by this is all the HT Condor jobs are running almost 100% on the CPU. So we need to define some method to have a little bit of a space. A little bit of a space for other processes to run. That's an interesting result from the first part of this monitoring. And also we realized that we need more spot memory for the jobs to run properly. We introduced a temperature checks. It is very important to be in range and do not overflow. Actually, for the next point, we made sure that all the data is accessible, and also for the disks on the server nodes are in RAID 1. So if one disk fails, the other work node is healthy and running. It's quite obvious, but you need to make sure these checks are running. And if we find some disk failing, then we discuss with the team from Bonafide Gergely, and we change the disk, of course. Okay, there is network connection, which is also very important. And as Gergely mentioned, we are aiming for the 100 gigabit per sec uplink. So it will be very important later. So we also introduced traffic checks to make sure that it is really valuable to have multiple connections, and all the connections should be up and running. We decided this monitoring system to run in a separate VLAN, separate network, not to interfere with running jobs. Yeah, that's what I thought. Other aspect is nowadays power consumption is very important. 2 years ago, we started to monitor all the racks, how much they consume. And from last August, we have a special dedicated system to read this data every month and every day and every, I think, 1 hour to have the power usage of this cluster. It is very important because in the end, somebody needs to pay the bill. So since the prices are going up, we need to make sure that storage, compute, and network services can be defined how much they consume. Scaling up, we decided to do a methodology to start with a small core of this analysis facility to monitor them. And after it was successful, we doubled the capacity and doubled the checks, doubled the entities we are monitoring. And we are in a phase where we have now 20 nodes for checks. And what we will have to do in the coming weeks, we have all the system monitored and run properly. We are also using automation tools because we have more than 200 servers in this cluster. And without it, it's not possible. We also introduced a historical data system. It's called InfluxDB, where we can go back in time and check how much, for example, how much CPU it consumed last week or 2 weeks ago. And we can do some very nice from this. And hopefully in future, we can cooperate with Gábor Piró and his team to make sure that it's optimized and used properly. For future, I would like to just tell you some points that since we have a lot of disks, we need to have a plan to test them randomly and not by one day every disk. So we need to spread it through 1 week, for example, and test them continuously. If something is broken, then we can fix it. We are planning also for a scheduled backup for the monitoring data. So later, maybe 10 years, in 10 years, we can go back in time and check what happened. It will be useful for the future. What we would like to do as well is basic under service monitoring to give more feedback for the team. And we are doing this iterative process, doing every step one by one and discussing what is the future and what is the most important thing to do in the list. And because this is the GPU day, I would like to go for the next infrastructure, GPU lab, and provide them also this service to monitor the GPU cards as temperature, utilization, and GPU RAM to have the most out of it, and hope we can also work together with them. Thank you very much. And if you have any questions, you can write me or ask me in the link 18.
Okay, thank you very much. We have time for questions. It's kind of early, but we still.
So you were mostly talking about the software that were analyzing and monitoring it. What about the hardware? I guess if you have more than 3,000 CPUs, then hardware failures software.
Yeah.
And is there a similar system or how to solve this?
Yes, we are integrated these questions into this one system. So we try to cover fully, not just the software, but also the hardware. So if one CPU is down, of course, we will see that the node is not available. Otherwise, if the network card is broken, we won't see it communicating on 10 gigabit per second. So we will see that. So we are prepared for that, yes.
Okay, further questions? Yeah, please.
So I'm Martha, and I would like to know how do you help the users when there is some hardware failure to maintain their data integrity, and what tools do you provide to run the program that doesn't crash and not all the simulation is in the node fast in your grid?
I think this question is for the other team, but what I can say from the monitoring side that we provide interface and password authentication for them, so they can check what failed. And the best would be to have an alerting system with SMS and email. And otherwise, for the software to test it on the grid, it's like, does it work or not? So, but I've heard that you need to try multiple times, and hopefully you have templates, so you can be sure that that works. So you just tweak the parameters, and in the end, it will work.
Okay, further questions or not related to this data center? I cannot see anything else, so let's thank Adam again. Wait. And the next speaker, we have a slight change in the program. So the next speaker will be Raluca Crucero. She's from CERN and she's responsible for a very, very important task in ALICE, that how to run the trains in multiple CT.
Yes, can you hear me fine?
Yeah. Yeah. Sorry. Today is not the internet day. And this is the time. Yeah, this is not the fun to the beginning of it. Okay, anyway, you can, if you start, then I can set it up in 2 minutes and 35 seconds.
Okay, so I guess I can start by saying that yes, my name is Raluca Crucero. I come from the ALICE experiment at CERN, and today I want to talk to you a little bit about our analysis system and what were the needs, what were the reasons why we had to develop new tools, and then which tools we developed and why. So there were a couple of upgrades to the ALICE detector that made us brought the need of new tools to handle a new amount of data that we were able to have. And whenever I have the slides, actually show you some other things, but the idea is that now we have 100 times more collisions than in the past, and for that we need to handle this amount of data in a more efficient way with new tools. Otherwise, a lot of resources would be used. So we needed new tools, and those two are the O-square system, online, offline, that is for data processing. And then we have the Hyperloop train analysis tool, which is an idea of a train system that allows physicists to integrate workflows and then run analysis on the grid and analysis facilities. And then Wigner is one of the analysis facilities that we have. Yeah, so that's okay. I think I could start by saying that the analysis train system Hyperloop is fully integrated with O-square, and the workflows that are defined in O-square can then be integrated into Hyperloop as wagons. And then in these wagons, the physicists can continue doing their analysis, and afterwards they will be able to test it in a wagon test. And if this passes, then they can compose trains of analysis that can contain multiple wagons. Successful, it can be submitted on the grid. And I will show you, I have some schemas to show you about OSPER and also about the analysis train system. And I think soon we will be able to see.
Oops.
Yeah, sorry.
I'm happy to be with this, by the way. It's my first time here and my first time at this institute, so I'm very happy to be here. Yes, so Hyperloop train system for Alice, we are mainly going to talk about the Hyperloop train system, but I'm going to introduce the OSPER system as well. Okay, so I talked a little bit about the. Does it have a point? Okay, so I was talking about some updated formats. So in Alice Director, we now have the new inner tracking system, a new type interaction figure system, an upgraded type of projection chamber, and also the OSPER dimension, which is the data taking processing infrastructure. So instead we have 100 times more recorded collisions and an increased data taking capability by 4 orders of magnitude. So for example, the resulting data throughput is estimated to be greater than 1 terabyte per second for network collisions. And a good example is that for 1 month of network data, we will create around 4 petabytes of AODs, which is the reconstruction output. So then, considering this upgrade in indications, we needed new tools to process this new amount of data. And the analysis infrastructure basically needed to handle this new amount of data in a much more efficient way. So for this, as I said, we have these two new tools, the online offline software framework that allows for distributing and efficient processing of the new amount of data, and the Hyperloop train system, which enables analysis on grid and analysis facilities. And analysis facilities, as maybe you already know, they are specialized grid sites with adjusted CPU and disk resources for analysis needs. And the Wagner is one of those that helps us the prediction. Okay, so OSPER, as I said, data taking and processing infrastructure. So here, collisions and tracks are represented in flat tables in trees that are connected to indices, as you can see here. So these are different tables that are connected to each other. This is an example. And in here, in OSPER, the user is able to define workflows. Basically, they can define callbacks and input-output declarations, which are in the form of table subscription, but they will subscribe to one or more of these tables. So these afterwards, as I said, they are combined into workflows, and they represent a particular analysis or group of analysis. And the good thing is that the OSPER data processing layer translates the defined workflows to actual ecology of devices. And the process is a little bit like this. So we said that we subscribe to tables, we define workflows, and after the analysis that we have, we get a root serial like that. So now let's see how Hyperloop comes into place. So as I said, it's a concept of analysis trains to optimize the usage of computing resources. And to give you an example of why we need to build this, the contours used in runs 1 and 2 is that we have around 40,000 cores utilized on average at any time in run 2. And this tool was used by more than 90% of the analysis. So clearly we needed some more efficient way. So the Hyperloop train system allows analysis of grid analysis facility, and as I said, it's fully integrated with OSPER. Individual workflows, they are known as patterns in Hyperloop. This is the template we use, and they can be combined into trays. Another thing that we can do is to store derived data or skin the data, if you know it this way. And this is used for further processing or also to be able to use it in future train runs. And to give you an idea, the data available is converted run to data, run 3 data in Monte Carlo, and derived data. And to make sure that everything works as expected and we have all the activity monitored and we know what happens if things go wrong, then we have full bookkeeping of several components such as data sets or run lists. We have change logs, which are basically the history of a component. For example, if a user modified the workflows or they modified the wagon test, then you will be able to see the history of this from the moment of creation until the present day. And we also have several comparison tools that I will show you afterwards, very soon. So this schema here basically shows you the main components that are used by users and operators. So we have operators from 4 institutes that work on a 24/5 shift type support and working hours. And this is very good because working from different times, so there will always be somebody, at least during the working week, that can take on the requests from the users. So the physicists mainly use analysis and nodal analysis, check the analysis to create wagons and start wagon tests. And the operators use pages such as train submission, train runs, or train issues, for example, to compose trains, to follow up the train progress, and also to check if there are some issues, for example, an analysis train is stuck in submission to the grid. Yes, so those are the main pages that are used, and then the dashboard is common for everybody. I will also show it to you later. It shows the current status of the system and the activity on Hyperloop. Okay, so to give you an overall idea, experts define data sets. So there are a couple of settings that are made, and afterwards, the user basically it's part of one or many more analysis. So within the analysis, they can enable a data set, and within the analysis, they can also create multiple values. So in this example, this user has 2 values, this one has those 2 have each 1 value. And they enable the wagon test per analysis. So depending which data set was enabled in analysis, they can enable the wagon test, which will start immediately. And once successful, it will be composed in a train. Then the train test will go on. If it is successful and there are no issues, it will be submitted to the reader analysis facility. Otherwise, it can also happen, as I said, that it can be stuck in submission, or maybe there are some other trains that are stuck and they are blocking this submission. So this is the place where train operators jump to help the users, basically trying to debug if there's something wrong with their analysis task, or if there's some problem with the system. Okay, so you cannot really see this part, but so basically the analysis that I talked to you about, they are defined in Jira, and multiple analyzers can join your analysis. There they can add wagons. So these are some snapshots from the wagon configuration. So we can see that it is the name, the workflow name that comes from Allsquare, and then we can also add dependencies from other wagons. And we support a variety of parameter types, as you can see here. So we have primitive types, we have matrices, label matrices, arrays, dynamic arrays. So there they can add multiple elements of the array. Then we also have a histogram binding, as you can see here, either fixed weight or variable weight, where we keep basically number of beans. And so if we can also create sub-wagons, which basically will run with the same with different variables. So for example, here we change these variables that we use, different configurables, and then so instead of creating the new wagons, we can just create sub-wagons and then run this all together. And once the users enable the wagon, so this is how they do it. This is the analysis page. Once we click on the red icon, we should enable the test immediately. So we can see the now it's ongoing. Afterwards, once it's successful, you can see that it starts here. Otherwise, you could have a warning, or it could also be failed. And this is how they disable it, basically. They just include the other icon. And it's quite straightforward. There's not a lot of effort to do. Once you click, everything is starting, the process is starting, and the test is ongoing. Then once it is finished, we have a lot of statistics. We have 35 statistics. We have the full test. We show the proportional set size in this graph here. And then we have information such as the input size, the private memory, the expected resources. So the users can analyze all this information before trying to let this compose in the training. We also have interactive graphs with different metrics. So the user can go here and choose their metric that they are interested in, which will just build the graph for this. And one can also click and drag in order to zoom into the graphs and analyze the area they are interested in. Something like this. Okay, so we have automatic train composition, and this one is scheduled per dataset. This is based on target memory wagon configuration and dependencies. And now it depends, because if the wagon test is failed, definitely it's not included. But if the wagon is ended in warning, it is also not included. So it has to be successful. That would be taken into consideration in the train composition that is automatic. And there are also some restrictions. So usually one is going to be if the CPU usage is too large, or if the maximum number of analysis trains per week was exceeded. And so in this case, we need to do a special request to compose other trains. And then after the train test is finished, it will be automatically submitted to visual analysis facilities. And we have a lot of statistics that we get for each train. So here you can see that we have graph that shows the files per job, the CPU time per job. We have the CPU time, the wall time in any node square, and also a job overview by state. And then we also have, similar to what we have for the wagon test, the full train statistics, and then all this information that is similar here, such as the expected resources. One can also clone the train, which means that the train will run the same model timestamp but different dataset configuration if it has been changed in the meantime. And it can also happen that we have datasets that are too large, basically, and we cannot run so often on them. And we should only run tasks that are really seem to be efficient. So for this, we add small datasets, which are also called link datasets, which are basically subsets of this. And in order for an analyzer to run on the bigger dataset, they first need to run on the small one. And if it is successful, then they request a long train. This is how we call it. And this one is to be approved by WGS. And with all this process, though, it's a long process and a lot of things can happen on the way. We have our operators. We have a dedicated channel where the analyzers can post requests for questions, and they will be assisted by our operators, which we also offer tutorials for so that they were fully prepared. So we also have organized feedback sessions so that we follow up with the activity on Hyperloop once in a couple of months, something like this. So this is how the channel looks like. This is how our request looks like. For example, this analyzer asks for 2 trains. One of them contains this wagon, and the other one also stores derived data. Now this one will be taken on by the operators, and they will compose a train on this data set here. And to make sure that everybody is updated with any issue that can appear, or if we have a new development, then we have the message of the day where we basically announce them that, for example, there's a new deployment done, and if they want any features that can reload. Okay, so how do you monitor and what we do in the bookkeeping? We have dedicated pages such as the derived data page and also the paging status page. So the derived data page displays the relation between the data sets. So here we have the derived data that we created. And on this column here, there are the data sets that use this derived data. So for example, here, there is one data set that is active using this derived data, while this one has one data set that is not activated. We have direct links to the derived data, of course, and then we can also mark this for deletion, for example, when it is not used anymore. But this can only happen if the derived data is either used in a data set that it's not activated, or it's not used in any of the data sets. And then we have the staging status. So in order for us to run analysis facilities such as Vigner, we have to first stage the data set. So if this is needed, then we expert start the process, and we have a page that basically summarizes the progress of the staging. So for each data set, then we have all the site that it was stage 2. And it's good to follow up and see if the staging is done, because then Once we know that, we are ready to compose and run the train on or SOP trains to that site. So that is very important to check this page. And then also that brings to the detailing to the detail to the transfer request. So yes, once it is done, then we can compose in the environment. Then I mentioned change logs and comparison tools. So on the right side, we have the change log for a wagon, data set, and run list. So basically what we do, we keep all the information from the moment of creation until now. This can be used, for example, if we have changed the wagon configuration and then the wagon is failed or creates a warning. So then we can just go back to see if we can find something that has changed within this change log. Then we have comparison tools for wagons and trains. And you look something like this, for example, this is the train runs page where we show all the train runs. And one can just select the two trains that they want to compare, we will open this new page. And as you can see, there are a lot of details. For example, we can observe that these two trains have completely different wagons, but they also have one in common. For example, if something happens in Belgium, we can find some problem in this wagon here, and so on. So we can easily find relations between these components. Now, the important statistics, I briefly mentioned the report at the beginning. This shows the overall status of the system. So we have information attached the number of trains that are waiting for the job submission. We have the number of running tests ongoing. So a lot of information such as the average completion time. And then below we have a summary per site. So we can see that we did the overall. And for example, we can also see if something is stuck in one of the sites. So this is very useful. Many users are the experts, but users can also go here and have a look. For example, if they are waiting for submission, they can check this box here. So in total, we have 200 analysis and around 240 data sets. The total input size right now is 160 petabytes, and in total, we have around 5,600 train runs. We have converted run to data and run 1 and 2 data to OSPARE, so to OSPARE format. So we allow analysis with all data from runs 1 and 2. And there's an ongoing QA of the multi-cloud data. And here is a snapshot from the statistics page. This page contains graphs and also 3 tables that summarize all the activity on Hyperloop, and the timeline that you want to check. The activity is also customizable, so you can choose from 3 years ago, for example, and you go until today, and then you just build this graph here. So, for example, from here you can see. So we have the number of trains and then the duration. You can see that at the end of 2022, start of 2023, we had an increased number of trains submitted. So increased activity because we obviously started around 3. So activity increased. And with this, we also see that the running time also increased because we became more and more busy. So we can now obviously see how we need very efficient ways of doing analysis. So there's a lot of activity, especially since the beginning of run 3, and we need a way to have real-time data to everybody at all times. We have real-time updates to WebSockets. So what this does is that depending on which component of Hyperloop you are in, it will be automatically updated. For example, the status of a data set or the status of a wagon test or a train run. So then the analyzers can just focus on physics, so they don't need to reload pages or anything like that. The only thing that maybe we don't do exactly right away is when you remember the train runs page, we could add basically train runs whenever they appear, but this will maybe make it difficult for people to see and read through the train runs. So for this, we just show notification and then it can reload whenever they want the new train runs. We also have personalized notifications to the users. We also send emails, for example, when train test has failed, or also when it is successful. So they are updated at all times. And then we have extensive documentation, which is accessible from all over the UI. And now it is completed, and with every feature that we have, we updated the documentation. Okay, so as a summary, as I told you, there were a lot of upgrades to the Alice detector, and it brought the need of more efficient tools to deal with the new amount of data. And here we have the OSquare framework and Hyperloop. So OSquare framework allows distributed and efficient processing of the data, and Hyperloop enables analysis workflows to be run with analysis facilities. There's a lot of automatic activity such as the general composition and permission, and this means that less actions need to be taken by operators, and also this also means that there is much less waiting time for analyzers for their analysis to be submitted to the grid. So that is very important that you focus on analysis. And because we also have real-time updates and personalized notifications, then you don't need to reload or go to other places to search for the information. So this means that they can just focus on their analysis. The user interface, we developed it with React, and React helps us have a very interactive UI, which means that a lot of things are very flexible. Users can customize what they see on their page. So everything is personalized, and there is immediate actions when they place a button, for example. And so we needed to test this, and for this we use new advanced tools such as Chat and Puppeteer. These are new frameworks that are very useful to test both the functionality and also the UI experience. As I showed in the previous slide, we have access to statistics, overview, dashboard, and documentation. And one thing that helps us a lot is the support of our operators that are always there, maybe even in the weekend on possibilities, and then have the analyzers. So with all these developments, then we have a good ongoing of the analysis inventory, and we have good feedback for the interactive user interface, and also for the more efficient way, less waiting time, and faster analysis. We are still progressing. We can add also new features. So it's now it's fully functional. We are thinking maybe we can improve some things, but the analysis is going as expected. And yeah, thank to all my informatics for the development and also for the analysis. Thank you.
Thank you very much. Time for questions. The audience.
Thank you for it really looks like an amazing system. And so I am not in the field, but I know other workflow systems like Nextflow that is working over Docker, and they have a similar words like Wagon and containers. I guess there are something. So my question is that is this huge and really nice system that can handle the price of data and workflows. Have you thought of generalizing it or reusing it for other purposes, like for genomics or any other fields that they are also struggling with handling big data?
Yes. We actually had this question at iChep last year, and so now it's pretty much dedicated for Alice, but from the development that we made, it could be at least taken as an inspiration for using it for other purposes. The UI definitely, and then the analysis part, the processing of the data as well. Now it's quite dedicated to specific physics analysis from Alice. So it will be more difficult, but I believe it could be done. It's just that I believe it would be more taken as an inspiration than to raise it at the moment. Who knows? Maybe we can make it more generalized. Yeah.
Questions? Maybe one more question. I would like to ask for some details on how do your users access the data. I will explain why, because I'm familiar with a much smaller data join where you store the data and derive data in relational databases. And if you change something on your analysis, like you add a parameter to your function that previously computed data is invalid for the new definition of the function. So how do you prevent that? How do you access your data without losing previous calculations? Thank you.
Yes. So we keep everything, in any case, we keep everything, so now if you change something, it's still gonna be on the record, so we could quickly go back to that. But yeah, this actually happens when somebody changes a function and then the test failed, the analysis fails, not something is not working. So for this, we actually have notifications for the users. We have nightly tabs basically, and whenever a user enables a button, you will enable with that tab, and that tab basically is the current workflow, the current state from OSquare. But you can also go to a previous tab that has your previous function and so on. Or if you see that it's not compatible, then you can modify your configuration if possible to be compatible with the new tab. So, and then we keep track of all of those, and if one wants to use an older one, can use basically the older tab. And because we keep track of everything and we notify them all the time, they will see something like the configuration is not compatible with the OSquare workflow and so on. So they are right away a notification appears that they try to enable. But this is how it is.
Thank you.
Yeah.
This is not a question, but a suggestion for particular purposes. On one of your slides, I noticed that the problem is that you are using lead collisions, and that generally specifies data. The problem may be that the chemical symbol will be CP. Generally specifies data. You will use air view collisions. It will only generate
Yeah. It's not that.
Such we get past the others management.
Yeah, I will pass the phone.
I would like to ask if you see some bottlenecks in the system from the CPU side around the RAM or anything storage as a whole in the merge.
Yes, so yeah, you finish right. So the bottlenecks right now is that we mainly use a grid single core and then also 2 cores and so on. And what happens is that we have a lot of activity in the grid single core and a bit less activity on the other one. So it can take much longer to finish analysis. And for this, actually, we have a plan to develop pipelines so that we basically split all this processing, and then it comes together at the end. So this is actually in our plans because the activity increased during round 3, and we saw how, for example, there were days when it was so busy, then the trains took a lot to be submitted to the grid because there was so many trains. So I would say this is one of the bottlenecks.
Further questions? We still have time. Okay, then I will ask a question. So how about to use the more parallel, more deeper architectures like GPUs or FPGAs or something in the future with the same system? Do you need further development on this, or it's kind of okay, it's simple but easily applicable or transformable to that one?
We would need to do some development. For example, when we started to use high performance computers from the LCA mobile grid, then we needed to do, there were some improvements that were done in the processing. So definitely we would need to change a little bit, but it can be done because we also did this for the high performance computers. But you will need some development. Yeah. But yeah, this is really very useful. So in any case, we are, I mean, at the moment everything is working as expected, but we still have a long list of things that we could do and improve. Actually, ideas are really welcome because we want to basically make this tool better and better with time. And now we learn a lot from Launchpad because there's a lot of activity.
Maybe one more thing that you just, can you remind me that which centers are for providing this continuous support from around the world? Yeah, it's Wigner and GSI. GSI. Yeah. At the moment, we're in GSI, just these two. And then of course, do you know any other further sites which are planning to turn to the same direction? So I am not sure. Maybe in the future. I know that there is a lookout for new ones so that we can basically make it more efficient, but I don't know about exact specific ones yet. I remember something on the connection with Kisti or yeah, there was a discussion I think about.
Peter Vivai, just a short question. In one of the documentation, I have read that the CPL loop system is generally was invented from Facebook and
Yeah.
so now bugs me that generally you could renew a complete system, or could you just comment that which part has been learned from the commercial side, or why that was important?
Yes, yes. So how can I say? The only thing that comes from Facebook, so React, the framework that we use, is a JavaScript framework, and it was developed by Facebook. But the framework mainly helps us to make a very nice interactive UI. So the part that actually processes the data is not at all inspired by React is also used by Facebook indeed at the moment. And it's a JavaScript library, so it's starting to be used, and what clearly like a lot of features that make, let's say, a good experience for the user. So the only thing we are not really dependent on that because it's JavaScript, but basically in a framework. So even if there will be something wrong with that in the future, then we can just use another framework or just pure JavaScript. So it's mainly dedicated for the nice interaction pages. That
Thank you.
Anything else? But I still have one. Is it hard to go to higher number of cores with the system? So does it have a limitation? I mean, we have this limit. Assume that we have infinite time motivation, but that's it. Does it make any sense? Have you made any optimization for the 8 cores, or is it better to go higher?
So even at the moment we have, let's say, rules for using more cores and limits as well, memory limits and so on. So we only run those when it's needed, and there are specific limits. And I guess if the analysis would be really, really heavy, then we would use more. But for the moment, we have regulations even for those until 8. So I guess we will have to see. Okay. And again, if that would come, to not use it very often, or use it very rarely, I suppose, when we have analysis.
Okay. Thank you very much. I think we are fully exhausted. So thank you, Ravi. Yeah. And I'm trying to download the next talk, and I'm asking Balázs Bánder and Anna Horváth. This way. This one. Okay. So this will be a specific talk on a kind of funny project we had during the previous years together with Balázs and Anna. Balázs is from the Technical University from now, and Anna is from my research group. So this air water temperature difference estimation from mirages based on learning. So please.
Hello, my name is Balázs Bánder. The last year I also worked here at Trainer, the part-time researcher, and similar presentation about base simulation, and we will continue of that work. And today I will talk about the importance in real life. The network image generation to digital network. conducting machine learning, evaluating the network result on generated data and on real life data. So about Mirage, how the Mirage occur? It has happened when there's a surface like a water body or pavement or ground or whatever, which is warmer than the ambient air. And these warms are the lava regions of the air. And it will develop a temperature gradient just above the ground or water, which has an exponential distribution of temperature, and it reaches the ground or ambient temperature quite soon, around 20 centimeters above the surface. And we can see the higher temperature difference between the surface and the ambient air, the larger the gradient is. And by happens the optical phenomenon, the higher the temperature and the lower its index of reflection. And this is actually what happens here in the observer. And if the light is coming from this object downwards towards the surface, it will bend on the lower regions of air near the surface, and thus this will arrive at the observer eye. And here's a real life example of Mirage. The photo was taken in Balaton, Balaton Hangars, and here's what actually see. This is the object, like the distance, and rays. Of course, part of the rays are coming to the observer, normal upright rays to the air without the bending, and the other parts are just get bent. And in this case, we will see the instant image near the ground for water. And this can also be simulated in a laboratory environment using the sugar solution in which the concentration and the reactor index of diffraction, and it creates the opposite phenomenon. And why it's important in real life. This can be quite important for today's development of autonomous vehicles, because Mirage is the decision making of the systems, and always kind of important in space research or exploration. For example, the Planet Mars. If the rover sees something of this form, he or the researcher should decide if it's a mirage or a real day on the Planet Mars. And to be able to train our network, we needed a source of picture images, which is not available in that or in any database. So we had to generate them. And first I started with this sort of images, but it was too versatile and gave probably result. So I went more specific and decided to late landscapes in which there is an overcast sky, some hills in the distance, the coastline, and the water body itself. And he is simulated mirage. The simulation of this field is based on Kelvin noise, which is dedicated developed decades ago for computer graphics applications. And in these images, we can vary the pace of horizon, the shade of water, the water fracture a little bit, time shade and contrast, heat shade and contrast, and heat shade and contrast. This is for coastline. And this way, it's possible to train the network to a wide variety of real life light scenery. This is the way we construct the images. First, generate the sky, then have water, then before the sky, we place the hills, then the coastline, then we need some post-processing to hide these aspects, to let the image look more natural, and also add some bad noise verification to the and the randomness to the horizon in order to prevent the network learning the very straight lines. No machine learning using this data we can only do supervised learning, which means for each image we also generated or provided the network the temperature difference used to generate the mirage and distance of the speed from the observer or camera, and also the field of view. We use TensorFlow and the Keras API, which is a very nice Python API. Because they are very well documented and well supported. And the nature of the problem calls for convolution network, which is really for pre-processing. And all of our input images of this type and grayscale. And for this, so this is our network. Actually, this is my very first deep learning network. It's a very regression network. It's not for classification, but outputting analog value. Here the time difference between the surface and ambient light. We have around 1 million kernel parameters. These are the most important parts. The convolution blocks, which contain the three-layer convolution layer, an application linear unit activation, and multiple intended declination layers. We use a support of 20% provide overfitting. And this is to input network getting one input image and the other input the field of view and distance is the data image. These are what training we use the website of 32. Seeing such 5 or 5 million, the addition was 120,000 and use the initial learning date of 1,000 with a dicta rate of 5%. With Adam optimizer and started with 30 apples, but the convergence was so fast that after 4 epochs, we already put in the results, and all the training went under Ubuntu Linux on this hardware, and we use the disk-based image cache to speed up the training process, although generating images not, I don't know. Perhaps 12 people generate 4 to 6 images per second. So it's not that slow, but the training was much faster. And Anna, please continue.
So this is the testing part of the program. So first we tried did the testing on generated pictures. So this shows 1,200 pictures that were generated artificially, and then we tried the algorithm, the machine learning algorithm, to predict the temperature in these pictures, which was of course known because we generated it with the large temperature, so this is the input parameter for the image generation. And this plot shows on the x-axis simulated depth, so that is what we know, and on the y-axis there is a prediction, and this should of course fall on the identity, which is denoted here by the blood type, and there are 3 different differences for the object. How for the object was that we can see the mirage of, and the red ones are the 4,000 meter ones, the green is the 8,000, and then we have the blue, which is the furthest away. This is 16,000 meters away, and we can see that the red ones, which is the closest to us, is predicts smaller temperatures, smaller temperature differences, but the other ones, the higher distance ones, are slightly lesser in this picture. And here's the error show. This is for the 4,000 meter case, and we have different object heights, and we can see that the blue one is the shortest object, and in that case the error gets larger. This is because the object is too small, the mirage effect is not yet apparent, and also there is some noise added at the water surface. So if we have just a small object, then this introduces much more noise, and this could make inference harder. So in that case, it doesn't work very well, but for the other ones, the error is quite low, it's within like 0.5. And we can also see the deviation of the error, which is indicated by the test. This is the same picture for the 8,000 meter case, and again, what we can see, the object height is scaled is not the same as in the previous one, because then the smallest one was 20 meters tall, but in this case it's 40 to scale together with the distance. But again, what we can see is that the shortest object has a larger error, and the other ones are has a similar trend how they go when they basically go together, and they also have a smaller error. And in the case of the 16,000 meter distance from the object, you can see that the errors get higher, and also we have a different trend than from the previous ones, but again, the error is the most prominent for the shortest object. And here you can see all of them in once. So in general, we have a mostly linear correlation when the object is not too small, but there are some errors that are coming from different facts, different places. And one is that if you have a small object size with either blue curves, then it's not going to be very good. The predictions won't be very good. So it's approximately if the h over d is less than 1%, which is the height of the object, and is different from the object, then the inference won't work properly. And we have also some problems on the edges of the temperature difference domain. So for zero temperature difference, which basically means that there's no mirage, and also at the other end there's a higher temperature difference, and we don't have any data that's a higher temperature difference to teach the system also introduces system error. And so the best predictions could be expected when the difference is not very large, because we can see that at 16,000 meters it's already most likely wrong, and of course this comes from limited resolution because we are doing ray tracing, and the further the ray tracing needs to do, the bigger the errors that the committed error, and also Earth's curvature plays a quite important role at the distance. This also introduces non-linearity, so it's much more difficult for the system to learn. And for small distances, around like 1,000 meters, it's not really, you cannot really talk about the mirages anymore, because it's just not going to, the whole mirage won't form. I think in case of larger distances, we won't have a real upside down image generated, so it could be probably more difficult for the system to recognize it. So now let's see some real pictures. So we went to the Balaton and took some photos, 4 of them all together. And here you can see the places of the photos that were taken. So the blue camera sign shows where we took the photo, and the red shows approximately where the object was. But of course, it's a bit difficult to tell where the object was, since we can see in the photo a large part of the shore, and also buildings and other objects that are further away from the shore. So it's not that exact to tell the distance, and also distance is a parameter that goes into the model when it's predicting the temperature difference. So it's a bit difficult to tell the distance, and we also have to tell the model the field of view, but that is more that is easier to display because that could be just done with the camera. So these are the pictures that were taken. These are already cropped, and they converted into black and white, and also there is some increase in contrast. And some possible error is the lighting and shades. For example, on the upper left image, there's a white kind of band, which is could be many things. For example, sun shining on the water, or maybe another partial mirage, and those things get introduced somewhere. And also the resolution is not very good, as you can see. And the contrast increasing method is also, I mean, it's a bit arbitrary, so it could also introduce some errors. And of course, the measurement of temperatures and distances are also problematic because you don't have to give the temperature to the model, but we need the temperatures to tell if the model is performing well. But it's really difficult to tell the temperature of the water, for example, because first we need the temperature of the water surface, and meteorological data is not about the water surface; it's about the water a few meters deep. And also these measuring stations are there's very few on the bottom, so maybe it's not at the same location where we needed it. And to tell the temperature of the air is also problematic because that varies a lot on a few kilometer scale, which we had. And yes, so I think it is there. And here and measurements that we had. So the gravity predicted is what the program predicted, and we had the gravity which was what we measured. So, for example, we can see that the last one we measured zero temperature difference, which is not possible because there was a mirage, so there had to be some temperature difference. But this shows that it was difficult to get the data. Now we are trying to get some satellite data so that maybe that will be better. And yes, but we can see that in some of the cases, actually the prediction was pretty good because here is the difference between the predicted and the likelihood is the last column. So in cases it was less than 1 degree Celsius, the difference between the prediction and the reality. So that's not too bad. There are other cases where the error was larger, but yeah, we are still trying to get better data because also for pictures are not a lot, so it's difficult to tell how good is the performance of the model. And in summary, so our goal was to obtain the temperature difference between the water surface and the ambient air from images taken of mirages. And the method was to generate first artificial mirages because otherwise we didn't have enough data to teach the network. We do our pictures, and we use the convolutional deep neural network and supervised learning to train this. And the result is that the inference works pretty well on the generated images, but for real life photos, it is difficult to tell if this works well or not. But it's promising thing, and some more research should be done. Thank you.
Thank you very much, and Balázs, and I really appreciate that you could jump in because that was its focus scheduled much more later on. So, questions for the audience?
I'd like to ask collaborate with additional motion techniques.
We can hear very, very.
Sorry.
Sorry.
Collaborate with traditional motion techniques. How to get backup images relation. It's in the artificial landscape trend. You had review as the pipeline of additional Carrying generators often. And maybe if you are collaborating with them, and it has the steps for generating images or motion graphics. And they try to raise physical handling focus that they can. But you know, motion graphics it's not the same as typical motion analysis and that kind of things, but with artificial images, maybe you should contact with them because with the help of them, you could have for getting images particular or landscapes and I know that artists and they like to find different settings and software developers wants to integrate different settings into their software. So if they don't have these kind of settings, we can have you each other. Images and our purpose.
But I think this is probably just to do it, but it's a good idea. More pictures.
Maybe I just want to comment this. So it's very hard to include a standardized outline the physics what we coded in on the image generation. So I think that's one of the crucial problems. So we have to develop the pipeline for ourselves in order to have this focus. So I mean, of course, there are many things available. You can buy, sea islands, whatever you have to do. That's for your next movie, but usually there's no image generated for the system. So this is one thing that is extra.
So if you will have a follow-up field session island, I will be volunteer too. But seriously, so my question is, have you tried to analyze neural network that you have called? So how it can estimate the temperature? So looking into the neural networks for using GradCam or other methods for explainability. We had a similar project where we used gravitational lensing and inferred cosmological spikes, and it was really useful to look into the neural networks, check the various convolutional filters, how they like, and find some explainable features how we can estimate the temperature.
We're also looking at the pictures of the brush for that thing.
Thank you for the question. We have looked at feature map only for more or less like fun, and could observe that some features insight on coastline or other than the water and these things, but on a scientific basis, we couldn't contact anything of these data because this was my very first network to teach, and the time was out.
Okay, further questions? Maybe I comment.
I can talk about it. First, try to analyze if you have the temperature, know how is the temperature. Can you guess the distance between those parameters I've seen? Because I've seen different types of temperature correlations. So maybe it's interesting question to analyze how much is the distance.
Yeah, I think that's the question. I don't think the distance could be, provided you have the angle of field of view, then you can take the distance and have a potential. But we need at least the distance for the angle of view in order to for the method to work. Because if you go to the scenery, you see a distant thing with a small angle of view can coincide very well to a not too distant field with a higher angle of view, which means small mirage can also mean a small angle of view, but also a small difference in temperature.
Yeah. Okay, so maybe I can answer. So what we faced during this project, one of the hardest things to give to provide the temperature difference, because as Anna explained, that the temperature which is provided by the National Weather Service is measured as 2.5 meter high from the shade in a nice way, whatever. So this is very nice, but this is really not the temperature what we need. And the same for the water, which is actually funny in case of Balaton, because if you want to have a precise water temperature, you have to go below 2 meters, which is very hard to do in the south part of Lake Balaton. So, I mean, we are really searching for precise data. Once we have a precise data, then we can have a much more precise correlation. And that's the point when this was the discussion I asked you a few months ago, that how to use these heat maps in order to see that which are where are the main focus in the network itself. And then maybe we can go further. But so now we have the access to the data, which is kind of funny. So you have the Hungarian map and you have dots which are changing in time and space, where the satellites could measure the points, and it's really not trivial to handle, but we are on it. So anyways, thank you very much, and thank you very much for Balázs and Anna. We have a short topic break. We will start again at 11. I really ask the speakers of the next section to come and put the talks here, because I don't want to waste all the blue snake and waiting and hesitance. So thank you.
Én elfogadtam órákkal délben, és jó, hogy a saját előadásra
A legtöbb fog töltöltitek, mert akkor és most letöltünk a picture-et. Pont 3
le is tudom, vagy nem tudom hova tenni, egy honlapon fel van.
Szerintem fiú, hogyha most behozod, akkor izé a ja, bocsánat.
Igen.
Hello. Jó. Az a
Ez most megvan osztva?
A videó, a kamerakép, igen. De bocsánat, a kamera nézi a kivetítőt is, úgyhogy végül is igen, a képen nyomok nincs.
Jó.
Közben rájöttem, hogy nincsen screen sharing, hanem hogy a kamera nézi a kivetítőt, úgyhogy nincs mit tenni.
De nincsen megosztva, vagy nem, jó, nem csak. Duplikáció van, igen.
Hát én ezt nem biztos, hogy be fogom tudni.
Yes.
De csak már még be kell tudnom még egy szót.
Már is jó.
Uram, az van akkor.
Akkor te vagy a második, ugye? Akkor szerintem azt csinálják, hogy akkor leemelnek az egészet onnan, így szintre, ugye? És akkor te föl tudsz költözni.
Az lenne jó, de legelőször igen.
Lehet, hogy ezt láthatom valaki, nem látom.
Akkor az igen fölmecsolok egyet, amíg rá. Ez nem csinál fel semmit. Adjad, csak egy pókot fölmecsolok. És akkor utána úgy van itt emberek, vagy el tudod inni a nekem.
És mi az egyik szép?
Szélti pont Balázs.
Jó.
Minden pont
Elküldöm.
A PDF? Jó, hát nekem mindegy. Hát ahhoz egy mesterséges intelligencia kell.
Biztos, hogy már érni az a baj.
Hát megkérdezem a lányomot, most érették. Majd még egyszer, ha feltetted az indikúra. Indikúra feltetted. Nem Ethernet kábel, nem tudok megoldani, hogy visszaadom.
Ja, jó. Ahogy gondolod, ezt is kérem, ez is az enyém.
Tudom, csak
Így aztán ma holnap meg tudnám oldani, de holnap. Köszönöm. Szóval,
Neked nagyon. Szervusz Pista. Merre? Az neked probléma, hogy akkor megcseréljük, viszont utána nem tudok megcserélni. Hogy van, talán úgy van, ezt leteszem ide, jó?
Ezt megfelelően.
Ezt meg feltesszük oda, és a hang az kívülre azon keresztül. Hát le kell látnod.
Hát ha jól értem, akkor igazából ezzel nem kell semmit csinálni Zoom-mal, hiszen screen sharing nincs, hang nincs, videó nincs, erről.
Igen, holnap vagy egy picit téged Zoli, te leszel az első,
Jó.
Vagy nem, tök mindegy.
tök mindegy.
Vagy nem tudom, hogy tök mindegy, de...
Maximum picit feltötted, letetted, és le is törölheted, hogyha...
Jó, nem tudom amúgy. Igazából nem nincs mód.
Költségvetés az esetleg. Itt talán ez. Jó, ha ez jön egy ez a szigeti Balázs. Ja, akkor vele. Bocsánat, nem néztem most. Jó. Bocsánat, csak nem kezdettem még Windows 11-et. Nem csak odaírom. Ezzel lehet majd irányítani, csak most éppen kiveszett. Sok fősz, én meg neki ez. Hát,
Ja sitä secondo mutatkozom meg. Könyves Ferem.
Leoszki Zoltán.
hát, Zoli, majd az evébe
Aztán
most szerintem cseréljük be. Akkor neked mi kell?
Hát ez ide átraknám, és elveg sem kell állítani.
De arról osztod meg a izét? Nem kell széthúznom a...
Nem kell széthúzni.
Oké.
A
Értem.
kamera nézi a képet.
Ezt
Viszont az esetben igen, viszont a kivetítőre, akkor bocsánat, még
akkor kivetítőt beszél. Átbuszolod, vagy ki tudjuk húzni ezt?
my thing.
Is that one that you say?
Igen, sajnos ennek kell egy külön tápasztálni. Így van. Igen, hogy egyszerűen.
Ezt ide, másokra teszteljük oda, és akkor azt el fogjuk kapni, és akkor nem csinálod.
Ja, ez a tárgy.
Hogy ezt azon az egy porton keresztül.
Nem, csak ő pedig így adalma mind a kettő.
Jaj. Bocsánat, belőle.
Szerintem így jobb is van, akkor összeadni. Kábel volt, igen, az olyan.
Akkor én is letöltem ide. This done, and there is something new.
Okay, so we will continue the second part of the morning session. And I'm very happy to introduce, for those who do not know, Zoltán Egoszky from the Longleaf Limited, and we are almost since from the early beginning, and you were a young student and active as in the first few days, but today Zoltán and Bence has a big company as a important in the Hungarian companies. So they are regularly coming to visit us, and we have a joint project as well. So now I give the word to Zoltán to speak about the open source automatic FPGA acceleration of massively parallel .NET code. Thanks.
Yes, thank you very much for the introduction. And it's let's see.
This way.
Nice, probably better. So, thank you for the introduction. And yes, it's great to be again here in this citadel of science, Valava, the city. It's a very, very picturesque place as well, and great talks today. For those who do know me, I hope you won't get bored because there will be some similarities with previous talks. But the keyword here is open source. A little bit of interaction. We already heard that I'm from a company called Longbeek. We are in day-to-day, we are doing actually web development with a content management system called Orchards that's built on the framework .NET. And that's what the project that I will show you is also using under the hood. Because when we are not doing web development, then we are doing research and development. We have a couple of projects, we have a couple of partners in the academic sphere. One of them, and probably the most important one, of course, being VNAP. But even before that, let's talk about you, all of you here. Let's suppose that you are some researcher who does some number crunching, like on the previous talks. And I mean, when I'm saying number crunching, I mean something like AI, machine learning, like in the previous talks, or image video processing, like in a few next talks, I think, or something probably more closer to the natural sciences, FFT, or Monte Carlo simulations, or something in the data compression space, cryptography, something like that. Now, let's suppose that you have a software and you want an algorithm and you want to make it faster. Now, of course, there's the usual runbook. First, of course, you can try to make the algorithm itself faster. You profile it, you figure out where it's slow, and let's suppose you have already done that, it's as fast as it can be. Secondly, you can employ more CPU cores. You can employ more servers to begin with. You can parallelize it. Let's suppose that you have already done that, and of course you can also always, not always, but most of the time, scale up. You can use more computers to begin with. You can use better hardware. Let's suppose that all of these are already done, and then you are at a GPU day, because the next step is heterogeneous computing with GPUs or with FPGAs. So let's talk about the last part, FPGAs, a little bit, because I'm not very good with the GPUs, but FPGAs a lot more. Now, I suppose most of the people here know FPGAs. Have any of you, who are the people here who actually worked with FPGAs before? Well, a couple of people, yeah. It's a lot more people who work with FPGAs here than usually on a software developer meetup conference or something like that. So good job, everyone. Well, for the others, FPGAs or field programmable gate arrays are pretty much chips that can be reconfigured. So if you want some kind of image processing, well, let's call it, or you can configure an FPGA to behave like that. If you want to have a piece of hardware that does some Monte Carlo simulation for you, you can configure an FPGA to do that within its limits, of course, because they have a certain capacity. And that's the point. You pretty much can get a dynamically reconfigurable piece of logic hardware. Now, why are we doing this? And why am I talking about FPGAs here when it comes to compute acceleration and not hardware design? Because FPGAs are also used for hardware design. Of course, that's their original intended purpose. Now, this is totally non-scientific. That's why there are no labels on the axis, actually. So you can't quote me on that. Why are we using FPGAs? Well, because they have some unique computing benefits. Because when it comes to parallelism, I would say that, again, in very non-scientific, broad terms, GPUs win. They have thousands of little processing cores, while CPUs have more like dozens of cores. And FPGAs are somewhere in between, although they don't particularly have cores, although that's not true for every FPGA. But usually the level of parallelism you can get there is in your many hundreds. Now, the complexity of programs is the other way around. So what you can run on such computing devices, what you can compute, I would say that on a CPU you can compute anything. On a GPU, the programming model is much more limited, and FPGAs are again kind of in between. So the algorithm you can implement on an FPGA, the complexity of it, the flexibility of the programming model, in quotes, is kind of in between. But there's power efficiency, and power efficiency is where FPGAs really shine. That's most of the time the points why we use FPGAs. When you have a lot of stuff to compute, but you have a power budget. And power budget is also dollar budgets in the end, an embedded system doing edge computing, but it's also important when you are in the data center because, well, you can't just use any amount of power, you can't just spend any amount of money. And FPGAs are really power efficient because they just compute what you need to be computed. It's not a processor that you program, but it's a chip that you configure. You kind of implement your own processor. There's no operating system to run. There are no other softwares. There's no memory management. Nothing. Is just bare metal what you need to do. And that's great, but there's also a downside. The downside is that it's very hard to utilize FPGAs. If you have done some programming, I would assume most people have done some kind of programming here, then that doesn't translate at all to FPGA development because it's super low level. It's you are not writing a software for a program, it's a software for a processor, but you're implementing your own processor. You have to think in terms of wires and logic gates and clock cycles. It's fun, but it's also very hard. And we intend to bring all of the complexity of using an FPGA down to the software level we have here. So what is it? It's pretty much a tool that can take a computer program and turn it into a piece of FPGA logic. And not just any computer program, actually. I mentioned .NET in the beginning. We are actually talking about .NET. Now, if you have heard of .NET of the old times, this is different. The .NET as of today is open source, cross-platform, and supports a variety of languages, including functional languages and including even scripting languages. And has their processes that converts into an FPGA implementation. Now, if you haven't worked with .NET before, then you may ask, okay, I know Python or probably C++ or something like that. Why would I use .NET? By the way, if you know Python or C++, you can already use .NET because those are supported languages. But on the right, if you are new to programming or if you are new to solving an algorithmic problem with program, then .NET has the advantage is that it has a huge community. It's a modern mainstream platform, a lot of modern development tools, and it's completely open source, including the platform, including some of the operating systems it runs on, of course, many Linux distributions, and including the development tools. And Haskell is open source as well. So everything from A to Z can be open source. So to summarize, before I show you the whole thing in action, as part of a demo with all of these buyers, what we are looking for here, or what we probably achieved here, is well, getting the benefits, the computing benefits of FPGAs for all of us software developers. So you can get the performance benefits if your algorithm is massively parallel or compute and compute or memory bound. And secondly, you get a higher power efficiency. Hence, all this is software development more or less as usual. And now let's see the whole thing in action. What I'm showing you here is a terminal window that's less spectacular, but what this terminal window is connecting to is actually this device here. This is a development board, so when it's actually put on board of a drone or on board of a satellite, because this is a thing that actually used in such implementations, then it's much smaller. This is an FPGA board called from the Zynq family, from a product family called Zynq. It's an ARM CPU together with an FPGA and a couple of peripherals, some memory, and a Linux running on top of it. Sorry. And from my laptop, I'm connecting to this, and well, I'm running a demo. I'm not live coding that because that would be a little bit slow. What's happening now on board of this FPGA board is that, well, the script is starting. First step here is converting the .NET implementation of a program that I will show you a bit later to a hardware implementation. And then it runs the software implementation. And after that, it also runs the hardware implementation. So we will be able to do some benchmarking. Okay, this happened. So let's drill a little bit into the details. So first there was the software implementation, and that took about 25 seconds. So that was a little bit wonky there. So we have done 25 seconds of computing. Let's see how long it took on the FPGA. And on the FPGA, it was executed 3 times, just so we can have a better understanding without the initialization time and everything. And there it took around 200, let's say 50 milliseconds. So 25 seconds versus 250 milliseconds. Now, this is not the speed up that you get every time. Your mileage may vary, of course. And I will show you the specific algorithm that I used here in a second. But this is to give you an idea that 1, 2, sometimes even 3 orders of magnitude speed up is possible. And similar or even better power consumption or power efficiency increase as well. So that's something worth checking out, and it's quite easy to prototype here because, well, it's software development. Probably the hard part is figuring out which part of your algorithm is suitable for such acceleration, so which part of your algorithm is highly parallelizable, and as mentioned, compute or CPU bound. Now, what I've actually run here is here. And so the code is nothing really that would be a real life algorithm, but kind of an exaggerated example of the kind of algorithms that you would utilize massively parallelized compute accelerators for. you may have guessed from the name because it's called parallel algorithm. Now, what it does is that here's the main thing. If you haven't seen C# code, because this is by the way C#, don't worry, there will be nothing that's perhaps not ordinary English. Maybe I'm stretching ordinary English a bit here. What happens here is that the core of the, let's call it algorithm, is a loop that runs 10 million times and does some logic decisions in there. Nothing real world, of course. This is just to give you an idea of that. Well, we are doing some number crunching here. We are doing some busy work here. And this whole thing is actually executed in what we call in .NET word tasks. Tasks are an abstraction over threads. So this is multi-threading that you see here. You could say we are starting threads. And actually, this many threads, now this many is just a constant, but its value is here, 260. So we are running 200, we are starting 260 threads. Now, since we are using not actually threads directly, but .NET tasks, this means that if you run it on a 2-core CPU, then we won't saturate the CPU. There will be actually a task scheduler, and .NET will make sure that the CPU does only as much as it can actually handle. But still, we will have those 2 cores that I actually have on this FPGA board. Or you have the 64 cores if you have a proper high core count CPU. But still, it's nowhere close to 260. Because when we convert this into a hardware implementation, we can have pretty much a core count of 260 on the FPGA. 260 because this many will fit on this particular, not very big FPGA. And that's where the whole advantages come from. So you can pretty much get a many core processor just for your algorithm. That's optimized just for your algorithm. It executes just your algorithm, nothing else. And because of this, it can be very fast and very power efficient. All right. So what else is there? By the way, the code I've shown you is up on GitHub. Many more benchmarks, many more samples as well. You can also, of course, get the whole thing and play with it yourself. If you have a suitable FPGA board on premises, or if you want to use some cloud resource. But what else is there? What I've shown you here was a small FPGA board for embedded applications. But we also support the Xilinx Mighty's platform. Now, yeah. There's that. Should I stay maybe here? Okay, we have to
in the camera.
Oh yeah, sorry about that. Yeah, we have to tune to the whole. So what we support is a platform called Xilinx Mighty's. And this means that if you have a modern FPGA board of the manufacturer Xilinx, then you can use Hestia with it. This also includes not just such smaller FPGAs for embedded devices, but also cloud FPGAs or data center accelerator cards, as Xilinx puts it. These are very large, even physically and capacity-wise, very expensive and very high performance FPGA boards that you can either purchase or rent by the minute, by the hour from both cloud computing providers, and we support those. We also have made some benchmarks. Again, the details are up on GitHub as well. But on the Algo cards, we get something like 1-2 orders of magnitude both speed and both power consumption. Both speed and both power efficiency increases. Something interesting for the natural sciences and for machine learning workloads are floating point number types, especially in machine learning reduced precision floating point. Now, something worth noting here is the POSIT number format. This, by the way, we learn about from the Wigner guys. POSIT is a floating point number format different from the flows that you use every day in any software, and they promise to be better, with a smaller size than standardized Ripley floats. This is, by the way, an invention by a mathematician called Dr. John Gustafsson, who is working on this, who has been working on this for years in Singapore. And with Heslier, you can already get kind of a POSIT processor, so you can already implement it as a hardware automatically. This is something that we have done. It's also up on GitHub. And if you are looking to accelerate your research or the algorithms in your research, we are also looking for you. So please let me know if you have some thesis work where you are using or where you intend to use heterogeneous compute acceleration. Would you otherwise work on scientific code basis and you want to accelerate it, then please let me know as well. And if you are working on something that goes into space, well, then definitely please let's go in the lunch break. We are looking for such applications in these areas or any areas, but these are that are probably in focus for this event now. So that's what it from me. Thank you, everyone. If you're interested, please check out the project on GitHub, and otherwise, be ready to see FPGAs more and more. Very slowly, they started to permeate cloud computing, but now they are indeed available in every cloud. There are also many scientific data centers having FPGAs. Also, the offerings there are very diverse, so it's very hard to support all of them. But still, FPGAs are available. And get in touch with me if you have any interesting use case. Well, not necessarily for Heslier, but FPGAs in general. I would be glad to hear about that. Thank you very much.
Thank you very much. Questions, Tony?
So we are in a robot development project, and the question is that definitely in the development phase. The question is when it is worth to switch to FPGA, and when it is worth to start working on FPGA, so we don't have a fixed program we have in just developing it.
I think when you are running into power budget issues, so you are developing the onboard software of your robots, and you notice that okay, we want to do more, and then either we can do it first, like with a lower FPS, because you have hardware constraints, or you need to drop features. So your robot can be fully autonomous, for example. So in any case, you are hitting some kind of wall, and then you need to decide whether you use some kind of faster hardware with a bigger battery. If that's an option, then do it by all means, because that's easy. If you can just throw CPU time at the problem and the battery at the problem, you can do that. If that's not an issue, not an option either, because you have a weight or a size constraint or some other constraints, then I would suggest to look into heterogeneous computing approaches. When it comes to embedded systems, there are of course GPUs available as well. I'll do specifically when it comes to aerospace, by the way, FPGAs have a longer history there, but robots, both of them are available. And then experiment around. I would do some kind of proof of concept. If I were you, check out whether it makes sense to put the time into using heterogeneous computing, or you are better off actually just biting to the bullet and getting rid of something in your onboard program to make it fit.
Further questions? Yeah, please.
Thank you for your presentation.
I'm quite interested in the power efficiency you mentioned about the FPGA. And on the theory level, I can understand it, but have you ever quantified it, like rearrange the same task? For example, a matrix multiplication to the GPU and to the FPGA. What is the difference of the power they consumed when you measure this? I know for the FPGA, it's hardware level, algorithm to hardware is quite efficient, but what is the real difference? And that is the first question. Sorry for another one. And you mentioned CPU, GPU, and FPGA, they have their own advantages and disadvantages. So for the heterogeneous computation system, is there any possibility to combine the three together? For example, on your development board, you use an ARM CPU to control or to arrange the task to the FPGA. And in my work, it's a same heterogeneous system, but I use CPU to arrange the kernels or the computation jobs to the GPU. So is there any possible to make some balance between, like there is a system can strike the balance between these three components? Thank you.
Thank you. Let me try to answer both questions. The first, comparisons. We haven't done GPU comparisons with GPUs, only with CPUs. Those benchmarks are up on GitHub, details as well. A few of them in very short terms. I've also put on a previous slide. But there are such benchmarks out there, only not by us. Now, I have to say that all of these comparisons, including ours, are not entirely fair because even comparing CPUs and GPUs is unfair because it's different architecture, but that you get at least you have a flops number for each. With FPGAs, you don't even have that. It's customized architecture. So you need to kind of optimize for something or say that I have a power budget. Now, which device is best in that power budget? Or you have a monetary budget. Have $100, which device will provide what I need? We haven't done these benchmarks, so unfortunately I can't give you a proper answer, but manufacturers did. So for certain workloads, there are comparisons. I think in the end, you have to make some proof of concepts, try it out yourself for your specific implementation. Your second question, can you combine these? Well, in theory, of course, yes. I think the limitation there is what's available for that specific platform that you are using. If you are running something in a data center, then you can combine everything, of course. There are actually also cloud computing resources available that have all three. Well, CPUs are of course always there when it comes to cloud computing, but also virtual machines having both FPGA cards and GPU cards. When it comes to something like this, embedded devices, more you have to make a choice because it's a system on chip usually, or at least a system on a board that you can't really customize. You specifically mentioned matrix multiplications. Well, that's where GPUs are the best. So if you have something like that, you don't need FPGAs. FPGAs are useful if you have a more customized algorithm. If you have bigger pieces of parallelism you want to exploit, so not operational level necessarily, but something I've shown task level, thread level parallelism.
Okay, we have one more question.
Hi, Lenka. First of all, a very nice presentation. I think it's really interesting. So one question is firstly, you have been able to collaborate with organizations. So from here, if you think this could be used in particle physics data processing, if they can do that, and also if you know ESA, the European Space Agency, and they use something like this, or if not, if you would think to find out about it or even collaborate.
Thank you. We'll be glad to collaborate in both of these areas. Gergely was doing thumbs up when it came to particle physics. FPGAs are widely used in particle physics, as far as I know, for all kinds of also online processing and backend processing. Hesper not yet, unfortunately, so we still have to get into Alice again. But we'll be very much open to you to collaborate. And you also asked about ISA. Now ISA is interesting because there's I can't remember the name of the mission, but probably FISAT or something like that. There's the first kind of test bed by ESA for small or nanosatellites with onboard FPGAs, because this device here is actually for nanosatellites, so not the big 100 kilogram and above satellites, but something from CubeSats 1 kilogram up to perhaps the 32 kilogram, still small satellite, but a little bit bigger ones. And we bring it out there, got a few replies, but not much, unfortunately. It's a bit hard, it seems, to get into the aerospace sector, very slow moving sector, it seems. But we will still be very glad to collaborate there.
Okay, thank you very much, Zoltan. So we can have more discussion with you during the lunchtime, I think, and even today. So let's thank Zoltan again. Very definitely, we always have at least one pioneer who is present in real hardware.
With a lot of wires.
Okay, so let me introduce the next speaker, who is Dr. István Szabó from the Eötvös University. And let me give some time to set up the computer and the microphone. Okay, so now we are ready. So the talk is the importance of research infrastructures for Hungary, and maybe some of you know that István was the one who created this framework among the top 50s of kind of other of these things. Sorry, I just tried to move this away.
Okay, yes, thank you for the introduction. And actually, I already told children about this talking to research infrastructure. So this presentation will be much more software, I would say, than the previous one, because I try to put this into perspective, actually, what we are doing in terms of research infrastructures and why are they important. Previously, I've been working at the National Research Development Innovation Office as Vice President for Science and International Affairs, and as such, I've been dealing with research infrastructures quite a lot, and that's why I was asked by Gergely to provide a brief rationale behind basically why the state cares about research infrastructure, and what might be their potential use. And I'm glad that while we tried to debate, but the last part I heard the word collaboration, because this is the very heart what we have been doing as well. This is just a quick glance on what were the programs of the NRDIO. And the logic here is, and this is the key message here, but in the right side you can see the international excellence, which means that for all researcher, we put the goal that they should go international, they should do something which is international visible, and they also should build somehow collaborations. And also on the left side, you can see the research and technological infrastructures, because we believe that you can reach international excellence if your career or your activities are built on research or technological infrastructures, actually, because you will immediately see these can serve as very solid grounds for cooperation, not just between researchers, but between innovators as well. But I don't want to go too much depth into innovation policy. This was the funding scheme of the NRDF fund previously. It's undergoing again sort of public sector innovation, I would say. But nevertheless, the logic was there that somehow you should have a dedicated open access budget and research data management plan, and this is the want to put into the light now. Here, there are quite nice amounts in Hungary and forints. There are quite a lot in euros as well. And among that, we have spent a lot on research infrastructure memberships. So this means that you will see in the later slides that we are members in many research infrastructures. And the question always arises, why do we have to pay for these? What's the point on being members in these infrastructures? So the message here is that you shouldn't take it as given that you are sitting, for instance, now here in this research infrastructure, because this is funded mostly by the state funds. The state always want to see some sort of return on investment, let's say so. But this return can be both from a societal aspect, or for an economic aspect, or actually from a scientific aspect as well. And this is what brings us to the next part, and this is something new and the sort of a researcher hat, what I would like to share with you, that you know the concept of open science, that it's important, it's already spreading, though everybody is still respecting much more a Nature article, which is not very open actually, but it's a Nature article, than being or making an open access publication. And at the same time, we know at the business sector part that there should be some kind of open innovation, which means that you should bring expertise from outside as well. And I think that research infrastructures can serve as an excellent, I would say, playground for these two aspects, innovation and science, for going meet, because they basically can cooperate with each other together, provided there is openness and the science doesn't want to go only for the Nature article, and innovation doesn't want to go only for profit, but they want to do something meaningful together, I would say. And this is something which should or could happen actually here where we are now. And I mentioned you the word cooperation many times, and the collaboration was also mentioned. And the innovation policy in Hungary, for instance, this collaboration somehow happened. You see that here are certain programs which actually answer these needs. You see that the national laboratories, which I will show you immediately, there are the system science parks, the innovation fund, there are sector, but at the same time, and so I think that this is quite a novelist approach, because it's somehow a directed individual research actually, but it shouldn't be a pain for you, because you actually research what you are doing, and it will benefit the company as well. And this is a nice example on how we try to build actually corporations. For the national laboratories, we have built a whole system of this. You can see the map of Hungary. And you see that there are many dedicated programs here in the framework of the national laboratories. The logic of these were that somehow we should build, I would say, lighthouses in Hungary, in certain scientific branches, so that the international partners who wish to cooperate with Hungarian researchers can immediately see who could be their best partners, for instance, in the framework of national reproduction, or in biotechnology, or laser transmutation, so you name it. Basically, these laboratories are not single-sided laboratories, but rather sort of distributed research infrastructures, meaning that you have a single point of contact at these national laboratories, and through that single point of contact, you can have access to all the national laboratory entities which are there in Hungary. And I think that this is quite a good, I would say, value proposition for the international partners. For the research infrastructures, Hungary has quite a long history of it, and now I'm talking about, I would say, the hardcore research infrastructures. For instance, CERN and the European Spallation Source, etc., etc. You will see many of these in the next slides. And back already in 2008, we made a decision that we should align our research infrastructure agenda with that of the European Union, which means that in the European Union, ESFRI, the European Strategic Research Infrastructure Framework, only accepts a research infrastructure as research infrastructure if it is open. So it doesn't mean that it's open from for 1 hour in the whole year, but it should have a direct visualization on how to access that certain infrastructure, how to use that infrastructure, and to make sure that this openness again helps science. And with this logic, we have formed a committee. Actually, you see here in line with the ESFRI thematics, and this committee decides which of Hungary's infrastructures can be considered as the top ones. Back in 2009, we had some 380 research infrastructures which were considered as important ones, but we decided that we somehow again should make sure that those which we select will be again internationally visible, and this means that you shouldn't have too huge numbers actually coming from these. Also at the same time, it's important that the Hungarian infrastructures are considered as sort of partners for the international ones. So this means that for our most important Hungarian research infrastructures, whenever it's possible, there should be some sort of partnership, or there should be some cooperation between major international research infrastructure, and that's why we are working closely again with ESFRI principles. And here you see the ones which we are members in, and you see that it's quite a broad actually scientific branches where we are taking part. You see the usual suspects, I would say, the CERN and the like, but there are other interesting infrastructures, for instance, which I'm not sure that they are well known here, for instance, CLARIN and CESDA. And at the same time, it's very interesting to see, and it might be a question actually for this workshop as well. If you see certain cooperation possibilities with the infrastructure which are heavily actually GPU based in the future, because you see that there are infrastructures which are working with big data in the field of social sciences actually, so they are, I would say, traditionally quite far away from the physics, but there might be again some sort of potential cooperations. I don't know, because I'm not an expert in it. I just wanted to put it in your mind, because I think that nowadays, it's not just my opinion, that science can't work by scientific disciplines, but rather you must build somehow bridges between the certain scientific branches. And you see that we are members in a lot of scientific branches, as I mentioned. Obviously, the ones which are related to physical sciences cost a lot more actually, because you have to pay for the hardware fees, I would say. The ones which are mostly for instance, the social sciences or cultural innovation cost a bit less, but at the same time, again, they need quite a huge actually computation capacity. And for instance, in the framework of ALPHA, our infrastructure membership, which is for a linguistic declaring research infrastructure, now there's a proposal that somehow we should build a Hungarian computation capacity actually to serve Clarin's needs. And again, the question comes whether the capacities which are presented here could be used actually for that purpose. They are working actually in the same framework as these institutes. Both of them are AIKH institutes. And we have selected the top research infrastructures with that in mind. It was again a key aspect that they should make excellent science. And we communicate also with the research infrastructures.hu website. I recommend you to take a look at it. And you see that there is all over Hungary we have some sort of research infrastructures, but also we have to say that many of these are located in Budapest. So Budapest is still the capital of Hungary, and some 70% of R&D is happening here. So this is the situation, but otherwise, as I mentioned, there are excellent infrastructures also, especially obviously in the university cities outside Hungary. And we also have hosted basically one of these top research infrastructures, and I copied this from the website actually of the researchinfrastructures.hu. You see that there is quite a detailed description on the research infrastructures. There are also the national partners who I mentioned, because when we collected these infrastructures, we also tried to encourage them to somehow make networks and build collaborations between each other. So this means that wherever it was possible, we tried to decide, when we had to decide on who will become a national research infrastructure, that if someone built a network already, then it was an obvious benefit instead of that which was a standalone one actually. And I think that this computing laboratories is a very nice example that it's actually happening, and it's likely happening at the other. And this is the still new in the future. Thank you very much.
Programs. So as an experienced researcher, as I may say, that one of the problems is that the system is changing too fast. So in each 3, 4, or whatever years, there is, or even there are no political changes, the system is kind of changing. So do you have ideas or examples how to make it more stable, or what can be the possible solution for this, that not to, so for researchers, not to change always the direction that we are going for excellent science? We need to, that startups, we need to do collaboration with industry and so on. Thank you.
Well, we have a very nice verse for it in Hungarian. Sorry for the foreign partners. Fecseg a felszín, hallgattam én. So it basically means that in the top part of the river, everything is happening and waves are, happening, but deep under, the changes are not happening that much. And I have a good example for that. So we have in Hungary, for instance, the basic research programs, the so-called OTCAP programs. These programs are aiming for the individual researchers, and they are basically blue-sky research topics. And the only selection criteria is excellence, and it's operated by the scientific community. And with this, my answer comes that I think that if we can build up programs where community is behind the certain too many of those, for instance, the new National Excellence Program, the already mentioned cooperative doctoral program, national laboratories, etc. And these are operated by communities of scientists. The strength of the OPCA, however, that it is operated by the huge community of scientists. And if that's a basis, then we should build actually these huge communities. I don't know actually how to do it, to be very honest, because these are already small communities. But if we can get engaged with those who are already there in these communities, then actually we might bring this forward. Honestly, I'm pretty interested to see if this research infrastructure initiative will continue as well, because I'm personally have been really a driver of it, because I wrote a PhD on research infrastructures and there's been a governmental representative on many of those. but this thing again that these are a key point for any innovation system.
Any further questions or remarks? Yeah, I would have one, so we would be very, very happy to host other fields. So, maybe I advertised earlier that we have connection with ornithologists. We had connection with ornithologists. We had connection so we never had connection to the linguistic sciences and the social sciences. So if you can help us to merge together, we will be very happy to share. I think the language what we are trying to use in parallel or massively parallel computing can be a common part.
Okay, I will try to do that, especially because the tradition, at least in Hungary, but to be honest, I'm pretty sure that everyone else in the world, if you have already your equipment, then it's yours, and you can do whatever you want to it, and you are quite reluctant to share it with others, and you rather apply for yourself something than use someone else's equipment. But yeah, we don't have all the money, we don't have all the researchers and everything, so somehow. Okay, so I will.
So maybe you can tell them that this is the agreement, that's yours.
That's yours.
Okay, thank you very much. So the next is András Tercs. András is the head of the Wigner's computational physics department, and I'm giving you this. And then trying to find the oops. So it's me. No, it's not there, but not in the screen. Okay. So the talk will be on this line, new results. I'm sending it.
Hi everyone, I'm András Tercs, head of the Department of Computational Sciences at Wigner Research Center for Physics. And getting closer to the lunchtime, I would like to give you a little appetizer. So the appetizer about what we are doing. So just following the proposal of István, I would like to invite you to collaborate. We are doing some basic research, but on one hand, our food is very much in computation. So we need hardware, we need hardware expertise, software expertise, and firmware expertise. On the other hand, we need data. We need interesting questions, challenges. We have methods to analyze data. And that's the first topic I would like to discuss here. So what are we doing? We are working on a new artificial intelligence paradigm that will be the topic of my colleague's speech later during this workshop, Antal Jakovács. We are analyzing complex systems, complex networks, and the brain itself, brain networks. We have a very strong group which deals with cognitive computational neuroscience. We have a project which deals with data analysis, in particular unique event detection, causality analysis, and there are groups working on theory of computing, quantum computing. Colleague is here, Zoltán Zimborás, and we also have a very special group working on neuro rehabilitation again, which is calling for collaboration. It's already collaborating with the Medical Institute, the Institute of Rehabilitation. So, of course, we are working on massive parallel software and hardware solutions. And well, what I am trying to give you here, just a hint what interesting and novel approaches we have. So first, what, of course, I won't speak about quantum computing, that will be done by my colleagues. I would like to highlight some methodological developments, for instance, the unique event detection, and that can be used, for instance, to recognize financial anomaly detection. And the other is the causality analysis. The case study will be about measurement on plasma in physics, of course, gravitational wave detection, and one very traditional area of our work is a medical area, epilepsy patients' data sets are analyzed by us. Of course, there are many application possibilities, but well, that needs quite a lot of efforts to somehow bring together industry and our theoretical groups. So, for instance, I can imagine that our methods can be applied for root cause analysis in large networks or in large industrial plants where there are many equipments measuring things like similar to the gravitational wave detectors, where thousands of measurement devices are around the core device. So the first one is, how can we find a unicorn? We have a long time series, or not too long time series, and there is somewhere a small particular thing, a unique event inside. There are several methods which try to find those anomalies. The problem is that typically they find those which are by pattern different from the rest of the time series. Our approach is different. It can be quite similar, but the problem is that it is appearing only once or appearing very infrequently. So we developed a kind of measurement, that is the so-called temporal outlier factor, which measures that if some instances of our measurement values in space close to our actual investigation point, is it true that they are also close in time? Could you imagine we have a long trajectory, we pick up one point. If the neighboring point in the space only neighbors in time, means that the system did not return to that point again. If there are very far time points, then it is a reoccurring, not a very unique point. So that's a nice kind of tool to detect the unique event. So colleagues applied it, and colleagues applied it to the gravitational wave detector, and well, it was after the pinpoints of the first case of the gravitational wave successfully detect just the point when this gravitational wave took place. The other application is, I would like to just highlight, is one particular application of a bench of methods we have developed. Actually, we have developed 3 methods to find out causal connection between systems. So simply imagine that we have temperature outside, we have temperature inside, we have temperature in my computer, how they are linked, which causes the other, or is there any connection between them? Of course, I'm speaking about causal connection, not simply correlation. So there should be a kind of information flow from one system to the other. There are many very nice and very well-developed techniques which are able to find out if the outside temperature causes the inside temperature, or vice versa. That's fine. But if there is a third common factor, either one, which we are not able to measure, so we measure outside, inside, but something else modifying both, those methods are not able to identify that. So our methods, 3 methods, are all able to do so. 2 of them is particularly for physicists, for biologists, where we can speak about deterministic dynamic systems. But of course, in real life, in many cases, we have stochastic systems. So we need something which is able to handle a time series in which many random effects. So the third is a Markov model-based system. So the example I would like to show you right now is about investigation of a data set coming from Prague partners of us. They investigate plasma development, and in particular the question which we try to find out, answer was, if we measure somewhere in the plasma with very tricky device the density of the plasma, the local density, can we find out the relationship with this density with the magnetic field strength, which of course influences the global. But locally, there are many other factors, so maybe between them. So we used our method. You can see here some kind rough picture about the equipment. Here you have a small part of the measurement enlarged from the bigger part here. And on the bottom, you can see steps and investigations concluding finally to the last part. Here we are able to provide probability of different causal models. What are those? Simply the magnetic field influences, causes the density change, or the density change refers back and influences to the magnetic field, or there is a hidden third common cause, or they are simply independent. So at least 4 of them we should distinguish. And based on these measurements, we concluded to the fact that the magnetic field, which is the so-called Smirnov coil signal as a proxy for the non-local magnetic field strength, causes the local density of the plasma. So this is quite a challenging task, and I do hope that we shall publish this result in the near future. Let me mention that the method is new, and the observation based on that method also from point of view of plasma physics is new. So that was first part, the appetizer for you, and let me stop for a moment.
Okay, thank you very much. Any question related to the scientific part? I'm getting tired now. Thanks for the question.
I have a question. I more or less know your system with this causality relation, inherence or detection. My question is that how for what system size can this be scaled up? Like I am thinking about, for example, gene regulation network, and there are thousands or tens of thousands of participants. What is the limitations or what? I agree that this is a too hard question, but what is your vision? What are the limitations and what is the way forward?
Thanks for the question. So, to avoid any misunderstanding, first of all, there are 2 major branches of causal inference. One is dealing with events, single events. So you have the node of many items, and the only question is if one item causes the other or vice versa. And the other branch is, of course, even more subtle. If you have time series, several thousand of time series, and you are looking between the causal connection between the systems producing those series. So if I understand you well, your question is belonging to the first one. But well, we are at the very beginning of our research. So the method, the software which we have developed is able at the moment to analyze a pair of systems. Of course, we are thinking about to upscale, and that needs again very massive computing. So that's another task for the future to develop the system which is suitable be implemented in large hardware.
Okay, further remarks or questions? Then we will not thanks to on that at this point, because we are smoothly continue to another interesting topics, which as if you see the program, you see a kind of networking package here. So I would like to ask András to continue with the introduction of scientific computing. So in early this year, that was the very first week of 2023, on that Discovery, I really thought that nobody here in the institute until those days, and he asked me to come over and discuss a little bit about the possibility to having a virtual institute which is related to our community. And now it's about to reform, and András will speak about this a little bit, and then we move to another connection which Daniel Verényi will
also present something which could be a kind of network possibility for users of the GPU laboratory or somebody others from the scientific computing community. So please, András.
Thank you very much, Gertrude. So, well, there were already words about collaboration. I guess that we all work on something very much related to computing, and many of us scientific computing, which is only, well, just a part. And we all face the problem that if we are doing something and we present that, in some cases, the audience claims that, well, that's engineering, it is not science. If we go to some other places, they told us, well, it is IT, why it is not science? Or vice versa, if we go to an IP or technical engineering conference, they thought, oh, where is the engineering problem here? So we have no place, we have no real friendly environment for us. So that's somehow the idea we somehow point and think that we need a kind of society. We need a kind of community which help us to come together, share ideas, collaborate. For instance, several years ago, we already started such an initiative with linguistic people working on computational linguistics. It was not as successful as we hoped, but now we are trying to renew our efforts and try to establish a society for us, for you and for colleagues. So why I am here to speak about that, just calling you, join us. Join us. We try to provide an environment for the people working on such areas. What kind of areas? Many. See, I think that this is actually formalizing discipline. So it is just getting the shape. So data science, data mining, statistics, computational sciences, many, chemistry, economics, mathematics, neuroscience, and so on, physics, of course, sociology, machine learning and artificial intelligence belongs to that. All of those belongs to that, and we all speak one or the other dialect of the same scientific computing. So what's the purpose of the society we plan? First of all, serve as a professional community platform, organizing professional forums similar to this one, so not competing with this one yet, issues. Help to access computing facilities like the Wiener Center or other centers in Hungary, like the HPC computer at Debrecen, providing professional support to use that. And last but not least, help students and early career colleagues which struggle the most with the problem that this is not an accepted discipline at the moment. Okay, so we would like to provide services, computing resources, at least help, support to reach them, to provide a kind of educational center, mentor program, run a job market, and of course, and that will be not very far, to organize a conference. In October, joined to the new workshop, hopefully, end of October, we shall organize the first the scientific computing conference. Well, the core, one of the most important activity I hope we can develop to help junior researchers with advertising, spreading projects, interim projects, research competitions, and provide and advertise theses and diploma teams and PhD teams as well. And maybe later we shall run some advanced computing courses as well. Just formality, but of course the key point is that you all are most welcome. Please find my name at Wigner, send me an email, and we shall send you application form for the society. We do hope that the society will be registered in a few months, and then you can be founding members of the society. Well, I guess that the mission, vision, and values are straightforward. I already mentioned what are the key activities we would like to have, and I guess that we all share the vision that computing and scientific computing will be one of the most important activity which help the society to shape a better future. Of course, we stick to scientific rigor and ethical conduct and support next generation researchers. So those are our basic ideas, and you are most welcome to join us. So please contact me. Thank you.
You have questions? Just make it short because the website.
Will this be an international community?
Well, I guess that we will be very happy if we can establish ourselves as a national organization first, run it for a few years, then and parallelly to build up some international connections, partnerships. So at the moment, that would be too ambitious.
Okay, thank you.
And then yes, from starting, I would like to just ask if you were already talking with other people in other institutes. I presume this is not only that you mean it here in this setting. So is there really a need for this? Do you know that from the universities and other research institutes?
Well, as I mentioned, say 3 or 4 years ago, we already had a kind of similar initiative together with colleagues from computational social sciences, particularly from sociologists and linguistic people. At that time, that was already very clear that there is a need for such an activity and kind of organization. In the last, say, year, I discussed the initiative with many colleagues, and as a result, in late April, we have a kind of informal assembly meeting where, for my biggest surprise, 80 people showed up, and there was quite a strong support for the establishment of such society. So, well, indeed, we contacted people from different universities, institutes as well. We invited colleagues from the Stucky as well to our first meeting.
Okay, so I think we should move on. So let's think on that. And he is here all the time, so you can get the details. I think the critical mass we have. So now we just have to put together the things to make a explosion. Okay, so thank you very much. And now Daniel Merrill will the Hungarian GPU community. Hi everyone, can you hear me? Hopefully, yes, we will put it close to this, so I, is it not on? Now, yes, okay, so it's nice to see many people here again. I hope a few people remember that I have organized this event for like 5 years and do it before together with Mate, who will talk a little bit later. So we've got the question a few times that people were interested in GPU technologies, and they wanted to learn more about GPU technologies, but they didn't know where to start, or unfortunately, still there is a language barrier for Hungarian people to enter into all the English resources and be able to solve problems based on documentation and things like that. So at some point, we decided that there may be some informal setting in contrast to what András talked about. It's a more formal organization. We decided to start a little bit more informal meeting place for GPU interested people or experts. So we launched Discord server. We decided on Discord because it's a technology that many of the young people use for the universities, and hopefully all the other researchers can pick it up. It's something that enables real-time communication, and it's informal and serves our purposes well. And so we launched this. You can join with this QR code. You can find it also at the desk. And we welcome everyone who is somehow trying to learn about GPU technologies, not just talk about them, whether they're interested in graphics, compute, simulations, or AI or machine learning. You're welcome to join. Stick to all the vendors and technologies and platforms, so it's not just like CUDA specific or AMD specific or something like that. We have different experts from different fields, and we have some competence with many of these technologies, so we can help maybe many issues that you might have. And we really welcome students, teachers, researchers, and everyone from all the different levels. We hope that we can help people learn faster, to help them with issues that might be hard to solve without specific assistance, or just talk about all these new trends, new hardware, new technologies, or help with bugs or optimizations, whatever. So please, if you're interested, check it out and spread the news and invite your colleagues or students if you are teaching them. Hopefully we can be helpful in this community. And as just András told, there are multiple initiatives here, but I hope these can work together and we can make each other more efficient, and the outreach would be increased. I'm also here for today, so we can meet up and talk about this, and thanks for your attention.
Thank you very much, Rami. I think we definitely will put this QR code to the GPU Labs web page, so you can also find this, and in the web, we will also put this the GPU web page as well, so you can also find, because we are very proud that Mate and Dani are coming back with a sick from the industry side. Okay, so thank you very much, and now we very important, the key point to get to the lunch as soon as possible. So I asked Balázs Kackovics and Balázs Szigeti to be the first, what is the engine of the train, and the very last people. And please try to be together, and we can move to the small restaurant here. And please come back slightly before 2. Especially the speakers of the next session. So we are starting to start, and since you need assistance to get into the building, please try to be compact together. Okay, thank you very much.
a másik Igen, ez a rész szinte ilyenek alapvetően a virtualizáció egy kicsit nehéz, mert ugye egy fizikai eszközről beszélünk, hogy egy nagyobb lehetőség nem az, hogy nem szarhat.
Akkor mindegy. Mondjad, mi legyen.
Valami ilyesmi, akkor nagyjából ugyanez. Egyébként vannak ilyen érdekes, még nem igazán használható megoldások ennél szofisztikáltabb virtualizációra. Mi arról szól, hogy nem
Beszélgetsz velem.
Annyira nincs ez.
Beszélgetni?
Máté, ez nézd meg, ez dátusz, de ez ad egy ilyen nagy.
De amikor az meg, amit elrakna azt, hogy egy lehetőség és a fordításon színű már. Az képest, tehát a fokira is nem megváltva, és akkor igazából az, hogy FPI az fejlesz, a helyszínen, ahol nem kellett így,
Én vissza kell azt
Csak látod, hogy filmben kell használni ezt valami. Csak egy olyan, aminek a vége volt, de be tudod tudni valamelyik látni. Ez is jó.
De a másik felé mi van?
Jó, ez egy csinál USB-re.
Jó, de még nem. Persze. Én szerintem egy úgy is elérni.
Akkor folytatom majd az elpakolást.
De amit már
Fölényesen szerepel volt menedékességgel. Ja, oké, akkor szükség. Megint.
Igazából erről is reagálsz.
És meg itt tesztet tartsunk, hogy igen, egy öltözte, nem. Nem volt vele pacinka. Everyone, please take your seat. Let's continue with the next section. So our next presenter will be Zoltán Kurowski. He will talk about automatic differentiation of platonic circuits. So I'm giving the microphone to you.
Thank you. Oh, thank you. Do you hear me?
Yeah.
Okay. Hi, I'm Zoltán Kurowski. I'm a PhD student from the Florida University, and I also work at Wiener. And I will talk about automatic differentiation of platonic circuits. Sorry?
How to remove this because
Sorry. Okay. Okay, so I would like to talk about automatic differentiation of photonic circuits using Picasso. Picasso is developed by this group of nice people. These are researchers from Wigner, but also from Ötvös University, also from Ericsson, and from the Polish Academy of Sciences. And the outline of this talk will be about, so this is the outline of the talk. I will talk about the basics of photonic quantum computing. Then I will talk about why should we use photonic circuits as neural networks, and then why to simulate them. And then I will introduce you to the Picasso simulated framework, and I will also at the end present you the TensorFlow integration which we have recently developed. Okay, so first, basics of photonic quantum computing. Photonic quantum computer stores information in independent optical modes called Q modes. What does this mean? So, as you can see, photonic quantum computer consists of quantum light sources. These essentially are the analogs of classical bits of bits in a classical computer. And the optical processing means the analog of logic gates in classical computing. These are also called photonic gates. These are quantum gates. But the difference is that we need to have like single photon detectors because we need to measure our system in order to extract any information from it. So that is the difference between classical and quantum computation, and it is also true for photonic. And why is this interesting? Well, because it has a quantum advantage over classical computation, which has been demonstrated by the quantum information group of the US University in Hefei, China. And so they demonstrated an advantage, and they improved it in 2021 and 2023. And in the latter article, they mentioned Armitov classical benchmark. So that is nice. And here you can see the quantum computer. Essentially, it's not very much accessible. So yeah, it is an laboratory. So how do you model a photonic circuit like this? So as I had said already, that you have an initial state and you have a set of gates, and after the set of gates, you will get a final state, and the gates do some transformation on the initial states, as in classical computation. And states can be written as, this is the difference, as superpositions of these initial or occupation number states. So, for example, this red state, which you can see, this is an occupation number. This is a national number, actually, or represented by national number. And the blue line is the Q mode or mode. And here you can see a very simple, at the bottom of the slide, very simple example state consists of one particle, one photon, and it is on two Q modes, essentially. And how do a gate look like? So here is a simple example of a gate. This is a beam splitter. This is essentially a mirror which partially transmits a photon and reflects a photon. And in this example, you have a single photon on the first mode, and it goes through the beam splitter, and there is a certain probability of transmittance and reflectance of this photon. And here you can see that the output state is essentially this one. This is a superposition of the 1, 0 and 0, 1 states. And you can calculate the probability distribution. It is essentially the absolute value square of the coefficients. So that is easy. It gets harder, actually, for multiple photons. And here I should mention that the probability distribution is continuously dependent on the theta variable. So the theta variable can be tweaked a little bit, and the probability distribution only changed a little. So it's continuous and differentiable. Why is it good for using a neural network? So the idea is that qubit-based quantum computing, in the measurements or the probability distributions corresponding to measurements are discretely dependent on the circuit itself. However, it's like in classical computing. However, in photonic quantum computing, the measurement outputs are continuous, as we have seen, for example, at the beam splitter. There you have the theta angle, and you can differentiate it. So the idea is, in photonic quantum computing, that the photonic circuit can be used as a neural network, and the gate parameters, the theta before, the parameter of the beam splitter, can be used as a weight. And here you can see a simple example of the differentiation of this beam splitter actually. This is the differential is not exactly so it's not a state, but it can be used in expressions corresponding to measurement outcome. So how does our neural network modeling it's not in photonic quantum computing, it's in classical. So it's classical in classical computing, a neural network model looks like this. X is the input, and epsilon is the output here, and L, a single L, is a neural network layer actually, and it consists of a linear transformation composed with a nonlinear activation function. And we have to do very similar in photonic quantum computing. So the photonic analog is very similar because you have an input state, psi, and psi prime will be the output state. And L, so the calligraphic L, will be the continuous variable quantum neural network layers, which I will introduce. And these states will be the set of parameters of the circuit. These will correspond to the gates, but L should be the composition of a linear and nonlinear transformation. What does that mean in photonic quantum computing? It is not entirely trivial, but here I will present to you what corresponds. So here you can see that it consists of two interferometers, line of squeezing gates. This essentially squeezes the quantum state in the phase space, a displacement, and a Kerr gate, which is a nonlinear gate. And we will use these. This is a single continuous variable network layer, and we will use the composition of these. Or these are essentially used. Why do we want to simulate a photonic quantum computer? There are many uses. Photonic quantum computers are still not widely available. You could see the photonic quantum computer which the FAI group used, and it was not very widely available. You could actually purchase smaller quantum computers, but they are still very expensive, and a lot of researchers couldn't use photonic quantum computer. We need to simulate a photonic quantum computer as well, because some researchers try to approximate quantum computing, and this approximation may inspire better classical algorithms. For example, if you can approximate the probability distribution with a very close probability distribution, then it might help in the problem which you would use in our application of a quantum computing. It can also be used to test hardware, and it is beneficial to have multiple simulators for testing hardware, and it aids implementation of quantum circuits. So, for example, I will present you this deep learning and the gate synthesis. However, simulating a photonic quantum circuit is hard, it's classically hard. If it wouldn't be, then we wouldn't do this actually. So example problem. Given a photonic quantum state, how can we prepare it using a photonic quantum computer? We can use CVN layers. We can define a cost function, which consists of psi and psi asterisk. And psi asterisk is produced by the vacuum and a layer and a sequence of CVN layers. And you can actually differentiate this, and you can use backpropagation, and you can essentially minimize the cost function with this. So that's how you will eventually end up with a photonic quantum state which is really close to the desired one. So that is essentially an application. This doesn't use photonic quantum computer, it helps implementation in photonic quantum computers. I should emphasize that. Okay, so now I will talk about the simulator framework which we have developed. We have developed a photonic quantum simulator because there is an existing one, but we weren't really happy with that. It had a lot of issues, so it was better to just develop a new one. We could experiment with it, and we could extend it and improve it by ourselves. We didn't want to improve another one, and it is also beneficial to have multiple simulators for testing hardware. Hardware photonic quantum computer elements, for example, an interferometer, a beam splitter. And the main goal is to make it extensible, to be able to write multiple plugins for it. And we already have a plugin which is called Picasso Boost. It's a C++ plugin for Picasso, which is a high performance plugin. Reproducibility. So the issue with the previous solutions is that the probability distributions were not reproducible. So there wasn't any seed which you can use to redo your calculations. And finally, clean code. Picasso is open source, it's available on PyPy, and you can install it via Git. Okay, so we want to simulate nonlinear gates in Picasso because the CVNN layer consisted of it had a Kerr gate, which is a nonlinear gate. So we have to use the Fock simulator. Fock essentially means that we have the construction which I presented to you before. That is called the Fock space. But the Fock space is where the photonic quantum states live, and we essentially store the coefficients in the Fock basis. And we need to differentiate the Fock simulator essentially, or circuits in the Fock simulator. For example, a Fock state is a coherent state, as you can see in the equation 9. And we essentially store these coefficients. But we would need to store infinitely many of these, but we couldn't do that. So obviously we need to use a truncation, which you can see in the equation below. And this C parameter is the cutoff. We will call it a cutoff. But there are two ways to do that. So the Fock simulation is an approximation, but and one has to make a choice which occupation numbers are stored in the memory. And when you impose, then it will make the Fock space, the vector space of the quantum states, photonic quantum states, finite. And what the competitor did, it's called Kubernetes, the apparently aggregators, is that they use the local cutoff, and this stores the quantum state coefficients by mode. So this imported a cutoff on the Q mode. But what we did in Picasso is that we imposed the global cutoff. And we said that, okay, this is a number, and you shouldn't have any more photons in your system than this number in your whole system. So not on a single mode. And you can see that the C to the power of D is, it's a much larger number generally than the one presented below. But still, cutoff results in photon loss. And we should ask the question, if we throw out contributions from the quantum state, do we lose a lot of photons, or is it still like manageable to work with it? And we compared the two frameworks in terms of photon loss and execution time, and you can see on the blue crosses, this is Picasso, that, for example, given a photon loss, which we allow, the Picasso executes much faster, so like an order of magnitude faster than Strawberry Fields. So this is nice, and it means that this global cutoff is something that is worth implementing. And we wanted to, so the reason I presented the Fox simulator is because we wanted to integrate TensorFlow into this simulator because of the nonlinear gates. And we did it. So now Picasso or the Fox simulator supports TensorFlow. You could essentially use TensorFlow variables in the Picasso simulator. For example, in this example code, you have TensorFlow variables, and you can input it into a Picasso program, and you can essentially execute the Picasso program in a gradient tape, which will provide probabilities which are differentiable, and we can see that we calculated the Jacobian of the probabilities here. So that is nice. And we also benchmark these CVN layers, or exactly one single CVN layer. And here you can see that the Picasso or the calculation time grows exponentially. So, and we also did the calculation with multiple cutoff values. And you can see that we could calculate with 14 modes. So that is a lot. And in Strawberry Fields, we could only have calculated with 9 modes, actually. And it seems to be super exponential after a time. So it kind of hits a wall, actually. And maybe it is attributed to the fact that it also uses a lot of memory at this point. So, yeah. And that was it. Thank you for your attention. Oh, here is the website. It is the website of Picasso.
Thank you for the talk. It's great new to this. Any question?
How rules are that you simulate and train a network in a computer and you build it as an optical computer?
Sorry, so the question was how close?
How close are we to that point that train artificial intelligence is manifested physically as an optical quantum computer?
So sorry, what is the search?
So, when will the first quantum computer, optical quantum computer trained artificial intelligence appears physically? What will it be? How close are we?
I have no idea, so I don't want to give you any opinion on that, actually. We are waiting for that for a while. I don't know when will it be available.
I think the politically correct answer for that is closest to fusion. Anyone else?
Thank you for your presentation. The quantum computation is not my field, but I have a sort of naive question. You mentioned that the quantum computer is not widely available, right? But my question is why it is not? widely available, what is the hardest part for in building a quantum or optical quantum computer? I mean, if we can figure out an easier way to build a quantum computer, the simulation is definitely not necessary, right?
There are many obstructions actually. I'm not an experimentalist, but as far as I'm concerned, it's really hard to produce certain occupation number states. So like producing the input states is fairly difficult, and the detection is also very difficult. It's really hard to detect like if at the end of the computation you have like 5 particles or 6 particles. It's really hard to distinguish apparently, and so there are optical chips. The interferometer is not that difficult. You could fit interferometer in your pocket. It's not difficult. The detection and the quantum light sources are hard, and I think they also need cooling. So yeah.
Okay, thanks.
Anyone else? Then maybe last one from me. I just thinking on whether if you could have a photonic quantum computer now, would it be able to simulate more of its quantum cores than a current computer? Exactly, my question would be, how much more efficient would it be in this need?
So if you had like a photonic quantum computer, how much more efficient will be in
simulating a bigger quantum computer than itself?
I'm not prepared to answer.
Yes,
like a bigger quantum computer than itself.
For example, so now we are using classical computers to simulate quantum computers. The quantum computer would be able to simulate another one, and so a bit more and more efficient. But
so the pattern is very similar to like simulating a classical computer with a classical
it's no like in virtualization.
I've never thought of that, but I have no answer for this.
Then, thank you very much.
Okay.
Speaker list. Is Erzsébet Suhajda. Hurts.
Okay. Can you hear me? Is it okay? Is the microphone okay? I don't know. Is it on? Is it on? Can you hear me now?
Yes.
Okay, great. Thank you. Welcome everyone. My name is Erzsébet Suhajda. I'm a master's student at the Budapest Technical University. However, I conducted my research in Semmelweis University in the research group of Tamás Hegedűs. And today I'm going to talk about the use of AlphaFold neural network in protein structure prediction, and especially in the prediction of CFTR, that is a transmembrane protein involved in a disease called cystic fibrosis. Cystic fibrosis is the most common hereditary genetic disease in Caucasian population. It is caused by the malfunction of an iron transporter in the cell membrane, and it is associated with short life expectancy and frequent medical complications due to the imbalance of salt and water retention in cells. The most common mutation has already an available and approved therapy. However, there are many rare mutations that cause the same disease, and it is virtually impossible to develop an individual therapy for every rare mutation. So in our work, we propose a general molecular approach to cure this disease. And let's take a closer look at CFTR, which is the transmembrane protein that plays a key role in cystic fibrosis. CFTR is a transmembrane protein, meaning that it extends through the cell membrane. We can imagine it as being composed of two halves, so two transmembrane domains that are really similar to each other in structure, and two nucleotide binding domains that has the function of binding to ATP and providing energy for the conformational changes of the protein. So here are the nucleotide binding domains. They are located inside the cell. And we can also find a regulatory or R domain shown here in red, which is an unstructured or intrinsically disordered region. And when the transporter is closed, the R domain is wedged between the nucleotide binding domains, preventing them from dimerizing. Let's take a closer look at the function of CFTR. So as you can see, CFTR transports chloride ions. And in a closed state, as I have mentioned, the red regulatory domain is wedged between the nucleotide binding domains. The nucleotide binding domains bind ATP to provide energy for the conformational changes, and then chloride ions can exit the cell. However, R domain is so in a closed state, R domain is situated between the nucleotide binding domains, and solely the ATP binding is not enough to trigger the conformational changes. The R domain also needs to phosphorylate and change conformation. Thus, the nucleotide binding domains can dimerize and the conformational changes can occur. The focus of our research was the structural space of R domain and the interactions between nucleotide binding domain 1 and R domain. And our ultimate goal would be to find a small protein or peptide that could fixate R domain in this position, therefore hypersensitizing this channel. And if we can fix R domain in this position, then we hypothesize that the binding of ATP would be enough to trigger the conformational changes, and we wouldn't have to wait until the R domain is phosphorylated as well and changes conformation and exits the space between the nucleotide binding domain, because it would be fixated in this position. So how should we do that? R domain is an intrinsically disordered region, therefore it is really hard to visualize it by experimental methods. And the great paradigm of sequence and structure, which is more than 50 years old, is that if we know the amino acid sequence of a protein, we could assume its structure, and from the structure, we could make assumptions to its function. However, this paradigm is more than 50 years old. It has not been until recently that this bioinformatical question seemed to be solved. A few years ago, AlphaFold came out, which is a machine learning and deep learning based method. And it takes an input sequence of amino acids, performs genetic database search and multiple sequence alignments, and also searches structured databases. And basically what it does is it models the structure of the amino acids provided. This neural network was trained on a plethora of protein structures, and therefore it can be considered as a method that has reliability of those that experimental structures has. The output is protein structures and also confidence score, per-residue confidence score, and overall confidence score of the model. And one of the ways that AlphaFold tries to model structures is that it searches for amino acids that during the course of evolution has changed related to each other, and this could infer that these amino acids are close to each other in 3D space. AlphaFold also has a version that is tailored to protein complexes, meaning that more than one amino acid chain or amino acid sequence is present in the structure. The input is an amino acid or various amino acid sequence as well. The output is X times 5 structures, where X is the user-defined value, and AlphaFold Multimar has a modified model confidence score to also include information about the contacting interfaces and about the confidence of the contacting interfaces. It actually has a greater emphasis on the interfaces than on the individual predicted template modeling score. So our objective was to explore the complex structures that could happen between nucleotide binding domain 1 and R domain using R domain capsids and not the whole length in these 4 positions based on previous experimental results. We also had the aim to explore complex structures of human ABC dimers and to collect, categorize, and publish available ABC protein structures as a large superfamily. First, let's talk about the 795 serine. We performed 5 times 5 prediction structures for every peptide that we modeled. Here are every structure built for S795. Most of them are flexible structure with some occasional beta barrels, and the best confidence score was 0.45. The confidence score ranges from 0 to 1, 0 meaning that the model has no confidence, and 1 meaning that it has a full confidence in the model structure. 0.45 is not such a great number. We usually aim to gain information from structures with more than 0.5 confidence score. The other modeled peptide, 737, had 2 binding sites, one here with flexible and unstructured peptides. But the interesting thing was that we had one model with a confidence score higher than 0.5, and it binded to another region. Here are the 2 in one picture, and that peptide that binded to the different region and that had a confidence score higher than 0.5 had alpha helical properties, unlike every other model for this peptide. 768 peptide was really interesting because they had two characteristic binding sites, and more than half of the models had high confidence and alpha helical properties. So these are the two best models of the two binding sites. And there were also some occasional flexible structures present. During our work, we also wanted to explore the more wide superfamily of CFTR, which is called the ABC proteins. ABC translates to ATP binding cassette, meaning that the mechanism of the transporter is based on the energy of ATP. And we performed AlphaFold simulations for every human ABC dimer. And although many of them already has an experimental structure, for example, ABCB6, which is seen here, this is the experimental structure. And in the regions that are circled in red, the experimental information is only available in a rather low quality or low resolution structure file, and therefore performing an AlphaFold prediction could complement this finding. And during our AlphaFold simulation, if you look at these regions, you can see that the confidence score values was rather high, typically higher than 0.7. So we could gain more information than just from the experimental structures alone using this novel method. We have maybe 20 structures of human ABC dimers, and we wanted to make them available to the larger scientific community. So we joined 3D Beacons and we made them available at 3dbeacon.haglab.org. You can browse our structures here, and we included some information about the method we used, about the protein we predicted, and we also included the structure files in various formats. So what is 3D Beacon? 3D Beacon is a network that has the aim to connect individual structure providers with large biological central databases like PDB, Protein Data Bank, or UniProt, and also to standardize the formats in which these protein structures are presented. So users can access a large database, for example, Protein Data Bank or UniProt, search for ABCB6, and they would find our predicted structure as well as the experimental structures and other predicted or experimental structures. They could browse, download, analyze, or visualize these structures all in one place. And during our work, we also became interested in the whole broad ABC protein family, not just only human dimers, but every ABC protein. ABC proteins are really ancient protein families, therefore they are present in almost every organism from bacteria to man. And we did a comprehensive collection of available ABC protein structures, and we categorized them into 9 structural families presented here. This categorization was based on literature data and also our own findings. And you can see that every structural family has 2 templates. They are all named from their most representative member. And the two members are needed because since these are ion channels and transporters, they have 2 conformations, one closed and one open. So we should differentiate between a closed state and an open state. And we also made this comprehensive collection available online at abc3d.hagelab.org. You can browse here, you can select all structures, human structures, only experimental structures, or only computational structures. They are grouped according to these 9 structural families. You can make custom selections, bulk downloads, and really there are multiple ways of browsing this website. And what is really cool is that you can also visualize it on the spot. So if you select one protein, you can just view it in the right side of your screen as it is shown here. So to summarize, AlphaFold greatly covers the structural space of proteins, and it can be a really valuable supplement to experimental protein structure findings. And you can find our results at readybeacon.hagelab.org, where our novel protein structure predictions are available. At abc3d.hagelab.org, you can find our comprehensive collection of ABC protein structures. You could also find our publications of these topics presented here. And thank you for your attention, and thank you to everyone who contributed to my work, with a special mention to Tamás Hegedűs, who is the leader of our research group. And if you have any questions, I will try my best in answering them. Thank you.
For the talk, and is there a question? Thank you very much for this. Do I understand correctly that in the first part that you were talking about the flexible structure?
Yes.
Okay. That this confidence score of what is a good predictor of finding flexible parts of protein. So if I simulate a protein with AlphaFold, then the low confidence parts will be more probably flexible ones, or
yes, actually there are publications that state that a low confidence score is a great way to find an intrinsically disordered and unstructured part of the protein. So yes, this was a correct assumption. But these intrinsically disordered and unstructured parts of a protein are really dynamic in nature. So our overall goal was build models with as high as a confidence as possible to explore this. To explore this structural space that this intrinsically disordered region could populate.
And if I have another question, that have you tried to compare AlphaFold's performance to ESMFold or other tools?
We have not tried to evaluate them, but AlphaFold emerged first at the CASP14, which had the intention of comparing these methods. And also maybe not me, but the research group has a publication about the performance of AlphaFold on transmembrane proteins specifically. So if I remember correctly, AlphaFold is a great tool in terms of transmembrane proteins, which are our research interests. So I think that I would say that it is a better tool than previous tools, but who knows, maybe in some years we will have something even better.
Thank you.
Thank you.
Is there any other question?
Hi, I'm Veronica. First of all, very interesting presentation. It's very interesting what you're doing. And I have two questions. The first one, you mentioned that you use data from some public data sets. Do you know how comprehensive or up to date they are? and also where the data is coming from, like how much it's contained from cases and everything. And then the second one is looking everything to the future. If you already talked about collaborating with some for medicine, for example, you talk about these findings that you would do so that you would have a look at the treatments. I guess it's very fine in the future, but you thought about that.
Okay, thank you for the questions. As for the first one, AlphaFold is a pre-trained neural network, so we haven't performed the training part of the work. It is actually open source. You can find it on GitHub. It is the work of a company called DeepMind. And if I remember correctly, they trained their neural network on every protein structure available in Protein Data Bank that was deposited before 2018, 30th of April. Maybe in the later releases, they also included newer data. But the first version of AlphaFold 2 was trained on every protein structure deposited before the 30th of April of 2018. And as for the second part of the question, well, we are located in the Medical University of Budapest, basically in Semmelweis University. We are in the Department of Biophysics and Radiation Biology. We usually attend conferences related to ABC proteins and biophysics. So yeah, I think that we are quite interlaced with the medical science community as well. So, and then hopefully in the future, yeah, it will be, yeah, so yeah, that's yeah. Thank you. Thank you.
I absolutely don't know what is the cost of such computation. So can you give a context of if I want to predict the structure of one of your proteins to show if how much time would it take on one GPU or is a big cluster of GPUs for multiple days or how expensive it is?
It depends on a lot of things. It depends on, but basically it depends on your input, which is the amino acid sequence. So it also depends on the length of this amino acid sequence, but also the conservation of the amino acid sequence or the protein. The conservation means how many similar proteins can the algorithm find in their databases. And the more hits it gets, the more RAM is needed, basically. The first part of the computation is more CPU heavy, and the second part with the model building is more GPU heavy. And really, it depends on computational resources, how much time it takes. I think for us it was maybe one day, half a day, but it's really hard to say because for example, for multiple sequence alignments, which is like the first step of the prediction, you could only perform it once and then reuse it. So once the MSA is computed, you don't need to compute it again for the same amino acid sequence. So we usually try to save time by reusing these MSAs. For example, in the NBD1 structure complexes, we only had to compute the MSA of NBD1 one time because it was the same and only the peptides, the red ones, varied. So yeah.
Thank you.
You're welcome.
So thank you for the questions. Now we have to move on to the next talk for this author.
Nem a meg a működésünk, de ez nem PDF, az PPT, nem? Na, PDF. Akkor tudod, ide megy fel. Ja, nem, most megint ez a baj.
Okay, so good afternoon. My name is Gizzo, and I will present some latest results in collaboration with my colleagues who are present here, István Pap and Sheng Feng Deng. They are working with us in the complex system department and the Center of Energy Research, or AK, or MFA, whatever you like. And our fourth colleague, Jeffrey Kelling, is in Germany, and he is responsible for developing the GPU code, high performance GPU code, what we have been using. Okay, so as you can see from the title, I will speak about synchronization modeling to say model brain systems, and there is a hypothesis, which I cannot go into very much in detail in brain science, that the brain usually is caused a kind of critical point. So how can it happen in collaboration, I mean, in combination with synchronization and oscillations? And I have already investigated it for some time. But now we will go further and ask whether some kind of force, which is a periodic force, how does this synchronization, transition, and criticality affect? So to describe our system, we will use the so-called Shinamoto-Kuramoto oscillator model, which is a couple of differential equations. So for each site node, you have a theta and angle variable, and they are interacting with the difference, sign of the difference in the interaction term with the nodes, and there is a coupling W describing the structure and the global coupling as well to just to control the system somehow. And every node has a so-called self-frequencies with omega is 0, which is a quenched variable at the beginning. And we have, this would be the simple Kuramoto, which I've already presented in the previous year maybe. And here you have this additional term, the fourth term, where you have a sine theta. So it's an external force, and you can also investigate Gaussian noise, the effect of Gaussian noise, but it will turn out to not to play too much role if the force is not strong, because already the forceless deterministic equations are very chaotic, and due to this chaoticity, randomness is quite randomness generated. Okay. So, some words about networks we studied, large human connectome graphs, which are obtained by MRI images with 1 millimeter cube voxel resolutions. And these are hierarchical modular graphs. containing about 10 to the 5 to 10 to the 6 modes, and these are following the green regions where you have this atlas of 7 top levels, and the lower levels are obtained by tractography. This was not done by us, was published a long time ago in the Human Connectome or Open Connectome projects. The point is that after this image reconstruction, you can generate a kind of undirected and weighted graphs, which we will use. And these have a topological graph dimension less than 4. This means that we have a 3-dimensional base system, but due to the long links, the dimensional will be slightly higher, but it's still less than 4 according to our measurements. And we have studied it long before in this scientific reports paper. As for comparison, we also studied the fruit fly connectome, which is an exact. Here the nodes corresponds to real neurons, and this was the largest non-exact neural networks. It has about 21,000 nodes, about 3 million edges, but it turns out that the dimension is larger than the previously mentioned human connectome. Of course, this is smaller. And if we plot, for example, here the weight distribution, so it's a weightage graph now. The weights, the distribution of the weights and the log plot is this heavy tail, which can also be fitted some power also. Somehow it's not a random graph, although here you can see the adjacency matrix structure. It is very small. Some structure can be found, but a very, very weak one. And on top of it, you have this weight distribution. And it's a bit modular. The Q coefficient describing it is much smaller than in the case of the human connectome, where you have this 0.9 modularity constant. And somehow to model the dynamics and inhibitions on the structure, we apply this weight normalization, which means that these W's, the incoming weights, are divided by the sum of them, and somehow it makes equilibrization of the cells. Okay, so we performed numerical integration on these graphs, and we measured the synchronization quantities. So you have the theta. These are the into the theta functions, and you can sum up. You can get the global order parameter R or the absolute value, because this is a complex variable. This is one of our main order parameters. This is the so-called Coulomb order parameter. The other quantity we measured was the frequency spread. So the second moment of the frequencies. And we also studied the local synchronization methods, which are defined very similarly as the global ones. The difference is here you don't perform the sums for all nodes, but only for the neighbors of a given set. So these will be not dependent. And furthermore, to analyze the time series we obtained, we did some first and beta exponent analysis of the local order parameters. And in case of long-range correlations, they follow some kind of power law behavior, where h is the first exponent and we have the beta for the frequency. Okay, so we did a numerical differential solution with the adaptive Ehrlich-Stuart stepler, which was implemented to use GPUs. And just a few words about the GPUs. So it is written, the code is written in C++ with using some vector libraries. It was written in CUDA, but can also be recompiled for OpenCL or OpenMP. And we use this Boost libraries as well. And different solvers are implemented. Yeah, what's up?
Yeah, I thought that we would.
Yeah, random generators and ADIOS with input outputs, high performance input output of the results. And here is some performance benchmark. The first part is for power grid. My colleague Christoph or students from BMA will speak about a little bit later on. So here, if you saw the Kuromoto, similar Kuromoto, not exactly this one, you can see the comparison with the Xeon CPUs with respect to the GPUs, different P100, 100. The speed up is just about a factor of 10. About in case of the fruit fly, so also similar, and in the human connector, which is much larger, then you can exploit the parallelism of the large system. You can see 2 orders of magnitudes speed up, and it's in the random case it is worse, but it's still almost 2 order of magnitude speed up. Okay, some latest benchmark results for our Kifu colleagues who asked is that we compared the simulations on the development with the Leo machines, which is the K40 GPUs, and new Commodore machine, which A100 GPUs. And we found a speed up of 3 in case of the fruit fly, and speed up of 6 in case of the human connector. Oh, so let's speak about the result. If you run this numerical solver, if you start the system from asynchronous disorder state, you can follow the R, the order parameter, how it grows for given different couplings, K couplings, global couplings. And you see they initially grow and then they saturate to some steady state values. If we plot the steady state values as the function of the force, you see that the force induces a synchronization transition. Okay, so this is the kind of interesting thing. And the blue symbols shows how the frequency spread decays. So as the synchronization gets stronger, the frequency spread will be bigger. And this is the chart for the fruit fly. And if you are also plot the variance fluctuation of these quantities as the function of f, you can see peaks like in phase transitions, but these are not really phase transitions because in Kuromoto system you can expect it only very high dimensions. So okay, variance is possible because the dimension is high, but in the human connector is not so much. Anyway, you can see different peaks for the frequency and the phase order parameter, and very similar results could be obtained for the human connector. I don't go into the details. Okay, what else we measured? We measured how the durations of the synchronization, and this figure shows the global order parameter start from a single realization, single self-frequency realization. These are different self-frequency realizations, okay, many of them. But if you follow one and you apply a threshold, you can test whether the system is synchronized or not synchronized, and you can measure the times in between the 2 crosses. And if you histogram the crossing times, the synchronization times, and you plot it on the histogram, you can see this kind of power law tails for different force values. And the fluctuation peaks, I don't go into details now anymore, it's also interesting. And this is also true for the human connector. And so this was for the fruit fly, and this is for the human collector. Okay. What else we done? As I said, we measured the local order parameter. So here you can see in case of the fruit fly, the local order parameters encoded in these colors. The green is the most synchronized locally, red is the less synchronized. So for example, without force, this is the initial short time scale. You see this lower synchronization value, but after some time, it will synchronize, but not fully synchronize. Some domain structure, some so-called some kind of rustic synchronization will occur. And for different force values, you can do the same thing. If the force is very large, you see the system is much more synchronized than it can system. And we can do this local analysis in a different way. You can determine the communities by modularity optimizations, community optimizations, and this plot shows this Hurst and beta exponents for different communities. So you can see variations of the exponent values for different communities. And the main point was here that we could reproduce this Hurst exponent around 8, which was measured by fMRI experiment very recently by some Polish group. I will show you later. So these are for the fruit fly, and these are for the human connectomy. Human connectomy have much more communities, of course. Okay. So, right. Here is the fMRI experiments by this Polish group. The beta and the Hurst exponent measure the different brain regions and different status. Okay. So, just to conclude, periodic external force induces synchronization transition parameter type models, which we applied for fruit fly and human connector maps. The local synchronization analysis reveals this chimeral states, or this first city synchronization. I didn't explain the chimeras, but it is related to this first city synchronization. First and beta exponents in communities show quasi-criticality in agreement with the fMRI experiments. Force enhances long-range correlations, so it's stronger in the task phase. The task phase means that when you have external force with respect to rest phase where you don't have external drive. And I would like to thank your attention, and if you are interested in the results, we have this publication which appeared in Frontiers of Physics just in this year, and then earlier with Gustavo Deco, scientists, research, and this was about the forceless case results. So again, thank you for your attention.
Thank you for the talk. Is there any question?
So human brains, actually some human brains have some function, not just that function that the basis of this model. So can you infer something on the function of the brain, or how different brain structures may higher or the functioning or something like that? General picture, I guess.
By functioning, what kind of functioning? Yeah, it's functioning. It's I mean, we compare the task phase when you have an external stimulus and the resting phase, but you mean?
Yeah, but the external stimulus was just a force.
Yeah.
And not so. I mean that say that you try to do a similar experiment using instead of brains that you want network, or you want just to do on a random network of resonators or something like that. So can you differentiate between a system that have some kind of I will not define higher order function, but some kind of functioning rather than just a classical statistical physics system?
Oh, we are not doing this. Yeah, I mean, we just wanted to investigate this criticality, you know, all of these things about to see how close we are, the critical behavior, and what about the dependence of the heterogeneity of the modules. But I mean, if you, I'm not a neuroscientist, you know, and if you want to ask if this model can simulate one kind of neural pattern by functioning in, you have this, the tool, and then you can try to do it, but it was not our purpose at that moment.
Does anyone else have a question?
You have mentioned the other definition of Polish population and what how many people. Have you performed similar research on people from different countries as well?
The experimental results were done by this Polish group, which we haven't been in contact yet. Actually, we'll meet next week in a conference. We just found a paper and we compared our results with that.
Okay.
Different what?
Imaging methods could be online. Different methods could be online. And this merge together also take a higher level paper from CMT computation, the activity that they measure FMRI. And they merge those data with EEG, and they build out some model and then about synaptogenesis, how synapses are firing up with those kinds of stuff.
I don't understand the question, but what comparison? I mean,
so you know, could you recommend any kind of paper where different neuroimaging methods could be combined, and how this could be combined?
Yeah, there are different methods. For example, very similar method was used by a Spanish group. They also investigated Shimomoto Kuramoto without quenched disorder. But you know, this is what we have added. A big extra is this the self-references, which is fixed at the beginning, for example. And of course, you can study it not by this Kuramoto type of models, but other synchronization models. But the more, the closer your model is to the reality, the more difficult to solve, and the more we have lots of parameters. So, but it is our target or aim to extend the Kuramoto, and then Jeffrey has a promise that in future Yaplife will be a fund as well to make, how to say, involved in the solver other synchronization models. Okay, does it answer your question?
So, again, let's move to the next presenter. So our next presenter is István Regui. So he will talk about whether that's an experience from Lumi running CFD's workloads. From Plasma Catholic Universe.
Right, hey everyone. So I'm here to talk about Europe's latest and biggest supercomputing gadget, Lumi. It was, I think, first appeared on Top 500 last November. It is now the biggest supercomputer in Europe, about 375 petaflops, if I remember correctly. And importantly, this one is built on AMD GPUs, sort of a little sister of the US's Frontier supercomputer, which is now 1.5 exaflops or so. So I was basically curious to see what sort of performance one can get out of these cards, how well it works. Sorry. All right. How it works, how well you can program it, how easy it is to use, etc. So in terms of raw specs, these cards are a little bit similar to the K80s of ancient times, where you have two chips integrated onto one card. And so one chip it actually appears as one logical GPU. It has 64 gigs of stacked memory, can do about 26 double precision teraflops, has 1.6 terabytes per second of memory bandwidth, and about 110 compute units. So if any of you keep track of GPU specs, half of this GPU is roughly similar to one of NVIDIA's 800 cards, so similar bandwidth. This one has a lot more double precision compute, but otherwise it's pretty similar. So Lumi is built out of these. There are 4 cards in one node, which means 8 GPUs. And actually the network cards interconnecting nodes, there is 4 of them, and they are sitting next to the GPUs themselves, suggesting that you really should be doing direct GPU to GPU communications. And there is just one CPU socket in each node, and there is 2,500 of these, giving you this roughly 370 petaflops of peak performance. Right, so how do we program these? Some of you may argue this, I'm sure, but programmability has been a bit of a challenge for AMD. I mean, they were very quick on adopting OpenCL, but then OpenCL never really gained enough traction in the HPC space. So NVIDIA had a bit of a head start in that regard. So what they did recently, well, 5 or 6 years ago, is introduce HIP, which is more or less just the trivial clone of CUDA. And the express goal of that was to really enable existing CUDA codes to use AMD GPUs with as little effort as possible, and they have all sorts of scripts and machinery to automate this transition. So basically almost all except the latest greatest CUDA features are supported in HIP. Of course, libraries are still a little bit of an issue. Again, NVIDIA has quite a bit of head start on this, but AMD has been working hard to deliver these dense linear algebra, sparse linear algebra, FFTs, neural networks, and so on, and make these available. So that's for folks who just want to migrate from CUDA. Of course, lots of people from the get-go wanted to get an architecture agnostic programming approach. So OpenMP offload has been around for a while, and this is supported on AMD cards by the Cray compilers, which are very good, except they are only available on Cray supercomputers, so not accessible to most people. And AMD also have a fork of LLVM, which they call AOM, which implements the OpenMP offload functionality, which they call AOMP. And then sort of as an unofficial approach to programming these GPUs, there is SYCL, which is really being pushed by Intel to program heterogeneous architectures. It started out as a C++3 layer on top of OpenCL, but it has really become its own thing. And Intel themselves, I think, actually paid for CodePlay to extend the DB++ compiler to be able to target NVIDIA GPUs as well as AMD GPUs. So once we really get our hands on Intel's GPUs, this is going to be a programming language, or rather a compiler, a single compiler, which can target 3 kinds of GPUs. And there is also the HIPSYCL, which is now known as OpenSYCL, which will soon be renamed because of legal issues. But anyway, a compiler developed by a group in Dresden. Nice. Heidelberg, thank you. Which is actually another very interesting approach to implementing the SYCL standard and convert or generating code that executes. Now that's all C++. If you are unfortunate enough to have to deal with Fortran code like I have to, your options are much more limited because HIP doesn't really support Fortran. It has some bindings for the API calls, but you can't actually write kernel code in Fortran. So your only real option is OpenMP offload. And again, Cray's compilers work reasonably well, but the AOMP compiler, so AMD's own implementation, is based on Flang, and if any of you have tried Flang recently, it's not mature yet, to say the least. All right, so these are the tools we can use to program AMD GPUs. And in my research, we are working on domain-specific languages that let people, physicists, engineers express CFD algorithms reasonably easily without going into details of how data gets moved around and how parallelism is orchestrated. So the idea here is that one writes an application using the OPS or OP2 APIs. One is for structured meshes, the other one is for unstructured meshes. Then there is a source-to-source translation layer, which spits out basically a boilerplate code, which is going to take the computational part of what the user described they want to do and generate all the necessary boilerplate to run this on any given specific target hardware, as well as some slightly modified version of the code that the user wrote. So this code then can be compiled with your traditional compilers, distributed by the vendors themselves, and linked against libraries implemented by OPS and OP2. So you get an executable that can run on a particular platform, and optionally this can use parallel I/O to read and write files and ultimately run on the target hardware. So I looked at a bunch of CFD applications. The first bunch is structured mesh codes, which use OPS underneath, and then OPS in turn generates MPI, MPI OpenMP, SYCL, CUDA, HIP, all these sorts of different implementations. And there are a few interesting either real production applications or proxy applications. Cloverleaf is representative of national security, nuclear security codes. So, explosions. There is a 2D and a 3D version of this. These are not toy codes. These are complicated codes implementing complicated physics. They are not quite as complicated as the real thing, which would be millions of lines of code, but it is a few thousand lines of code intended to be representative of the real thing. Then there is a direct numerical solver for the Navier-Stokes equations called OpenSBLI. It focuses on how shocks are created and travel, usually around aircraft. And we also looked at an acoustic wave equation solver, where the interesting thing is it's a high order method, it's 8th order finite differences, which also means that MPI halo exchanges are going to be expensive. So these are the structured mesh codes. We also looked at unstructured mesh codes, specifically a code called MGCFD, which is an Euler equation solver, which then uses multigrid to better converge to a solution. And this is supposed to be representative of turbo machinery simulations done by Rolls-Royce. So here we again have two test cases, a fairly standard test case, the NASA Rotor 37, and we also have a fairly large mesh from the German aerospace company, which is about over half a billion cells. So unstructured meshes, the key thing to mention here is that the common computational pattern that occurs is, say you are computing something on edges and incrementing values on nodes. And then, of course, if you execute two edges at the same time, which touch, then you have a potential race conflict. So you have to do something to avoid getting the incorrect results. And one of the trivial things to do would be coloring. So you just color your edges, so no two edges of the same color share a node, and then execute edges of the same color. This will avoid these race conditions, also, although at the cost of having horrendous memory locality, because by definition, you're not sharing any data. So an improvement on that is a hierarchical coloring approach, where first you break your mesh into blocks, which are sort of compact, and there is reasonable data reuse inside of them. You color them, and then you do a second level of coloring for the edges within the block. And then what you can do is, for example, assign one of these blocks to a CUDA thread block. They can share data amongst themselves and then collaboratively use, for example, thread synchronization to avoid race conditions relying on coloring. All right, so these are the key applications. So what does performance look like? Well, here is a whole lot of numbers. This is a clustered column chart. So the clusters are the different applications. These are all structured mesh applications. You shouldn't really compare the different applications together in terms of how fast they run, because that's not really meaningful. And down at the bottom, there is a little extra row of numbers with runtimes from an A100 GPU. So basically what we see here is the native HIP implementation is almost always the best. Not terribly surprising. Then the second and third columns, orange and gray, are OpenMP offload, either by Cray or AOMP. Cray, when it works, it didn't on Cloverleaf 3D. It performs quite well. AOMP doesn't perform that well. Then we have the DPC++ compiler, as well as the OpenSickle compiler. And for each, we have two variants. And let me just take a quick detour. Show of hands, how many have used Sickle before? All right, not that many. Well, the concept, although or still is easy. You have a parallel computation you want to express. Say you have 1,000 iterations you need to do in parallel. So one way of doing that in Sickle is to just say, I want to have 10,000 iterations to do it in parallel. This is what we call flat expression of the loop. And the other alternative is more in spirit of CUDA and OpenCL and all these languages. The ND range version, where you specify a workgroup size. So you basically specify a chunking of your iteration range, which ultimately will be mapped to hardware. I mean, of course, the first version, when you map it to a GPU, still has to execute in the way the second version does, but what exact workgroup sizes it should choose will be decided by the runtime, as opposed to you, the programmer, which, well, has its pros and cons. For this particular set of applications, we saw that the ND range version, where I did actually fine-tune the block size, did almost always perform best. But for most applications, actually, the flat version was running reasonably well. Okay, so how much performance did we get out of these hardware in the sort of absolute sense? So here we have the 3 latest GPUs with their maximum bandwidth achieved using standard stream benchmarks. You can see that the MI250X, again, just a half of it, has roughly the same bandwidth as an NVIDIA A100 GPU. And then we also looked at the NVIDIA H100 GPU, which has about 1.5x the performance of the other 2 in terms of maximum bandwidth. Why maximum bandwidth? Well, these applications are primarily limited by bandwidth, and if not, then it's latency, but it's definitely not compute. So the simplest or structurally simplest application is Cloverleaf 2D. You can see that we are getting a reasonable fraction of peak, but as we move to more complicated 3D applications, or more computationally expensive 3D applications like the acoustic wave solver or OpenSBLI, the fraction of peak achieved drops significantly. Sort of importantly, the utilization achieved by the AMD cards is a whole lot worse than by the NVIDIA cards, despite having roughly the same peak performance in terms of bandwidth. Even so, it's up there. It's achieving quite reasonable performance, and then the H100, roughly speaking, delivers the 1.5x performance improvement. Except for one very interesting jump is on the acoustic wave solver, where it's 2.5 times faster. The H100, again, probably better out of order execution and scheduling, and I don't know, maybe more registers. I'm not sure if it has more registers per thread. No. Okay. Anyway, it's quick. In terms of the unstructured mesh application, again, the fastest implementation uses atomics, and we have the version with HIP, the version with DPC++, OpenSQL, and then the 2 OpenMP versions. Now, what you have to note here is that AMD GPUs have slow but safe atomics and fast but unsafe atomics. And for this application, unsafe atomics are perfectly fine. They give you the right results, but they aren't easily accessible by the programming approach that you use. So sometimes you just can't access them with the language of your choice. In comparison, the global coloring scheme is a whole lot worse, and the hierarchical coloring is slightly better, but I mean, still the best versions, there is a 2x difference there. It just comes down to memory reuse. Again, here it's interesting, though, that the MI250 and the A100 are roughly running at the same speed. So the performance between these 2 applications, these 2 cards is actually fairly small. Okay, so finally, because we are in a supercomputer, we wanted to see how applications scale. So we did strong scaling and big scaling. For strong scaling, we packed as much data as possible into a single GPU, so to close to 64 gigs, and then just use that same mesh size and scaled it up to as many GPUs as we could. And then big scaling, we used the same sizes as in the previous benchmarks and just kept the same problem size per GPU constant as we increase the number of GPUs. And then we tested, how much quicker it is if we enable GPU direct communication instead of going down to the CPU. And we also have an algorithmic optimization where we exchange fewer but bigger messages and also do some redundant computations. So in terms of Cloverleaf 2D, you can see that strong scaling goes quite well. Up to 32 GPUs, we have an efficiency of 85%, which drops to 56 at 128 GPUs. But for the weak scaling, it's really very good. I mean, there is an obvious jump going from 1 GPU to 2 GPUs, just because there is communication now, which didn't happen before. But compared to that, we get 96% efficiency going from 2 GPUs to 8,000 GPUs. So in terms of how well the system is put together, the networking, the communication stack, it's actually quite impressive. For the 3D application, all the strong scaling numbers are a little bit worse because there is a lot more communication happening because now you're in 3D and it's talking about faces. But still, it's reasonable. And again, for weak scaling, we are getting 90% efficiency up to 8,000 GPUs. And similarly, for the OpenSBLI code, we see similar numbers. Actually, here the strong scaling is even better than for the 2D case. And one of the interesting points here that at the point of 8,000 GPUs, we had 1.1 trillion grid points in the simulation, which is quite a nice size. Finally, the unstructured mesh case, again, very reasonable scaling. The smallest we could do here was 16 GPUs, scaling all the way up to 512, you get 55% strong scaling efficiency. Right, so in conclusion, we looked at all these different programming approaches for AMD GPUs, and we extended our libraries to handle these. We saw that native HIP implementation was still performing the best, but the SYCL implementations were actually quite close, despite SYCL not being an officially supported programming language on AMD or Intel for that matter. So in that sense, I think SYCL is now very interesting for performance portability because you can actually take these codes and run it on GPUs of 3 different vendors and it will work reasonably well. And it's arguably much more productive to use than OpenCL was. And in terms of the supercomputer itself, we saw that it's really well architected, scalability is excellent. I mean, for GPU supercomputers to have this kind of strong scaling, I'm not sure I've seen this on NVIDIA supercomputers before. And just a quick call to action. Lumi is, for all intents and purposes, almost empty at this point. When I launched the 8,000 GPU runs, they started in like 15 seconds. So, go and apply for access and run your science on Lumi. They'll be the happiest to have somebody running codes on their machine. And with that, thank you. And if there are any questions, then we go.
So thank you for the nice talk. Is there any question? Yeah.
Yes, for this last point, maybe it would be interesting for what you think earlier that the application process for framework of Lumi, what is required and how it will go down in general.
Right, so for the application process, it's the standard PRAISE or Euro HPC system. So for large science projects, you have to submit an application, and I think there are about 3 or 4 deadlines every year. It's I don't know, a couple of dozen pages. You basically have to say why this is important and all that. And if they do approve it, you get access for free, so you don't have to pay for it. What I did was submit a benchmark access application, which is evaluated in, I don't know, a week, very, very quickly. And they gave me, I think by accident, 1.2 million GPU hours, which I don't know, I used 10,000 of them at most. But yeah, so you shouldn't expect this many. Those are primarily intended for making sure your large science code can run efficiently. And then when you want to actually run science, you should submit a proper proposal.
Thank you. I was mildly surprised by the numbers that you showed. So our experience with optimizing for HIP and the MI200s is that the 250X can typically reach A100 performance, not the Hopper 100, but the A100 performance is within reach for most applications. The two biggest places when it cannot reach is when the difference due to warp size 64 versus 32 in NVIDIA. So when there's that kind of thread divergence that it's really hard to unify 64 threads in a warp and have them all be active. So when that is really hard to achieve, then yes, that starts to hurt. And the other is when there are a lot of small kernel launches. So that is the other thing which the HIP runtime still struggles with, like the overhead of launching a kernel is a lot more than NVIDIA. And when the code cannot be made to work around this issue and there have to be a lot of atomic small kernel launches, then, but these are the two places which hurt, and if it cannot be solved, then it's going to hurt. But in all other cases, it can reach and surpass a 100 in most cases. So that's why I was surprised that there was only perhaps one workload where it was.
So yeah, that's a good point. And I think it speaks volumes about the maturity of the software stack that when Lumi got a software upgrade in March, there was sort of an instant performance bump of 15-ish%. And that's still only ROCm 5.2, I think, and we're at 5.4, so it's behind. Well, okay, 5.5. So something I definitely observed is register pressure. The AMD the compilers produced implementations which use significantly more registers than the equivalent CUDA versions. And when I went and forcibly tweaked, so basically max thread count on NVIDIA, the equivalent on AMD, it did help a lot more than it did on NVIDIA. But for these numbers, I did no such fiddling. So I did play with optimizing the block size, but not the register counts. So I have a few data points which say that this certainly helps, but I don't consistently optimize that. Thank you.
Thank you for the really detailed comparison. And I would like to ask a technical question. At one point, you talked about atomic operations, fast and unsafe, safe, and so what do they mean? Because on CPU, I'm familiar with atomic operations that are safe and always performed in one cycle, one after the other. Thanks.
Oh, that's a tough question. I think there are some more computer science people who can give a better answer to this, but it has to do with some memory consistency guarantees. And at that point, they lost me because I don't know enough about that. But the point is, in some cases, it may not come out with the right answer. But you know, these are some very edge cases.
Thank you.
Anyone who knows about this a little more maybe can comment. Memory consistency.
Okay, I'm not entirely sure, but if you open up the C++ specification, there is a longer entry on the sequential consistency and similar I memorize that there are 3 or 4 points about different consistency requirements, and there. So if you want to know, you should go to the cppreference.com.
Which is what I never did.
There are the 2 versions that you're mentioning are at very different levels of this consistency that is different there, but yeah, I cannot guess anything more closely. Which one would be?
I'm sure it's documented somewhere.
All right, then let's continue on the coffee break. So.
This is note for the last round, please, and those for comes for one event.
Szerintem, hogy volt le, hogy is sajátot, hogyha.
Jó, van,
Research and classification. Kész, szemben nincs kész. Ezen volna, nem tudom, hogy feltöltsem, vagy ott megszem a szekció.
Nem szervezünk Gergelyékre.
Ja, igen. Tisztán papírnak, jó is, de jó persze, jó. Összetudunk, hogy van HDMI-t zoomodva, és mindjárt számít kb. De jól tudom ilyenkor. Ugye maga a közvetítés, de erre van gépen. Zoom, csak a megképedő alatt jobb nem veszik.
Az lesz. Megkezdtünk?
Együtt csak a végéből is van.
Igen, az, ami rám.
Húzzuk a mutogatót. Hiszek a Windowsban, képes bármit is elbaszni.
És hogy van nekem egy videóm is, amit be van téve mellé, az valószínűleg PDF-ből nem fog így elindulni, de ha van esetleg egy valami videó lejátszó, vagy tudunk játszani a dél.
Alapot is felajánlani. De a VLC-en itt van, hogy azt mondjuk, azt mondom. Megkes vagyok. Megvan. Még műszik.
Windows 12-ig támogatják.
Tényleg, vagy csak poén? Poén, jó. Elfogadom. Vajon én mutam meg kell? Igen. Igen, már elkezdtem. Volt nyomottam.
De én nincs. Nem én vagyok.
Pap István, igen, a...
Ja, István.
Jó, akkor minden mixik nálad, a tesz kopi. Működött végül a kétfoglyos érintés. Annyira hozzá vagyok működve, hogy ezek a dolgok jól működnek, meg kell, hogy teljesen szokat, amikor Windows-os laptopot kapok. Nem az a miért
Nem? A Session 4 lesz.
Azt most csináltam.
Jó, akkor menj vissza és húzd újra az oldalt. Kristóf Benedeket másodszor.
Igen.
Már egy film, hol van?
Én majd betöltöttem magának a OneDrive-ját, és akkor
akkor megint ez a
Everybody take your seat. Let us continue with the fourth session of this day. First speaker will be István Papi from Ismer Institute. And he will talk about this monoplasmonic fusion. Okay. Yeah. So I'm giving the word to István.
Thank you, and thank you for having me. So I will talk on update functionality models of resonant antennas towards laser-induced fusion. This is a national laboratory which started with a few people only in 2019, but we evolved, and this is a larger group based not only with theoretical but nanotechnology group, a laser group, and a spectroscopy group. The nanotechnology group is fabricating the targets. The laser group, of course, shots it in different settings, and the spectroscopy group will analyze the clusters or Raman spectroscopy. Basically, the idea is to help out laser fusion technology. So the thermonuclear fusion, as one knows, is usually has for energy production. We have criterion, which is called the Lawson criterion, which basically means that we need to have the matter confined for a specific time with a specific density. And for fulfilling the Lawson criteria, this also automatically implies that we have two approaches. One is magnetically confined, which increases the confinement time, and the inertial confinement fusion, which creates a high density plasmas. And also some news that there are Livermore emission facility not long ago achieved higher 3.11 megajoule or something kinetic energy from 2 megajoule inserted. And also some news from the boron fusion. It actually this fuel is not the deuterium tritium like we are used to, but this is a radiation of the fusion. They also in a stellar configuration. They also recently achieved, and every news you would like to know, there is Sabine Hossenfelder. She's quite good at compacting news. So basically, our aim is to increase the increase the likelihood of laser-induced fusion. We are working with lasers, and we chose the direct drive configuration. We understand why. So the indirect drive is basically we have a whole ROM, and the target pellet is inside the whole ROM. This was the 2014 setup, and it was also the most successful until 2020. And here we see that they have not changed, literally not even the angles. However, they changed the laser, the whole raw material, and they changed the ablator thickness, which then led to this achievement. One very common problem, not just in laser fusion, but in magnetic confinement also, are the Rayleigh-Taylor instabilities, which occur on different density, on the border of different density fluids. And just coming from the coffee break, I put this illustration. And here, just to understand how does it work in the national unit simplicity, they managed to remedy this. Basically, our idea is can be traced back to relativistic heavy collisions. When we solved the Rankine-Hugoniot equations in the shock frame, Abraham Taub was first to solve, but he overlooked one thing. He overlooked that there is a solution where we have a time-like hypersurface also. And this means you can have a smooth change from space-like to time-like detonation, meaning that the material does not, at these hypersurfaces, there is actually not a causality relation, but a phase transition. And in the we can do this because the shock front, the shock front is not moving with the material in that sense, the instability. In the National Ignition Facility experiment, in this at constant absorptivity, they can achieve only 12% with this simultaneous volume ignition. However, when we change the absorptivity, simultaneous volume ignition occurs up to 73% of the target. We came up with a so-called flat target design, where we shoot from two sides cylindrical target. Here we can see that at constant absorptivity, the radiation penetrates only 40% or even less. However, with varying absorptivity, the energy deposition can be increased further into the target. Similar configuration was already successful. Aldo Bonacera's group, they also had this type of two-sided shooting, when they managed to have a higher compression at low energy than at the National Ignition Facility. We chose for manipulating the absorption of the target, nano antennas, which are randomly placed in the target. So far, we use UDMA Tegma target, which is used for tooth implants. But this experiment is a proof of concept, so we chose everything that could we have. And these nano antennas are resonant at 800 nanometer wavelength. Simulating these nanorods usually require finite element methods, where the electric constant is the calculated quantity, and unfortunately in these solvers they are neglecting particle movements. They usually or typically correct it with extra parameters. And this is where my part comes with particle in cell simulations, where basically I use also a finite element method. However, I use marker particles or super particles, which move. So I update the fields on the cells. However, the particles can move freely inside the simulation box. For this, we use the Epoch particle cell code, which was also developed, unfortunately, in Fortran. But this is widely used in laser researches, even at LE Alps. Basically, we update the fields at every half step and calculate the movement of the particles, and the resulting with the resulting current we update for the full time scale. We update the relativistic relativistic equation of motion under the Lorentz force, and the Epoch uses this Wilson-Gunnemann current deposition scheme. The most important trick is that we do not use the number of particles as they appear, the same number of particles in real life, as we would have no computation possibility. We instead use a particle shape function, which allows us to have a wider marker particle which interacts with neighboring cells. And the whole nanorod, we consider the whole nanorod as plasma, actually, because we consider conduction band electrons as they behave as strongly coupled plasma. And we calculated the effective wavelength of another nanorod according to this empirical formula. And in vacuum, it results that the nanorod with the size of the nanorod, which which resonates at 800 nanometers, is the length of the nanorod is 130 nanometers. Basically, these work as Yagi antennas. And the electrons we consider the simulation box with 530 nanometer square and nearly the complete wavelength. And as we can see, the number density of the electrons are moving outside of the nanorods. That is because the particle in cell method does not lack what the other type of method have. We can also consider and have in the calculation the spilled out electrons. So we used as the center of the nanorods, we used gold ions, and we took into account 3 electrons as the conduction band, and we can see how this behaves in vacuum. And we tested the effective wavelength in resonance and out of resonance, and this was in line with COMSOL simulation, which is the finite element method. We also tested this in UDMA Tecmaco polymer. In the simulation, we tricked everything by calculating the refraction index of our Runa Tecmaco polymer, which is 1.53, and we can see that in vacuum we have a higher electron spill out effect, as in UDMA, which is the black line. We have nearly 1 order of magnitude less electrons spilled out. That is due to the fact that the nanorods that are resonant inside the UDMA are not 130 nanometers, but less, and less energy is deposited. And here we see that the conducting electrons achieve also above nearly 200 keVs, but also as we study the distribution, we see that in time our laser comes in at 10 femtosecond and leaves at 100, and just like on this figure, the black line shows the laser without nanorod when we don't have anything in the medium. So and we can notice that the electrons also are spilled out. In the experiment, of course, it is very difficult to implant these nanorods. There is a capping which acts as a glue called dodecantiol, and we studied the layer of the dodecantiol around the nanorod is around 1-2 nanometers. Of course, our resolution we have to work on that, but we noticed that the protons surrounding the nanorod will actually synchronize to the conducting electrons. These are the protons which are very much in the vicinity. And these are preliminary results. As we can see on a lower intensity, the whole hydrogen, we put it also in a hydrogen whole target, which was ionizable. And it's noticeable that after ionization, this is the proton line, the average energy of the protons. They are kicked out at ionization. However, when the nanoplasmonic effect kicks in, they are accelerated a little further. This effect at a very high intensity, the plasmonic effect is shorter, so the antenna effect, and this is not very much visible. We can see here at this is at lower intensity and at higher intensity. And lower intensity, the conduction electrons are staying inside the nanorod. However, at the high intensity, they are getting kicked out. However, we reach a very high enhancement in the field. Here we see the protons, protons and electrons, and also the hydrogen atoms, which of course will not move. They will evaporate because they, after ionization, we leave the hydrogen atom and move forward with a proton and an electron, which is different from, of course, the conducting electrons. And this blue line is the conducting electrons, and here I think maybe not very visible from the back row. The protons which are close to the surface of the nanorod, maybe here is better at higher intensity, more visible. They are following the conduction electrons with a phase difference. So in conclusion, the model is a good agreement with the finite element methods, the CONSOL, which is widely accepted. Quantitatively, there are some differences because of the resonant lengths and due to the fact that we have electron losses actually. The model is less idealized now than before, as in previous GPU conferences. Now we have ionized raw material, and now only one step further is to include the nuclear reactions. And thank you for your attention. I hope I
Thank you very much. Questions?
If you try simulation with different materials, nanorods, for example, iron or maybe something like that.
We tried with the finite element methods, but the literature suggests that the gold is the best for this. So the plasmonic effect is related to the negative diffraction index of the metal, and the gold has best for this, also from electron density point of view, and yeah, basically that. A better would be a sphere filled with silver, a gold sphere filled with silver. That would be the best. but that is very hard to fabricate.
Any other question? Maybe one from me. What kind of code do you use to simulate this?
There is the Epoch code is a Fortran code. We actually started the GPU version of it, but then later I realized that they are giving away 10 million pounds in the Warwick University, the original developers who are doing it also. So we went on with this Fortran code because it is well optimized and it has good results for not having numerical artifacts in it.
Thank you for your talk, and we're moving on to our next speaker. So, our next speaker is Vilko Benedek, and he will talk about the generality of the European grids. So, giving the mic.
Welcome, everybody. So my name is Christoph Benedek, and I want to talk to you about power grids and heterogeneity in power grids. Just a small motivation maybe before I begin the talk itself. Why it's important? So one simple answer to that question is the increasing energy prices, the energy topic, and quickly developing network science as well. But returning to the developing power grid networks, whenever we want to develop it furthermore, for example, with renewable energy sources, then we want to attach to the already existing network, then it's crucial how to do it efficiently, how to preserve the stability of the network, or well, even improve it, right? So I quickly would like to present the group members, so of course me, and the group leaders, Gabriel Odor and Bálint Farkman. We have on team also István Pak, Shengpeng Deng, and Jeffrey Kelly. So maybe let's just skip this slide. Let me give you some more motivation. Why is it important to talk and think about the stability of networks? And let me recall that it was 2003 North American blackout when the whole eastern coast and Boston practically went black, right? So here's a little movie which I don't think works, but yes, it doesn't. But I will just go and show you the movie from here. So basically, what we will see here is just the time of the frequency in the network, in the US network, and we can see that the nominal frequency is 50 Hz, and it drops. Dropping in frequency means that we have a load, an extra load in the network. And basically what happened, either a crucial link or nodes just failed to function. And we see that later on in the frequency, we have this oscillation, interferences if you wish. And these are further other failures in the network. And where does this lead? Well, actually it will lead to the collapse of the whole system. And here in this slide, we see the frequencies corresponding to the different regions, and we can already see the instabilities in the network. And it will be more spectacular when we reach this point. Yes, and here we will practically see that the whole network goes back in just a couple of seconds. Let me just fast forward it because nothing really interesting happening there. So, yes. And the thing what happened here, besides the whole eastern coast going black, yes, here, okay? So the thing that happened here besides the whole eastern coast going back is that nobody did anything. So practically that was the reason. The transmission operators should have shut down the critical points of the network, and then they maybe could have remedied or reduced the damage. And today we have this transmission system operator because you can see that and you can think that naively that a power grid system is interconnected and it's more or less homogeneously interconnected. But that's not quite true because we can identify different power regions in the power grid. It can be well divided or separated from each other. And within these regions, there exists crucial links which assures energy transmission from one region to the other. And since we can't really store electric energy, the stability and this design to be secure is crucial. And well, similarly in the US, these power regions exist. So what we wanted to do is just to take these real networks and study their stability, their behavior, the cascades in them that may occur if we run simulation on this network, on this graph. And later, we firstly only took real networks in that sense. We considered the connections between the nodes, but we wanted to go a step forward, and then we wanted to make the system more physical, in the meaning to give them parameters, weights that has real physical meaning and being calculated with respect to real physical parameters. And then identify these real points, nodes, crucial links, and find possible ways to improve the network based on a couple of considerations, maybe graph theoretical engineering, and of course, to not just talk in the air, we have to cross-check these results. And we have the possibility because we have the complete data for Hungary, and results could be checked. But problems arose pretty quickly because power grid related data is kind of sensitive information, and we have two ways to go. Basically, we either use the official data set, it is really cumbersome to acquire, or we use open source data, which is usually incomplete. So we went for the latter option, use open source data, and then we had to come up with some considerations, assumptions, how to complete this data, and that was practically one of my job. So just for comparison, here you see the US network and the European high voltage power grid, and I should mention that this is the giant component of the network, so the biggest connected component. And here you can see that these are not the political parties, but the links for which we don't have data actually in the database. And it's not that visible here in the European one, but there are factors there. So here are some characteristic information about the two networks. The giant component, of course, the node and the link number. And what can we do with such a network? Well, analyze with means of graph theory. So, for example, calculate the clustering coefficient of it, and maybe compare the adjacency matrix. There's some basic things to do when you get a graph handled on a plate. So we did that, and we checked the clustering coefficient for both networks, and they are pretty similar and not much larger than for a random graph with the same parameters. We also compared calculating the adjacency matrix for the two power grids, and what is surprisingly for me, it's surprising because I thought the US will be a much modular structure, but it's not really. They are kind of similar. So let's go on to the simulation part, because I'm giving this talk at the GPU Day conference, right? So simulation, it's all right to talk about it. So the underlying theory is the already mentioned these Coulomb-Model oscillators, and namely the string equation, which is a very well-known model to describe electrical systems and high voltage generators and things like that. Because what they do is the nodes of the networks are imagined to be these oscillators, which are interacting by this sinusoidal curve, and then this becomes a coupled differential equation, right? There we have here the thetas as the phases, the omegas are the frequencies. The omega I0 is the ith oscillator natural frequency. This alpha parameter is the feedback, a negative feedback. K is the coupling, which is practically a constant for the whole network, and it can be understood as the somehow the total power flowing through the network. And then we have here this matrix, Aij matrix, which in the first case, in our first study, it's the same with the adjacency matrix, which considers the connections between the different nodes. But later on, this was substituted by the so-called strength matrix, where we can incorporate the importance of different links, namely the weights I was mentioned. And yes, I won't waste too much time here because these were already presented. Some usual synchronization measures like the global order parameter or the frequency spread, and we can also define the local variance of this, which Jeta already showed you. And one important thing to mention is this line cut threshold, because we want to simulate somehow cascade failures in the network, and we have to have a parameter which tells us when to cut the line. And whenever the phase difference will be too big between two neighboring interacting oscillators, we will practically cut the line, and this is expressed by this threshold. So, okay, we have kind of 13,000 or something network with that many nodes. And why use GPUs? So it's been already mentioned that GPUs is massively parallelized calculation and efficiency, and it's quick and it's good and it's yes. But how good it is? Well, just for fun, I got a temporal network for one of my assignments, and it had only 9,000 nodes, and I tried to allocate a matrix for it, the adjacency matrix, and well, my Python was that kind to inform me he didn't manage to allocate 90 gigabytes of data for that. So sorry. So this is why we should implement on GPUs and massively parallelize, vectorize the network. And we did that. Basically Jeffrey Kelly did that. And we ran the simulations on K40 Tesla GPU cores on Leo and Commodore supercomputers. And the implementation is written in C++ with CUDA libraries like Vexia and OpenCL with this Oberint package support as well. And well, for me, one of the most important things is the integration method, which is now we currently using this Fourier-Stoller method. So our first result was when we only consider the network with the connection, so no weights in the network. And we discovered that the cascade failure somehow exhibit a universal behavior, and their tails is just a power law behavior. And this is expressed somehow in this figure. And also very interesting phenomenon arose in this network as well, mainly these bonds. The red line, if you follow, these are the so-called gigantic cascade failures, which are well known in the literature. It was interesting to observe them here as well in the European literature. Maybe as far as I know, they are more characteristic for the American one. And if we check for different couplings, the frequency spread in the network, then we see a kind of a phase transition, but this is not a real phase transition. Maybe it's more correct if I say a transition from an ordered state to a more ordered state in the system. So yes, these are kind of our first results, maybe the outline of them. And then we wanted to weigh the network, make it more physical to see which are the most important connections. But as I mentioned, there were over 5,000 links with missing parameters. So what can we do? Do data science, right? And engineers involved, we discussed with our colleague, Balint Portman, who is an electrical engineer, and we cooked up some method how to approximate this data and divide the whole network into different voltage levels, take characteristic parameters for that voltage level, and then we can just find the parameters that we need. And these parameters are basically the power, characterizing the power flow, the power flow level that characterizes the line, and the impedance of the line. And with these two parameters, we could weigh the whole network, and this somehow give an importance of the line, because if the power level is higher, then it's more important, right? And the bigger the impedance, no, the smaller the impedance, the bigger the weight. So also the more optimal one. And then we run the simulations, and again, what we did to identify weak spots, weak nodes of the network, crucial links of the network, and communities of the networks. Because we kind of try to reproduce the power region map of the network I showed you in one of the first slides. And we managed that. Here you can see the biggest 30 communities in Europe, which more or less correspond to those power regions I showed you from a completely different source. And what we could do is just to identify the so-called bridges. These are the important links that connect these communities. And then, okay, we have our community, we have the important links. How can we improve the network? Well, double the bridges. Simple assumption, right? So, for example, this is a valid strategy. Of course, there are more sophisticated ones, but the more simplistic one, let's go try. And whether the networks, the stability in the network will improve or not. But before talking about that, let's take another way as well and construct bypasses. If anybody is familiar with basic graph theory, then constructing triangles in a graph is beneficial because it makes the graph more robust. It constructs just different roads to grow from node I to node J. So what we did is to identify the weak nodes of the network and check their neighborhoods. If there is any weak neighbor, then double the link between the two weak neighbors. And if there is no weak neighbor, then take the two closest neighbor, that is good, and construct a triangle with these 3 points. And then this again, these bypasses somehow, we expected that they will improve the stability of the network. And here you can see with orange lines the bypass routes we constructed in the European power grid. One thing to mention is this is the dynamic stabilization, because how we detect and classify the nodes which are weak or strong is based on this local order parameter, Gromov order parameter, which is the dynamic result of the simulation. And what we found, well, surprises, the bypasses and the bridges, they represent an improvement in the global order parameter compared to the simple weighted network. And as well, if we check the frequency spread, well, we don't really see improvement, but it's neither worse, which is good, because we don't want the frequency to widen, the frequency spread to increase, because we've seen what happens if there is oscillations spreading frequency. Blackout. So, yes. And practically, this is the point where we are now. And what we have to do is, again, to check for these power load distributions in the cascades, in the weighted network as well. Maybe if there is any dinky dragon failures in the network, we can come up with other bypass patterns and try out how, to what extent it improves the network. And one really interesting thing is just to consider interactive networks, where we don't consider pair interactions, but we construct a simplex around the neighboring oscillators, and then we can consider a more sophisticated interaction somehow between the oscillators. And yes, maybe those are the tasks for me and for the group in this project. And in summary, well, what we did is just we invested some real-world networks. We observed some power laws, which are telling us about universal behavior in these networks, at least regarding the cascade failures. We did some data analysis, and we came up with a method how to augment complete incomplete data sets regarding the power reads. And we come up also with some strategies how to improve the stability and the synchronization level in the network. And yes, stability synchronization improved, Smiley. And thank you for your attention.
Thanks for that talk. Any questions?
I will talk about obtaining official plans for expanding network and comparing that with your suggestion for regional part of it.
Yes, basically one of the official sources is the ENSOE dataset, which is the all European high voltage dataset, but it's really cumbersome to get. There's a lot of bureaucratic progress, and our colleague Balint Hartman was trying to obtain it like for months, and we get promises to get it, but for now we don't have the official data set. Actually, I just mentioned here that we have a new data set for 2022, and that is official one, and we can compare the values from there. So yes, it's on the menu.
But I don't mean the current data set, but the official plans.
Or the official plans to improve the network. I see. Well, yes, also for that, we have the plans for the Hungarian networks, also from Balint Hartman, but I think we don't have it for the European grid, the whole European grid. We don't have yet. Yes?
I see. Just Balint gave the link for the official plans for actual for the next 5 or 10 years. So indeed, we can do it.
Okay, then we do. Then we do have it. Yes, yes.
Thank you for the talk. I have a question. I was always curious how you take this speed of propagation of the signals, so the speed of electricity into account in the equations. Because let's say that if we have a 3,000 kilometers wide range, then even for the light with 300,000 kilometers per second, we have like one over 100 of a second, which is compared to the frequency of the network. So how does it impact the oscillations that propagate back and forth between, let's say, the north and the east coast of America?
Yes. So basically, what one can do is to put here another term that is a delay term. Basically, in the interaction, you can do that. But what we do is just to have this feedback.
this alpha feedback, the value of this alpha parameter, feedback parameter, gives you the somehow characterizes the time scale on which the network responses to a line failure, for example. So that's how we approached the problem.
And how do you solve the triangular, how can you solve the triangular inequality? So if you have a triangle in the network, but the time of propagation through the two edges is longer than on a single edge.
I feel very.
Those are the questions I couldn't find any.
Yes,
written evidence, and I take the opportunity to ask that to these simulations.
Wow, actually, I don't consider myself that expert, but I will try my best to answer your question. So basically, what you consider is that if the route doesn't exist between A and B, but exist the route ACB, then it will go ACB. It just doesn't think about it. This is a simple-minded approach somehow, but it works to some extent, right? It's an approximation. I don't think it satisfies you, right? But this is the answer I can give you.
Thank you.
Next question. So this is a hot topic, I guess, going on for decades of how to design the electricity system robust.
Yes.
And there are always rumors that if there is a big enough solar flare, it could induce such significant currents either in the system itself or the regulation systems themselves that it would be collapse. So the question is, we have these robustness studies. Do you see any actual manifestation of building these links that would cause the system to be more stable, or is it just appears on paper by researchers and not made up to
Let me respond to this question with a quote from Michio Kaku. Time travel is solved only an engineering problem. So kind of thing goes here. It can be done. The robustness can be improved. It all depends on the communication between nations, because you can see that some lines are crossing borders and things like that. So yes, we can suggest things like in COVID, scientists did do suggestions. It will be implemented or not, that's another topic.
Thank you.
We are moving to our next speaker, which is Urs Legedla. Nem, Zoom-on osztjuk.
Hagyjátok, jó, és amit fogunk, majd elmondom, hogy mit javítottam majd. Jó?
Oké.
Yeah,
A mikrofon mindenki lesz.
Ez még neki. Itt van.
So let us continue with Negetla from Wigner. So he will talk about massive tensor flow application.
Okay, so thank you very much for the opportunity to be here. And in this talk, I would like to just give you some review about some recent stuff that we have been working on. And I will talk about a couple of things which is maybe not very common and some special terms. Therefore, I would spend a little time at the beginning to define just just to give some definition about those which are related to this work. And also, I will not go into the mathematical or technical details, but I'll just show a couple of slides. And so what the kind of algorithms that we work are equally applicable in not just in condensed matter physics, but in nuclear shell physics, also in quantum chemistry, and in basically in all different fields which are related to simulation of quantum systems. So just a few words about motivation, then about what is this mathematical algorithm, then all these novel solutions that we have been working on, which made us possible to get the kind of results which I will show you, and some benchmark results, something about power consumptions, and also how to make extensions later on towards exascale application. So we all know that in quantum systems, there are a lot of exotic materials because the electrons in the system correlate, and then just because of the electron correlation, the materials will have different properties. So that what we have in room temperature, if you cool down some materials, then at some point it will have some kind of superconducting phase, which of course is not apparent in the room temperature, has very special properties. These are some of these materials. And of course, there are nowadays, we can also have the magnets, which are called molecular magnets, where single molecules can have some kind of these magnetic properties. What we also work very hard on nowadays is this so-called nitrogen fixation, which means that in nature, there is this extremely complicated structure, which is called this PEMOCO, this iron molybdenum cofactor, which helps to convert from atmospheric N2 to ammonia, which is just basically one of the most important things for our life. You know, that this is just a guarantee that we can really have the living creatures in Earth. And only one of these ligands which makes it possible to capture N2 and just convert it to ammonia. So it's like a miracle. And so that these are this computer simulation, which I will show also for some of these systems, and of course in battery technology and so on. So the aim is that what we do in classical physics, like developing buildings and cars and or some kind of ships and so on, that we run simulations, and then at the end we select those which are the best because we know the classical physics and we know all the equations, so that we can do some kind of simulations. And this is exactly what we want to do also in quantum physics. The other possibility is that we can have some lasers and put some atoms and pull it down so that the atoms will be localized at these minima of the laser beam, and then they form a kind of lattice, so that the electrons can hop between these lattice sites. And there is also some kind of mathematical formula which just describes how electrons hop from one to the other. And when two electrons are in the same place, there is some extra energy or cost that they pay. So there's a kind of correlation again that how electrons can move and what kind of properties they will arise. The question is that how to do this simulation, these classical computers that we have, or in quantum computers. And of course, we know that in the past year that there is this tremendous evolution in high-performance computing, as well as development of numerical algorithms. So we can do this simulation in physics, chemistry, biology, economy, and so on. But when we apply this to quantum systems, there's a problem which is called the cost of dimensionality. And that means that the computational effort scales exponentially. So as we increase the size of the system, there's an exponential growth. And of course, this doesn't fit into the computers, only for limited system size. And there is no universal fix for this problem. And so this kind of interplay between quantum and classical simulation is one of the key features that is a part of this so-called tensor network state networks that on HPC infrastructures. So without going into details, I have shown this lattice where you have this kind of sites or atoms where electrons can jump back and forth, so that for each of these sites, we just describe this as a basis, so that the site can be empty, there is no electron, or an electron with a down spin or an up spin, or with an up-down spin. So the dimension here is 4, because there are 4 states. And the number of these legs, which means in this quantum many-body wave function, you have as many legs in this so-called tensor as many of these sides or orbitals you have, and then the full dimension scales as 4 to the n, where n is just basically the number of these legs. So you can see that this exponential scaling, this n to the d, is basically the major problem. So how to solve this? There are these new mathematical algorithms when we write these tensors in product of matrices, and then I will really not go into the mathematical details, but just by cartoon, this tensor, which was this big tensor and had these legs, now we can write it down as a product of matrices or for the product of other tensors and split up into smaller components. And basically that's the part of this algorithm, that how to factorize such a complicated tensor in terms of these matrices. And then there is some way that we can control the dimensions which are labeled by m here. If you keep it below some threshold value, then we can have the same problem, but in polynomial cost. So this exponential scaling is reduced to polynomial cost, but still very expensive. Even we have some possibility to make simulation. And also, of course, this is also looks nasty, but this is just in quantum chemistry. We write down the electrons that they go from one side to the other. This is what is called the kinetic energy. And then there are two electrons that they interact with each other. This is written with these complicated terms. And just for those who are working in this field, this is the most general form up to two-body interaction. So this can be used in quantum chemistry, condensed matter physics, nuclear physics, and optics, and so on, and also in quantum information theory and many others. Okay, so this is what we are working on, and what keep it in mind, there is a scaling in this algorithm, which is MQ, which basically the dimension of these matrices. So I said that there was this exponential scaling. This is reduced to MQ, so it's a polynomial, but there is still an exponent which is 3. Okay, so it's still expensive. Now, what happens is that this kind of algebra that we have, this can be split up into millions of independent tasks, which means matrix and tensor operations. And if you make some kind of scheduling and pre-calculation of what would be the task so that you describe the full algebra that you have to carry out as independent tasks, then you can form some kind of model where there are some threads which generate the task, and there are some threads which consume the task and produce some results on the given task. For example, matrix multiplication or tensor contractions and all these things. Now, usually these tasks are different in size. So there are some heavy, which takes a lot of time. There are simple ones, and of course, usually there is some kind of sophisticated algorithm to make a kind of scheduling that how to schedule the different parts that which task to give to one thread, which task to give to the other thread, or if you have like a CPU or if you have a GPU, what to keep on the CPU level, what to keep in the GPU level. But usually you don't know a prior that how to distribute these tasks. So you can use machine learning to do some kind of rules and update it, you know, based on some experience on some simulations. But it's extremely difficult to make it general. So what we did is that we developed a new method where we have this complicated structure. I will not go too much into details, but the idea is that there is a bed where there are some threads put in the jobs, and then there are some others which just take the jobs and then, you know, just get the result. But the thread at the beginning doesn't know that what kind of job he will get. So we have something that the thread has also a possibility that it is going to look for the job. If it finds the job, it will execute it, it will produce it. So it's the idle time is basically reduced. And with this, that the tasks are really formed by this kind of producer-consumer model with this modification. We can really make sure that we can get a very big improvements that how many threads and how to feed the task feasible into this scheduling algorithms without making any prior algorithms to really to make the scheduling hard according to the problem. So this is a fully general method. So that the idea is that there are these workers, they are looking for jobs. If they found it, they do it, and then they go for the next one. So there is this kind of life cycle. The other big problem when you go for GPU is that these problems that we solve, because of this exponential polynomial scaling, usually you need a couple of terabytes of RAM, but the GPU cards are limited to maybe 40 gigabytes. So you have to transfer the data between the GPU and between the CPU or the RAM and between the VRAM. And if you just do this copy paste backend for the data, then of course it takes a lot of overhead. So we worked out also a kind of new method that how to form data so that those which happens in the algorithms are formed in a tree-like structure. And then those, if you go down in layers, then you put this A into the pool, then you put AD into the pool, then you put ABD into the pool, then you go up step back here, there is ABDE and so on, so you can follow this. That means
that it's like in a videotape. You have something, you revise it back, you put some data, go back and forth, back and forth, back and forth until everything is done. So there is no allocation and reallocation in this way, only the pointer structure that must be changed. And therefore, finally, it's a gap-free, there's a sequential write-read operation, there is no allocations, and that's basically help us to hide the I/O overhead behind the CPU and then the GPU calculation. The other thing is when you work in matrix and tensor algebra, there is always a question that how you represent your matrix in row-wise, column-wise, what kind of manipulations you do. And I don't go into the details, but here we managed to come up with some nice solution that how sequence of matrix operations together with some summations can be just turned into a single batch type operation, this batch jump, where just a single run and single call can carry out several hundreds of these matrix multiplications in a single run and then do the summations immediately if you just properly order the data structures according to rows and columns and multiplications with this. Okay, so let's keep it in mind that, as I said, this scales exponentially, which is now reduced to polynomial form. That's basically the mathematical part. There are these millions of several independent tasks that we have. These are done independently of each other. And in these algorithms, the size of these matrices, which basically related to the problem is capital D, determines the accuracy. And of course, also the computational demands. It scales as D to the Q. And then the memory requirement is D to the N square N square, where N is this number of sites or the number of modes, so how big your lab is, how many sites or these orbitals you have. And in these algorithms, usually the time that we spend is the so-called diagonalization of this complicated matrix and tensor algebra. And there is another part where you form some so-called renormalization, and you make a transformation of the states. That's another 10%. So these two basically counts almost 95% of the total execution time. Okay, and so without going into more details, I would like to show you the results so that at least to show you that how far things can be pushed. And this is just a performance measured in teraflops on a single CPU with 48 cores for different system sizes. So for example, 18 electrons were correlated on 18 orbitals. So there are these 18 sites and there are 18 electrons, and we want to solve this problem. This is the limit of the present day supercomputers that have to perform exact diagonalization. So to this exact diagonalization, you can go up to 1818, and that's basically you cannot go further on because of the exponential scaling. Okay, if we just use this MKL self-validation from MKL, like 1OP, then this is the performance that you can get as a function of the size of these matrices. Okay, now if you go OpenMP and some sequential loss, then you get this one, which is better at the beginning, but later on, if then you don't have enough tasks and tools, then there is a saturation. Now, if you go this new maze runner, where I told you that all the threads are looking for the jobs, there is no idle time, and basically it's reduced to zero, you get this red one. And what is nice, it's an extremely fast increase, and it's almost a saturation at 2.5 teraflops, which is the theoretical maximum for this CPU that we use, this 7-volt CPU with 2 times 34 physical cores. Now, if you go for larger system like 5454 or 11376, these are, by the way, the largest calculations at the moment that presented in the literature. Then you get these curves here, which again shows you that with these new techniques, we can really get the full power out from the CPUs. Now let's switch to GPU. If you have the CPU GPU, then some part of the task can be transferred to the GPU. And then if the performance is measured again as a function of this matrix size, but as a function of the GPU card, then you can see that this is the CPU limit. There is no GPU, there is 1 GPU, 2 GPU, up to 8. You get more or less a linear scaling. Okay, and this performance, this obtained performance for 8 parts, that of course increases as you increase the size, because you can utilize the underlying power of the GPU more and more. And here, for 8 parts, we got 70 teraflops at the very end, which is almost the theoretical maximum from NVIDIA for its A100 cards, which is basically 76 teraflops. So this means this overhead from the I/O with these 3 structures and all these funny things which I just mentioned helps us really to push the performance up almost to the theoretical maximum.
And also, if you make the same performance measures now for different system sizes and also for different matrix sizes, so this is for 3,000, this is for 8,000, this is for 10,000, the size of the matrices, you can get these nice linear curves. What is rather more important is what is this diagonalization time. So now this is really time measured in minutes. So this is the time that is spent on computation plus the I/O. So it already includes the time to transfer the data from the RAM to the VRAM. So it's already, this overhead is included. So this is the CPU limit, which drops to this one when you use a single GPU card. Then you use 2 GPU cards, 4, 6, and 8. Now, if we increase the matrix sizing or the system sizes, we still get the same. So here is this red one. This is the biggest calculation in the world at the moment. This one drops to somewhere here, which we didn't calculate with a single card because we just have only the 8 GPU limit. We didn't want to burn the GPU for nothing. What is important, if you make a fit on this double logarithmic scale, you get lines. And the slope of these lines are 84, 84, 87. The idea would be -1. That would mean that doubling the number of the GPU cards would have the computation times. And you can see that we are almost at -1, so it's 87. We are extremely close. So that's basically how the overhead is hidden behind the computation. Now we can also look for the speed up so that we do a calculation with 0 GPU. And what is the speed up if you go to 1 GPU? This is this blue curve for this 1818 problem. Now, you can, of course, go to 8 GPUs, then you get this red one. Okay, so then for 8 GPUs, the speed up is around 20. And this dashed line shows you that where is 1, so that for these matrix sizes, it is better to keep it on the CPU the whole problem, while around 4,000, you can push it to the GPU, because this is this kind of overhead that you have to transfer the data, you have to do the calculations, you have to gather back. And of course, the question is that what is the balance between the time of the I/O, the overhead, the data transfer, and the computation. If you increase the system size, you get this speed up earlier and earlier for much smaller matrices, and for this big problem, this 113.76, you get the speed up of almost 25 already for matrix size 2000. So this is something that's nice, that with 8 cards, you only get a speed up by a factor of 25. Okay, now if you measure the performance again, this matrix size is also in teraflops. That's one issue that you can see this increase, the fast increasement. But what is amazing is that if you take again the computational time and you just calculate it for different matrix sizes in the CPU limit, you get these boxes, that one or this one. These are 2 different calculations, and also the blue one. If you fit it, you get an exponent of d to the 2.3. That means that originally, as I mentioned, the scaling is d to the cube. But just by CPU parallelization and all this kind of tensor algebra that is worked out, you can reduce it to 2.3. But that's blank. You cannot go further on because you use this 2.5 teraflops and so on, or you can do MPI parallelization. But if you switch to the GPU, for 8 cards, we reduce this to 1.25. As you can see, these are these curves, this red one and also this blue one. So that's something which is very important, that if you do this kind of parallelization issue, that how can you change the scaling? Of course, this will not hold for the full range of this matrix sizes, but there is a very broad range of parameter range where you can really boost the performance. And this is just something, another issue, that how this is the diagonalization time, which I just talked about it. So this is how it reduces as you reduce as you increase the number of the GPUs. Or if you go to a much larger problem from 1818, we go from 8,000 to 24,000 in these matrix sizes. Then this was this red one, and you can see how it drops. There is another part of the algorithms where I make some change. So this is when we say forming qubits, and sorry for this Q. This Q is not 2. I just want to say, so quantum digits means that in quantum bits, you have the 0 and 1 bits, which you make a linear combination. Now, in quantum digits, you have more than 2 degrees of freedom. It's not only the 0 and 1, but you can have 0, 1, 2, 3, and so on. So in quantum physics, you mix these kind of states, these basis states together. This is what Q was introduced here, but it completes with this Q. So please ignore this. In the revised version, I have bits larger than bits. So that's what I wanted to say here. So there is, of course, some other parts where you make this kind of transformation. Then there is this D to H, which means so from device to host. So when you copy back data from the GPU, there is, of course, some overhead. So depending on the load of the problem, this is this purple one. You can see how it drops.
it scales a little bit worse than the diionization because there is an extra ion. Okay, so that's nice, but what is also nice is that nowadays this energy consumption is so important. Since the eruption of the war, everyone is talking about all these issues that the energy price went up like sky. And that's exactly what, if you convert these calculations to GPUs, then we got these 2.5 teraflops, and then on this 7 volt, the TDP where data is 165 watts, which for the two CPUs would be 7.5 gigaflops per watt that you can get. While for this NVIDIA, the TDP is 250 watts, and then for reaching the 70 teraflops, we have something like 30. So we can get 30 gigaflops per watt instead of 7.5, so that the energy consumption is reduced by a factor of 4 or even more. And since in the calculations, the load on the GPUs fluctuates, you can get even a much better ratio. So you can think about it that going in this direction, you can really reduce the cost of the calculations, which if you want to do these large-scale simulations, especially in industry, but it's not just for the academic purposes, then this is going to be a serious issue because someone has to pay for the electricity. And that's super important to develop methods which you can put on the GPUs in order to reduce the cost of the computations. Okay, not going into details, but we can, those who are working in the field, we can use more symmetries, we can use more general tensor networks, which all work in a way that more and more independent tasks can be generated with better polarization. And also, if you combine this with the MPI, this is what we are working on. So we have an MPI code, we have the multi-GPU, and the combination of this will put us immediately to petascale computing so that we can really get from this teraflops to a couple of petaflops. And so let me conclude finally. What I just wanted to say that even this simulation quantum system, which is an exponential problem, due to mathematical developments, you can push it down to polynomial scaling. You can get out all the power of the CPUs, or you can basically reach over the theoretical maximum with for the GPUs. This kind of scaling, you know, when doubling the GPUs, basically half the execution time. That's basically 0.78, what we got an exponent, which is very close to -1. And this reduction of the D was, as you could see, this step by step. So, and the power consumption is by a factor of 4. And again, as I said, this kind of multi-node, multi-GPU will push us to the petascale computing. And I would like to thank you for your attention.
Thank you for your talk. Any question? Oh, already.
Maybe I did something like this, when simple question about the sparsity of this method. Are there for tens or?
Exactly. So you have here the full matrix with dimension D. So let's say it's a D by D matrix, and then it just splits up in this quantum number sector so that you form some kind of quantum number sector sparsity. So that this big matrix, which is D by D, you have these smaller blocks. In the blocks, it's a dense matrix, but it's a block sparse dense matrix representation. And that's why if you do this way, and together with the polarization, that's how you can make these reductions to 2.3. Okay. If you, so just simply using this kind of quantum number sparsity, you get a reduction from 3 maybe to 2.7 or 8 or something like that. Plus, of course, the polarization to the CPU, you get this extra factor or reduction, and then the next is, of course, go to the GPU. And that's why if you use more and more symmetries, you have more and more of these quantum number sectors, so that you can have a even better scaling.
Any other question?
Maybe this is just one thing that I have to mention, that we are very thankful for the Wigner laboratory, because this is when the beginning of the work started. You know, just to do the code developments, it was very important to have access somewhere, you know, where we could try, you know, the codes, not just on laptops. So that we started here. Then we use the computers. There's one node at the Utrecht University where we just use the one node with the 1-800 cards. And then there was something on Commodore, and then I'm just running most of the calculation in Stuttgart in the HPC and in the HLRS, where we have access to several nodes with several GPU cards. Each node has 8 cards, and so it's important. But it's very important that we had access to
the Wigner lab, because usually you can't go to the HPC center that here's a code, I would like to run the calculations, because they are asking, for this testing and performance results. So you have to convince the people that your code is good enough to be, allocating the computational time. So I think it's super important to do things and all these testings here. So we are really thankful for this.
Yeah, we can help you. And also more good news, I hear there is an extra computer coming to Germany, so I hope it will help everyone. So, is there any other question? Then we are moving to our next speaker, which is, if I remember, Don't be under, non più combate. So next speaker then Máté Ferenc Nagyegri from Stream HPC.
Okay, so hopefully you can hear me. So hello everyone, my name is Nincs bekapcsolva. Okay. Now it should be turned on. Oh yeah, okay, now it's turned on. So my name is Máté Ferenc Nagyegri, and I am working at Stream HPC. So we are a international company, and we are a services company. So we implement high performance codes. Either we develop ground up solutions, we port codes between APIs, frameworks, we optimize a lot of things. So that is what we usually do. And I also happen to still teach at the Eötvös Loránd University, GPU2 physicist. And we were lucky enough to work on multiple occasions on Khronos ecosystem, on Khronos standard ecosystem components, which this talk will be mainly about. If I would encourage anyone who is watching this presentation online or like offline later to check out my two previous presentations from last year's GPU Day and the one previously, because both of them touch on various topics that I will mention today, but it's not like that this presentation doesn't stand on its own. So yes, PDF conversion went well with the font. So I will be talking mostly about
about standards and Chronos standards, that is, so OpenCL and SYCL, and how these two technologies have evolved in the past year and what are some of the recent developments. So OpenCL, even though it was mentioned that OpenCL did not really live up to its promises in the sense of what kind of market penetration it had at large. It is still developing, and to quote a wise man, yes, newer standards and new features are always better than previous ones. And the important part of this is that OpenCL is still in development, and the things which the OpenCL work group develops isn't would large, so it's not in and of itself. But the features which get added to the standard are motivated by real-world needs and real-world use cases that need them. So some of the improvements which have happened in the past year or years, one of them is that Chronos has released a first-party OpenCL SDK, which I had mentioned in the previous talks. It aims to serve as the one-stop shop for developers who want to code OpenCL. So even though there are vendor SDKs which try to tune the user experience to their specific hardware and needs, there is a first-party SDK which covers all the vendors who really contribute to OpenCL and have compatible runtimes. And Stream HPC was lucky enough to be awarded this project. So the OpenCL SDK, the short big batch of features, was developed by Stream. And so it happens that the second round of improvements was also awarded to Stream. So there will be a lot of goodness landing in the SDK, in and around the SDK as well. So there will be more involved and more tricky samples. It will be easier to consume the SDK and also to install. So not just consume, but also install the SDK. So there will be a lot of goodness coming in the coming months. And also around, not in the SDK, but there are quarterly updates to the spec itself. So even though the major and the minor version are still OpenCL 3.0, every quarter there are clarifications, bug fixes to the standards, and also new features being added, which I mentioned, mostly in the form of extensions. So OpenCL did follow the suit of Vulkan, and instead of having like a huge gigantic core API, have a slim core API set and have everything else as extensions. And what are some of the extensions that have shipped recently? All of the extensions which are on the screen, they are provisional, so none of them are final, although I wouldn't expect to have huge changes in their APIs. So the reason why none of them are final is because they're still lacking implementation experience. So all of them have implementations. It's just that when applications start using them, that is when some of the shortcomings can manifest before these extensions are finalized. So one of them is CL Semaphore. If somebody is familiar with the newer graphics APIs, DirectX 12, Vulkan, or simply has had sufficient computer science courses, then Semaphore is a typical synchronization primitive. And OpenCL has had CL event, which was a synchronization primitive, but it is a multi-purpose entity, and something which is more flexible and serves only as syncing. It will be semaphores. External semaphore is a very interesting feature, which allows importing and exporting semaphore-like synchronization primitives to and from other APIs. So yes, I have mentioned DirectX and Vulkan as examples of semaphores, but other APIs have similar sync primitives as well. And this extension allows to interop with these other APIs and have an efficient synchronization way between APIs which are otherwise unaware of each other. External memory is a corollary of that. So it is, why do we want to synchronize? It is because we are sharing some kind of resource, and the resource usually is memory. That's how we can communicate between APIs, some piece of data. And external memory is the extension which allows exporting and importing images and raw data buffers to and from other APIs. CR-Chronos command buffer is again another interesting extension, and is also inspired by the low-level graphics APIs. So here the command lists, if I'm not mistaken, in the text, but I may be wrong at the exact naming. So the idea is that if there is some API overhead, and just about every API has some degree of overhead, if we have a calculation that constantly issues the same series of commands, then there is no reason for the API to make the same checks over and over again, whether this buffer has, where was it last updated, who do I have to wait for, all of these kinds of host-side overhead. So if our application is fairly repetitive and we're invoking the same APIs, then we can record them into a command buffer, and then we can, all of these checks can be baked into just single check or omit some of them. And these command buffers can be replayed faster than if we would reissue every single command again. And just recently, there are two provisional extensions to this extension. Yes, it is the mutable dispatch and the multi-device dispatch. So mutable dispatch allows to record commands, but change the arguments to the kernels or the size, the work sizes of the kernels in between launches. So mutable dispatch allows to record just the data dependency graph of various kernel launches, but change the arguments to the kernels in between. So command buffer, if somebody's coming from CUDA or HIP, it is the CUDA graph or Q graph. That is the similar feature. And outside of graphics, I believe the first use case in the compute domain was machine learning, where we really don't change the shape of our calculation. We just launch the same kernels over and over again. But also some other domains which don't really change the shape of the computation can also benefit from such an extension. I would also like to mention the advisory panel, the Chronos advisory panel. So it is a group of OpenCL experts, both from industry and academia. And if somebody wants to participate in shaping the standard itself, so somebody is a user of OpenCL or wants to become a user of OpenCL, like, yes, it takes all of my requirements except for just this one. So if OpenCL had just this one extension, or it would relax just one restriction, then they can join the advisory panel and participate in improving it so that it fits their needs. So naturally, the vendors are open for this because that means that there's more customer for the particular API. And overall, it will improve the quality of life of everyone who uses it. Participating in the advisory panel is free of charge, and the panel members get access to lots of materials that they wouldn't have access to otherwise. So naturally, somebody wants to develop the API itself, they have to be one step ahead of users and know what is going to come and what's being worked on. It isn't a huge commitment, if that is what somebody is afraid of, that they will be stuck in too many Zoom meetings. The meetings are fairly infrequent. So if somebody is interested, then drop a mail to the email at the bottom, which is mine, because I happen to be the advisory panel liaison in the OpenCL working group. And one interesting thing which kind of ties into last year's presentation is that OpenCL 3, having a very slim core profile, enabled it to be implementable atop other APIs, and the same is true in reverse, like other APIs can be implemented on top of OpenCL. And one such project of the Temple University and the Argonne National Laboratory is CHIP SPV, which is a HIP implementation. We have already heard of HIP on a previous presentation. One may summarize it as a clone or ripoff of CUDA. So the intention is to make it as easy to port CUDA applications to AMD hardware as reasonably possible. And one of the nice side effects of these gigantic supercomputers being built in the US, the El Capitan and the Frontier. Like Frontier we have already heard, and El Capitan is a sister implementation, which slightly smaller supercomputer. And luckily the American government has spent not just the money to create these supercomputers, but also to create the ecosystem and the software so that scientific applications can actually use these computers in a meaningful way. And because these supercomputers are on different architecture, they want to make sure that whenever something is written for one of these supercomputers, it can run on the other. And because AMD has landed quite a lot of supercomputer contracts recently, there's a lot of work going into HIP, and what allows that effort to be reused on other architectures is projects like CHIP SPV, which enable HIP code to run on any OpenCL runtime. And by any asterisk, it has to support SPIR-V. And the level of SPIR-V support across the ecosystem is could be better, so to say. Please watch the previous talks on that. So that is for OpenCL advancements of recent, and SYCL, if anything, it progresses even more rapidly. So just recently there was the international workshop on OpenCL and SYCLCon. So it is a joint conference between OpenCL and SYCL. And if somebody is interested in the program, then you can pop it up. Control F, search for SYCL, and there are quite a lot of hits. 92 hits doesn't mean 92 talks, it's a bit less than that, but this year's IOCO SYCLCon was pretty much dominated by SYCL, and that is still an understatement. So there were various interpretations of this. It's of what this means, like would OpenCL really be on the back burner, and is SYCL the only thing that people are developing in? And that is not the right interpretation. So if somebody pops open hgpu.org, which is a website collecting all kinds of research which happen, algorithm research on GPUs, and just look at how many OpenCL related articles are released, there's still, so OpenCL is still very popular among researchers in writing portable device code for any architecture really. So OpenCL in its, from a portability standpoint and the ease of getting into and adopting is still, I believe, in a better shape than SYCL. But SYCL is, there's a lot of work going into SYCL. So that is, I believe, the right interpretation of that discrepancy between the amount of SYCL versus OpenCL talks at IWACO, is that SYCL still has a lot of room to grow, and there is still foundational work needed in making it a widespread and reliable API. So some of the advancements, SYCL 2020 is the latest official standard of SYCL. It is quite a big change going from the previous SYCL 1.2.1 standard to SYCL 2020. On the right side is a non-exhaustive list of SYCL implementations and all their backends that they support. So the biggest change in SYCL 2020 is that it sheds off its OpenCL mandatory nature that SYCL previously had to run on top of OpenCL, but because of OpenCL's market penetration, that was relaxed in the newer standard, and now SYCL implementations that run on top of other runtimes, they can also become standard. And you can pretty much see that there is a zoo of implementations with an even greater zoo of backends available, which shows that there is a lot of interest in SYCL, and it is shaping up to be a nice interface to abstract away the hardware. And that abstraction is that the abstraction pretty much comes from OpenCL as the API. The way it looks, it resembles OpenCL a lot, and that's not by nature. It was meant to wrap OpenCL. And some of the new features which it introduces just make it much more easier to use, like universal shared memory, which I will get into in a coming slide. There is also an improved interface to accessing buffer contents and interleave host side calculations with device side calculations, and there are some nice device side algorithms so that one doesn't have to implement reductions from scratch, searches from scratch. And yes, minimally it's a C++17 extension, C++17 compiler, so the API itself mandates C++17. So unified shared memory, if somebody doesn't know what it is, but has programmed CUDA for a long time, then may have heard of UVA, Unified Virtual Address Space, Shared Virtual Memory, OpenCL, USM. So at this point, the industry is running out of 3-letter abbreviations for the same thing. It is essentially getting a pointer in whatever way, uploading into the device, and then dereferencing that pointer and accessing the data. So it is a pointer-based data access, and the level of what things can I do on the host, how can I manipulate that pointer and still upload it, get valid data, those kinds of things differ. And if somebody looks at this table of what kind of allocation types does USM have, like device allocation, where is it accessible, where is it migratable to? Really, this is nothing more than just giving new names to things that we already know how to use. So device allocation that we can only access on the device, that is the ordinary CUDA malloc. Host allocation that is accessible from the device, but it cannot be migrated to device, that is a pinned pointer essentially. And managed malloc, SVM malloc, is when we get a magic function, like a new kind of malloc function that gives me a better pointer that I can manipulate both on the host and the device and upload the manipulated pointers and still get my data. So this is like a poor man's summary of this table. But this is only to show that that SYCL is intending to be not much more than just abstracting away current practice. So SYCL intends on being like a really thin layer above existing runtimes and existing functionality. It doesn't want to reinvent the wheel. It just wants to give you a similar interface that we all know and love and know how to use, and just run away with it and use it on whatever runtime you have at hand. So how does SYCL then interact with its backend and code that exists, that already exists on these backends? The reason why SYCL is mentioned alongside GROMACS a lot of times, although today there were a lot of SYCL related benchmarks which were non-GROMACS related, but lattice calculation related, is that GROMACS is one of the flagship projects of SYCL. It is a molecular dynamics library, and the GROMACS development team prefers open standards over proprietary ones, as academia often does. And but then again, vendors prefer their own APIs that they have control over. And recently, so GROMACS both has a CUDA backend, HIP backend, and the SYCL backend. So it is one of those, and each of them are maintained by the project developers. So it is a prime candidate to match the performance of these APIs when they are literally running the exact same algorithm, just formulated in different APIs. And StreamHPC was involved in optimizing the HIP backend of GROMACS. We also took part in developing it, but mainly optimizing it. And also, this project doesn't just is a good example of how we can match and profile the performance of these APIs in relation to one another, but also how they can interact. So while we were working on the HIP backend of GROMACS, AMD did benefit from there being an upstream both CUDA and SYCL backends, because it does reduce the maintenance cost, that there is a lot of code which can be shared between these backends, simply because the nature of the APIs, as I have shown previously, they resemble each other a lot. So it's pretty much the same logic. And one can also draw inspirations from optimizations which are implemented in any of the backends. And also GROMACS benefits from there being a HIP backend, partly because of if some optimization is implemented in the HIP backend. So if AMD says that yes, we want to be more competitive against NVIDIA, so we are matching like the HIP backend versus the CUDA backend, and we do some optimization on the HIP side, then that optimization idea, or maybe even the code itself, can be adopted to the common code, the SYCL backend. And one example of that is one such optimization, which is a nice touch of the GROMACS maintainers that they attributed. That's one such code change came from an optimization that we did in the in the Hive backend. So this is the way when, so this is one possibility that these APIs can, and the code between them can interact, is that the API is inspired by existing practice, and when they live side by side, then it is really easy to take an idea or take an implementation from one side and have it directly benefit another code path or another vendor's piece of code. So OpenCL and SYCL, they are very similar to a lot of extents, and that is partly because if one tracks back how SYCL was born, is to turn OpenCL into a single source API. So in short, to make it the CUDA of Khronos, we could say that. And, but still, what is the fundamental difference from an end user's perspective? So if we say that, yes, they are pretty much the same thing, they can do the same thing, then which one should I pick? Which one is closer to my use case, or what will I be more comfortable developing with? And in my read, the biggest difference between the two APIs is really what they are. So if we look at SYCL and we look at SYCL 2020, then it is a C++17 API that I can write my code in C++17 both on the host side and on the device side, and it lets me write it in a single source fashion, but it also supports a multiple source type of development. Although most people typically use it in a single source fashion, that is the most convenient. While OpenCL has two sources by definition, we have two sides to it: the code that runs on the host side, on the CPU, and the code that runs on the device side. And while they are similar, the languages at least, they are different. So host side is typically ISO-C or GNU-C, or like Microsoft Flavor C or whatever, and same with C++, but let's stick with standards, so ISO-C, ISO-C++, and they can be really whatever language standard you want. So if you want to use newer C++ features on the host side, you are free to use newer C++ features on the host side. With SYCL, you may not get away with that because your compiler may not allow you to bump the standard higher than 17 in the single source use, that is. Simply because it is the compiler only has to compile C++17. I don't think that there are compilers that would really shoot someone in the foot in that regard, so to crank it up higher. But in OpenCL, as far as the standard goes and legalese, you can do that. And on the device side, you have a C11 flavor with the usual extensions to vector types, having synchronization primitives, and all the things that we expect from a device side language. And with C++ for OpenCL, one can even use C++17 on the device side. Once again, compilers may allow you to go higher than that, but typically not. So C++17 is currently where compilers mostly stand on device side code. And again, in OpenCL on the host side, you are pretty much free to use not even just C and C++, like we have Python bindings, Rust bindings, and all of those other language bindings, which come from the nice nature of it being a writer code and also your coding code in C++. Like exposing C++ in other languages is a bit more problematic. And the biggest difference between the two, in my read, is that there is an ABI in between the host side and the device side in OpenCL. So whenever I want to upload any kind of data to the device, I have to do that using a void star. So I have to erase all type information and then I can push it through the ABI. If somebody has used MPI, it is pretty much the same thing, that whenever I want to send a message through the wire, then I pretty much have to use lose all type information, cast it to a char star or void star and push it through the wire or the Wi-Fi or whatever. And OpenCL is very similar in that regard. If we want to push composite types like structs or classes or anything more fancy from host to device, then it is the programmer's responsibility to make sure that I have a matching type definition in these language flavors that I have. So I have some kind of C on host and some kind of C on the device, and I have to make sure that my structs are aligned exactly the same. This is something which we get in SYCL, in HIP, in CUDA, and all of these single source APIs for free, but in OpenCL we do not get that. And if that doesn't bother, like if that alone doesn't bother the programmer, then at that point these two APIs are pretty much the same from a functionality perspective. So I can use C++ on the host, C++ on the device, and if my type happens to be an array of floats, then what do I care? I can push it through and upload it in both of these APIs. So the convenience of not having to define types on both sides boils down as a downside when I have to compile my language or compile my program, because SYCL is a language. So even though that the API is box standard C++ 17, I do need a SYCL aware compiler to compile my code. If I don't have one, then I would say I'm pretty much out of luck. SYCL very much intends on staying such that library-only implementations can exist. But starting with the introduction of USM, that becomes harder to uphold. It's still possible to have library-only implementations. But if I want to have any kind of device acceleration, I will pretty much need a SYCL-aware compiler. And at that point, I have to update my build scripts so that it supports all the, or at least the SYCL compilers that I'm interested in. And that is something which I think the work group would need to, the SYCL work group would need to invest more in. Is that, yes, I can write code that that is standard SYCL code and it will run on all implementations, but I cannot really say the same about my, even like the best supported build system CMake in the SYCL ecosystem. I still have like the code building that will be pretty ugly. Whereas, and it's like I have to handle every implementation explicitly. And we have seen that there are a lot of SYCL implementations and they really don't agree on the interface of how to have them. Whereas OpenCL, it's a library, and we all know how to pull in a library and just link it to my code. So OpenCL, from the compilation model perspective, it is infinitely more simple than SYCL. And because of this, it is still a lot more portable than SYCL is. One of the big problems of SYCL is that essentially every implementation is a Clang fork, and everybody has a Clang plugin that they implement. Like the SYCL compilation is a plugin on top of Clang, and so it happens that plugins in Clang only work on Linux and not on Windows. So essentially all SYCL implementation Windows ship a full-blown Clang fork, and they cannot use just that additive plugin nature on top of Clang. So at the end of the day, it really depends on, like, do you have existing code? Do you like the single source nature? and is it mandatory? And that is the reason why one of the reasons why OpenCL did not take off is that there was a precursor, CUDA, and a lot of projects built into their build definitions and the entire code structure, that single source nature, and that is something which OpenCL couldn't give. And that is why one of the reasons why it failed to have that market penetration. And why it is, why things are the way they are currently. But at the end of the day, it's really up to user preference, and even current use shows that OpenCL is being used for a lot of research code out there. So that is all about recent OpenCL SYCL advancements. If somebody is interested in working on similar things, improving, optimizing, porting popular libraries, or writing solutions from scratch, then we're hiring. And with that, I would like to thank you for your attention.
Thank you for the talk. Is there any question?
It's quiet.
I know. Yeah. Don't talk.
I don't have a question. So, as you know, or you know that the GPU cake is split in many parts, and larger and larger parts occupied by machine learning community. And my question is that what are the developments like SYCL and OpenCL towards this direction, and what do you predict and will it happen that I can run PyTorch on the OpenCL?
So if you check out the iVocal program, there are a fair number of AI-related talks there. OpenCL itself has extensions which specifically target machine learning. So introduce built-in functions which expose the typical algorithmic shapes which are used in either in training or inferencing. So there is work from the OpenCL side on enabling machine learning to a wider audience. And the same is true for SYCL. So SYCL has a deep neural network library, SYCL-DNN, which can be used today to accelerate machine learning workloads. In my read, in the future, I think that like the vendors themselves, they are very motivated to provide the best possible hardware to doing inferencing and training. A lot of companies are interested in creating their own hardware. So just recently, news came up that Microsoft intends on creating their own neural processing unit. So everybody's all over it. From the software side, everybody's trying to push their own APIs in doing that. And because like everybody wants to secure a bigger part of the cake. And I personally don't really follow the machine learning libraries, like what is the platform coverage of them. TensorFlow, PyTorch, and the popular frameworks, they all support the vendor libraries. So every vendor makes sure that their vendor library is supported by TensorFlow. I don't want to say like what is the state of the standard solutions, because I don't regularly develop in that domain. So I don't want to say anything which isn't true.
So thank you, the extensive talks on the news from the Kronos group. So let's close today's session, and thank you all of you for coming today, and I'm waiting most of you back tomorrow. Small service recommendation for the morning. So as most of you could find out, it's quite hard to get into the institute. So we recommend to come half an hour earlier than the starting of the event. So you could proceed with the checking on the reception. So thanks for everyone to come.
Az mindenkinek, ez nem a magasságtól.
Holnap nem tudok jönni, de szerintem
nem hosszú
egyre jobb egyébként szerintem.
Amit reggel, hogy
Olyan őszintén, nem az elején úgy volt azért, hogy kinek van kérdése, meg van topikok, meg minden, de szerintem
és akkor azt kérem, van egy amikor egy kicsit I think you will be okay, so I have a couple of questions, so maybe you see what I yes, just put my yeah. So the thing is, and then you should see just this out in us, which is so you can go together like this, you get this side, and you have to go to the other side of the notes, the opposite direction. This side, you know, is the one that I think I can't remember. Either it's written because of us. And which one, the other than is so if you want to go from here to there. Oh, okay, then also I think it's very. It's not very because now it's still, I mean, so it's happening. Then from there we can go down, just always going down. So from the top, there's the wall of the castle. If you go down 15 minutes at the hotel. Yes, from there. I mean, just to save time, and we're going to put from here. Just Matthias. It's in the Latin and without the apostrophe. Matthias. Yeah, so this is 1, 16, they both goes into the direction. And then yeah, circle and the last step you see here that almost down. And here you see it has to cross some of those, but in a nice way, and then it goes up to the it goes on the range of the consultant. Yeah, and we are living here. Okay, so it's from here to there. You just have to find the propellers going down way, but if you have the Matthias just here, and this is this this is some parameter. If you go to here, which was the wall, then you have a stair where you want to start going down, and that's the wall of the house. So it's very high, like 3 meters. Yeah, then you have a lift over which is down, and then you once you go down, either the lift or you can have further steps almost right to the bloody field. And then you must cross to the other side.
Okay, so the thing is the capital of the church.
So you can spend a lot of time here. It's highly important to have a view to the other side of things, but the castle area is very nice. So 4 houses and everything is there. White House over there, but many things. So it's even very nice if you go to the castle walls and you take a big run, but that takes about 1 hour. And don't spend money there every month. If you want to, so if you go back to the Serkama, I mean, where you change the bus, this is the moment that the Finnish commercial center I told you. But a lot of friends just first and from the, I mean, this is what actually is. So I just used to walk when so here the shops are open until 9 or even later. Then there is a grocery also, I mean, which super important. But I think the supermarket here is also next to the hotel.
You show me.
And then that is also, but it's not, I mean, shops 7, 8.
Yeah. Yeah, and we go first one because I can't see the first like that.
Okay.
I don't know. So I don't know if everybody having yours. So when they chat. No, just.
No, but I mean, you will see if you are at the castle wall, you see the airport water. So it's, I mean,
So maybe okay.
But okay, just to be safe.
Okay, so from from the secondary change for the next bus, it's only little.
It's a small bus, it goes very slowly because it's almost everything in constraints and pedestrian areas. So, I mean, some special permission you can travel by car, and it's on the bus and all the time. And maybe I could wait tomorrow to I can let's see that.
It's okay, I can go and
we can discuss in lunchtime.
Sure.
So many various things.
It's like very various topics. Like we were so different.
So, and you know, you might be thinking of as well. I don't think I have to but the competition because they're doing many things. So you see these trains talk of Yakovas is QCD for a long time, and now we changed artificial intelligence using the randomization method coming from the theory and it's super cool. Of course, they decided to but after your point that the previous version of the system, you know, was developed by us. So the Budapest group designed and built, so all the couple, this is what I used to say, that up to until run 3, until end of run 2, all the bits are on the Hungarian system. So that so they have a group of people who are very in their teaching days, and the CRU cards and designing in the first version, and even the front end and the delivery. So the whole board thing was made in single cards. There's made by the time the name is and the company we have for example experience under the company so you all the system was really very and we still have some of the guys, unfortunately the two very key experts died, they were playing and but we still have some was designed by us but personally so we have this sometimes popping out. So they all we do is see the data store or the development of which is and the problem, the big problem, which faced now because of the non-management of people, that GPT was trusting there's so for example, in PayPal, and using other so this is why we are developing this low power between us. It's a asymmetric link, so it's us like one direction means slower to the other, of course, and to push data just from where we can and this is more faster, and but on the other hand, on the side is backward compatibility. So I mean, after my scale, you don't have to change, but the other side you can get a new version and just vice versa. So as we are going up, it's for Alice Swing, but for the next support. So now there's no other option. I mean, there are no available things like this. No, there's a certain number of these, and to do this in a large scale, it could be okay, but it's not it reaches 100 is not a large scale. So it's like, you know, 100 you can buy for 1 million and they have 1 million, this is also 1. Okay, so now it's not going to be the place. They trying to all the test devices and the analysis is ongoing, like everything, like we got once they have to say that it will be programmed in FPGA and what we are doing now. I'm trying to take
No.
Okay, so volt kétszer olyan, hogy lesz a gázvilágosság az egyik nap. Sziasztok, vagy lesz vergényes srácok, ők voltak, tulajdonképpen ők voltak a tesztelők, tehát én írtam egy levelet, amikor megjöttünk egy hét, mi az, aki ki tudja? Igen, valamit megcsináltuk, és megadtam, hogy nem tudtuk tenni. És meglettem, igen, mi is meg. Hát az nem jut, hát én rákoljuk, csak nem tudják. Azért a